Okay, thank you for joining us today. I'll start with an introduction to the event. My name is Kais Alrawi, and I'm co-organizing this event with my colleagues, Dr. Nirma Kridge and Javier de Castlier. And this event is organized together with the AA Public Program and the AA Visiting School. And we're excited to have you all here joining us. So today we will have 4 unique sessions. And between us, the 3 chairs of the event, we will be chairing these sessions. And I'll give you a quick overview of our schedule for the day. So we'll start off with the desert session with 2 speakers. And that will go for about an hour, a little bit over an hour. And then we'll move on to the Oceanic session with 3 speakers for about an hour and a half, and then a short break. Polar session, hour and a half, and then we'll wrap up with the space session. So before we get started into the event, I will be giving a quick introduction to some of the background of this event and its relationship to the visiting school. So about 8 years ago, I initiated a visiting school in Jordan, part of the AA, where we did workshops over different summers, different years. And this actually ties quite well into our event because we explored different locations in Jordan that had natural extremities. So we spent a couple of years going to the desert, 1 year to the Dead Sea, and another year to the Red Sea. And throughout that, we developed a program where the students would develop designs over these workshops that are based on natural extremities and the use of digital technology to design. So I'll show a few examples of our projects. This is one from the year we did at the Dead Sea, inspired by salt crystal formations. The students developed algorithmically these dome structures that were inspired by these. And at the same time, we invited international guests such as you see here, Benjamin Aranda from Aranda Lash, who have focused, almost their career on this type of research of these kinds of structures. We spent some years also in the Wadi Rum Desert, which is quite unique. And the students looked at different interventions, such as reshaping the landscape and creating designs inspired by the unique desert. And similarly here, we had guests who were also interested in this. Ross Lovegrove joined us in 2014 and lectured from the middle of the desert, which was quite exciting. In another year, when we went to the Red Sea, we looked at coral structures and how these work, and also thinking about designing floating structures that live within the ocean and can serve as viewing platforms. So this ties quite nicely today to our Oceanic session, where we'll see some real world examples of that. And for the last few years, we've focused quite a bit of the work on planet Mars and space architecture. The tie-in is the Wadi Rum Desert is one of the places in the world that has quite a similarity to planet Mars. It's where they filmed The Martian. This is how they filmed it without editing, with a little bit of editing, mostly the sky. And throughout the last few years, we've been thinking about designs for space, which ties into our final session for today, which is the space session. Looking at different ideas such as nesting structures into the natural formations on multiple sides, that creates radiation shielding, which is an important aspect on Mars, or thinking of underground structures to be efficient and work that. Last project I'll show from one of our workshops last year, and you may have seen this image over many of our graphics. This is a project that was in one of the online units and looking at procedural modeling and exciting tools that we can design with. So we actually have 2 workshops that are going to be occurring after this symposium. One of them starts on Sunday and Monday, which will be both in person and virtual, and another workshop a couple of weeks down. So we're going to give you just a brief overview about these workshops, and then we'll get started into the event. So I'm going to ask Levent to say a few words about Unit 1, which he will be leading.
Hi, I'm Levent Osru. I'll be running the Unit 1. This is second year. Essentially, I'm interested in the intersection between additive manufacturing, procedural design, and space architecture. This intersection was something I could explore at my diploma work at the Bartlett. And now I'm part of the space architecture team at Hassel, where I work on projects of like commercial space stations and lunar habitats. So regarding this workshop, we will actually have two options: in person in LA and online. But it will come down to going to a specific site on Lucerne Valley, owned by NASA's Rob Miller, called Skyworks. And we'll be looking into ways of designing for the site a research facility or a Martian analog, let's say. And in doing so, we'll think about the other examples on Earth, which act as analogs, such as Antarctic bases, oil rigs, and so on. And we'll use Houdini to have a procedural design approach to design systems rather than just objects. And we'll question things like centralization, decentralization, and other qualities of site, curvature, altitude. How could this affect the design overall? So if you're interested, you can email or contact us. There are still some spaces left. Thank you.
Thanks, Levent. And we'll have a quick introduction by Ella on the second unit, as well as Norma.
Hello, my name's Ella. I'm an artist in Bristol, UK. And we're running this workshop, which relates to a public art project that we're leading called Building a Martian House. So for several years, we've been working through a co-design process involving all kinds of different people, from school children right through to rocket scientists, to build a prototype of a Martian house. And we're going to be building it in Bristol in just a month or so's time. So one of the images there you can see is the mock-up of what it's going to look like. So overall, the project really looks at how the restrictions of Mars might inspire designs on Earth, where we could live more resourcefully and with better well-being. So it's the environment of Mars helps us to look at resource scarcity. If we lived in a place where things weren't available on tap like we're used to, and if we need to fix everything when it broke. So yeah, Norma, I don't know if you'd like to say a little bit more about the brief. So the workshop it's an opportunity to design something for the interior of our house, of our Martian house. And we're thinking about objects that provide a look at what the inhabitants of this house might experience on a day-to-day basis, that will give clues for the public about how people might live in this house, focusing around time and around exercise.
Hi everyone, it's so exciting to welcome everyone here and to be hosting it despite the extreme weather. We've got some people in the AA gallery with me. In terms of the workshop, it's also quite incredible that it's actually going to be built. So it's starting on site in March, and then it's going to be built by the end of April. And it's very much, I think the way the artists see it is very much a blank canvas for people to come and be involved and tell us what they think, what living on Mars or even living on Earth with more in smaller, more confined environments might be like. So the workshop will focus on two aspects. One is time, the difference in time, in the perception of time, as well as because on Mars there's no the differences between different seasons. Seasons are much longer and less contrasted in terms of there are only really two. And also an issue or a challenge for many who have to work in confined environments to how to stay active, how to keep on exercising, and how we can make it more productive and more fulfilling. So there are still spaces, and it's going to be between 5th and 7th of March. And we're working with 3 different time zones again, so that's why it's going to be GMT between 3 and 9. And please contact Mars Visiting School in case you're interested in applying.
Thank you, Norma. Okay, so we will shortly get started with the event. So we have 11 really exciting presentations today around the 4 themes. And overall, we feel this is a topic that is quite relevant with extreme environments and ties into many different things such as climate change, what we're seeing even today in London. Hope everybody's all well and safe. And also in general, resource efficiency and the use of materials and how we think about that. And also how different environments can help us think and design on other places as well. So we'll hopefully pull some parallels throughout the workshop and a few kind of just general things. Each presentation from our speakers is going to be 20 minutes. And after that, we will follow with a Q&A and panel for about 30 minutes. In the Q&A, we're going to invite any of our speakers to also interject and weigh in on their opinion from the 11 different presentations. So it'll be, I think, an exciting discussion. You can submit your questions through the Zoom questions feature. I believe you can do so either with your name or anonymously as you wish. And you can do that both while the presenters are presenting or at the end towards the Q&A time. And the panel chairs will be looking at the questions and using those towards the discussion. So with that, we will get started with the desert session that I will be chairing. And I will be really excited to introduce you to our first speaker, Arthur Mamumani of Mamumani Architects. I've been fascinated with Arthur's work and how he's been using digital fabrication technology to create really exciting designs, particularly fascinated by the work he's been doing in the desert, which I hear today he'll be sharing some things he hasn't shared before. So that's really exciting. Please join me in welcoming Arthur. You can go ahead and share your screen.
Thank you so much. Let me share my screen and please let me know if you can see everything.
Perfect.
Is it the right screen? Are you seeing 2 projects side by side?
Yep.
Brilliant, brilliant, brilliant. So I'll start my timer because I know I'm limited to 20 minutes. Perfect. And I shall start. Well, thank you so much, everyone. And thank you for allowing me to kickstart this session. It's quite exciting to talk about the desert in many ways. Well, first of all, because I've built projects in the desert, but also because it brings back so many memories. And indeed, I'll be showing you a lot of the process and what happened whilst building this structure on the left. And eventually we're going to go back and build a structure on the right. The one on the left is called Galaxia. It's a project that we've done in about 18 days with 140 people. It's about 60 meters wide, 20 meters high. And it sort of reflects the Burning Man values. And I'll try and explain what I mean by that, because desert is not just the place where we build, but it's also part of the values of Burning Man. And it's a community. And what the founder of Burning Man said is that real communities grow out of a shared confrontation with survival. They're produced by the sentiment of shared struggle. and that the situation in the desert is an incubator for community. I find this really fascinating because really the first time I went there, I thought, oh, that's just a party, you know, I didn't realize that this had a much deeper ramification with the communities of Burning Man. So I'm going to explain a little bit more, how does that relate to the desert and why it was important. But I just wanted to mention a few of those. And there's another quote that I really love and that resonates with what I'm going to show you. I think it's from the book Sapiens. And it said that maybe we switch from foragers to people that raise crops, not just because we wanted to increase food supply, but because we wanted to build and run temples. And that says a lot about why we turn deserts into, I don't want to say civilization, because Burning Man is not that, but all these are metaphors of communities building things together and sharing the struggles to do so, and therefore building social links and becoming more than the sum of the parts. So just to illustrate a little bit the struggle, this was really at the very end of the build, and I'll take you through the whole thing, but I just want to kind of emphasize that this was a hard build and that it really pushed us to the very edge in many, many different ways. And I'll tell you all about it. But maybe, if, I don't know, I can't really see you guys, but I don't know if any of you have gone to this place. It's a bit unique. It has 10 principles, including radical inclusion, gifting, and the one that I prefer, self-reliance. And you'll see, and I'll try and show through different projects, not just the ones at Burning Man, how this is permeating the entire work that we do, and how building in the desert has taught me about the life cycle of materials, for example, or how to be considerate about the energy uses and so on. It's strange, but when you build where there is nothing, you learn how to consider every single thing. Because it's a blank canvas, you cannot start from something, so you have to consider everything, and that's really fascinating. And that's why I started bringing students to Burning Man, because I thought they would maybe consider things like the sewage, which are things that we don't really consider in cities, things like that. So not just the crazy shapes that we built there, but most importantly, the life around it, and how to actually bring things to the desert, or how to consider the constraints around it. And so that's really important in the work that we've been doing. And I'll show you how every project informed each other and the path of learning how to go from one to the other. Desert is also present in our work in terms of use of material. This is sand printing that we've done in Saudi Arabia, another completely different desert. But I thought it'd be worth showing this idea of the essence. Here we're using a lattice. Galaxia is also a lattice. And then displaying the use of forces. And so every force is being translated into thickness. And so it kind of translates into how to use the minimum amount of material and using local material. Now, could we print a temple in the desert? I mean, potentially. I mean, and in a way, this is in our entire practice is always thinking like, this is in Hackney Road, by the way, we're based in London. And we always try and think like, what would be the material that is the least kind of harmful? What is the material that can be represented or made locally, so that we actually can display not just the drawing or the representation, but the actual thing. And it's really important for us. And so we've developed a fabrication space here in East London that has huge 3D printers, that has crushers, and where we can actually test different materials against one another. So this is bioplastic versus petroleum-based plastic. And this is a life cycle assessment, and these are the different axes that one can consider when comparing one material versus another. We've used this for many of our projects. We've used this is for COS, conifera, a huge PLA, bioresin, fermented sugar structure. Or this one was a kind of laser cut structure we've done for Brewer Happold, where we ended up being the contractor. I think at the I studied at the AA, and we were being shown all these, it was a long time, 2008, that I graduated, but there was a Fab Lab. And when I graduated, I was just like, what am I going to do with all these skills to do 3D printing and so on? And are we really going to be contractors of pavilions that all the pavilions that were being built by Charles Walker and so on? And actually, yes, digital technology allowed us to become builders, not just designers. And so that quality of being able to be the contractor of your own project really changed everything, I think, for architects of our generation. And so this is, for example, we were general contractor for the interiors of Orange Telecommunication. And this is based on steam bending straight pieces of timber instead of trying to cut them with a CNC. We try and always reuse material. This is a reclaimed bridge in Bali that was bought by our client. And then the skin around it comes wrap up around the structure. All right, I promised you to take you to Burning Man. And I just want to add this other element of Burning Man, the art. It's a city that's meant to have no spectator. So it's not like you have a DJ that comes in and there's a lineup, etc. No, everyone that comes has to bring something, has to be an actor, an artist. And the whole society of Burning Man, the reason it's that shape is because everything is around the art that's being produced. So, and it's not kind of coming from nowhere. There's a whole Californian ideology. This guy, Buckminster Fuller, that you probably know, was a real genius inventor. And he's a very activist engineer, architect, let's say, inventing the future. And for us, it was really important to understand how to consider architecture as part of a bigger spaceship. Buckminster Fuller called it the spaceship Earth. And here you see the students in the camp. And this is called the hexayurts. And it's a whole open source system to use insulated board to create a series of yurts, basically. And it's really fascinating because it's the kind of boring stuff you don't see because people emphasize the art and so on. But Burning Man is full of these innovation, like little innovation. And so we told our students, how do you minimize waste? And so these are based on half sheets and basically in a reciprocal way forms these domes. And so this is a typical project that we would encourage. But Burning Man also enjoys, a slightly more spiritual notion of fractal and so on. So the project that were selected at the beginning when we went with our students were things like this. This was inspired by a crystal on one side, and these were some crazy reciprocal structures. Now, I show these two projects before I move on to Galaxia for the other half of the talk, because this was a really good lesson. I'm obviously a geek and I love Grasshopper and so on. And this project on the left was the most complex Grasshopper thing ever, because it's like this kind of complex numbers based rheotomic surface. And then on the right, it's just offset piece of 2x4 timber. And I was just like, oh, yeah, not so excited about that, really excited by that. And then I started like helping the student on working on all the pieces, and it was a nightmare. All the pieces were not numbered. And the other piece that were made of the shelf timber just fit perfect on the truck. And I remember the truck driver telling me like, the most important designer is the truck driver. And it made sense. When things don't fit on a truck, it's a nightmare. I mean, we just put all these pieces at the back there. They weren't ordered, they didn't have names, and nothing really fit. Nothing was finished really. So the piece on the left was just left like that. And the one on the right was perfect. People loved it. And it's really just pieces of wood offsetted. And I was just like, I felt like I was like a Grasshopper loser, like, because I was so excited how innovative this whole was. And so when I kind of came back, we worked on this project, Tangential Dreams. And this was a bit like the baby of the two projects. It was symmetrical. I don't know, symmetry excites me now because then you can repeat pieces. But also it was very simple. We were just expressing the movement of a graph through tangents. So a curve made of straight lines. And we had this matrix of numbers that we could cut with a circular saw in a small space. The entire thing was then animated with LEDs, and people could write down their dreams on each one of the tangents. And so it created another element, an added element, which was about people. You know, same as a geek, we don't necessarily think of the experience of people and how they can interact with the structure, and how it could mean more to people than just architecture. And this was incredible, probably one of the largest CNC building I've ever seen. And this was the temple the year I went to Burning Man. And people were starting to write really personal words on the structure. And I came in there, and then I sort of realized people were talking about babies and so on. And I was just like, I started crying, and I just didn't understand why. And actually, it's because it's a temple. It's a secular temple, not associated with a religion, but it sort of connected people into deeper mourning and joyful things. And at the time I was working on this project for Virgin Galactic. It was a big hotel for the astronauts. And it was interesting because it was also in the desert, another desert, but it was based on this sort of Fibonacci symbol, you know, the universal spiral. And we used so many different tricks. And I thought it'd be interesting to show you that also because of the way it was generated in relation to environmental criteria. So the structure was growing we're using recursion. And whilst it was growing, we could test it against the sunlight, let the direct sunlight when it was cold, and diffuse it when it was hot. And this showed a little bit like how one could kind of create something that can grow as opposed to being top-down, something I learned at the AA, the importance of letting go of top-down designs. I'm sure it's the same for you guys. But also we worked with an environmental engineer that told us that because we had so much thermal mass, and because we created a stack effect, we can get natural airflows, and there would be some water on the edge of the structure so that we didn't necessarily need air conditioning. And I think that was really exciting, you know, just in terms of the environmental performance of that structure. But then also, whilst I was Burning Man, I was like, you know, usually temples have domes that encapsulate, they're a symbol of sort of owning space to some extent. And the inverted dome is sort of open to the sky, and it's a really nice contrast with the flat landscape. And so that's sort of the spirit around Galaxia came from all this thinking, you know, a sort of blank canvas with a dialogue with the universe, and how we could mimic the movement of galaxies and the black hole in the center, bending space and time, inviting people on the edge and making them go, you know, a little bit from a human portal to a more spiritual portal. Now, I said I would show things that I didn't show in the past. Galaxia was meant to have a roof. This is the roof. We never put it on because one, we run out of time to build this structure, and two, there was such a mathematical purity on the structure. I don't know if you can see, but it's like a bones, bare bones. There's no columns. Every single piece is acting as part of the grid shell. And so we looked at it, you know, just like, maybe we'll just leave it like this. And that's the kind of stuff you can do at Burning Man. You don't have a planning application or anything. But so that's a real part of the experimentation, and everyone participates. You can see the little hearts here on the side. Those are people just stamping hearts. We had these benches that people could use to put their bikes and so on, that were an extension of the petals. This is the city at the back. You can see this was made by Bjarkingos. That was a big dome. And they struggled too, like big time, which was really interesting. I mean, we all struggled together, but you know, it was interesting to see how everyone could struggle, and we would tell each other struggle in the evening, which was very nice. And at night we had these lights that were on the edge, on the ridges of Galaxia, and we had these teardrops in the middle. So I'm just going to tell you a little bit more about how we made it. And I know Kais asked me to show you like how we actually, you know, adapted construction to the desert. I think that's really interesting, because it's not your usual concrete foundation piles. For example, I mean, we had these petals. We called them petals at the beginning. They became bananas at the end. They were all connected by this bike wheel in the center. And that's because we couldn't dig foundations. And so we had this giant bike wheel that took all the kind of spreading forces. And then we built all these modules to test them in a shop. So I think what's kind of interesting is like the prefabrication versus what can be done in the desert. Of course, prefabrication is key. And of course, it has to be as simple as possible, because the volunteers that we had were actually people that were not carpenters or anything. So we did these triangles made from 4x4 and 2x4 timbers, and they would assemble themselves as modules. And so this was the only information that the carpenters needed. These were, you had a setting out and you had all these modules. They only needed the outside geometry, and we had to do it in inch, which was a bit of a nightmare, but we had a few shops, one in San Francisco, one in Reno. This was in San Francisco, building the altar in the middle using these hemp fibers and so on. This was our San Francisco workshop, tiny, where we built the wedges in between the petals. It was really interesting because the structure evolved over time, but we realized with the rotational symmetry that we only needed to understand really well one of the bananas, really, and the relationship between the elements. So it started from one-dimensional timber, went to two-dimensional, three-dimensional, and eventually folded into the modules. 400 of these. You can imagine the drawings had to be pretty simple, using off-the-shelf stuff that we could find at the local B&Q, Simpson plates, etc., etc. The more we had custom connection or digitally fabricated stuff, the less this was going to be likely, because imagine one breaks and you're in the desert. So we had just that bit was based on digital fabrication. The rest was all off the shelf. We had this cryptic naming system, M1, M3, everyone spoke like this, like robots at the end. But really, we had a lot of people on site. So you'd imagine that what usually would be complicated, because usually you don't have enough people because labor costs a lot of money, and materials are usually very cheap. This was completely inverted. We were all volunteer on this. And so we could celebrate the act of being together building this. So this was our village. We were all together. To give you a sense of scale, I put a picture of it, but this was where the shops, the workshops, and so on and so forth. And this was a matrix of all the elements we had to assemble. This was the sequence. So to give you a sense of scale, there's a little truck here, and we would actually start by having two scaffolds in which we would build a structure on one of the scaffold, a lower crown and an upper crown, and then we actually had to put this up. And one of the reasons we started from the top is because for the spirit of the people that were with us, like if you put something up there from the very beginning, you can imagine that people know what's going on. And so it was really great to see that, and really accelerated what ended up being a really, really complex site. So this is how we put up the structure on top of the scaffold, how we connected back the structure to the ground. Just to show you that there was this moment we had to actually remove that scaffold at some point, which was really, really scary. And the engineer that were involved, format engineer, gave us a really interesting challenge. They told us, all right, these are the forces, the newtons, compression for negative value and tension for positive. Let's maximize tension as much as we can to minimize the use of material. So bear in mind, we were fundraising by that time. And then this is the equation. This is how much newtons it takes. And so deal with it. So basically all plate was different. The number of screws differed based on the amount of forces. And we would alternate the 4x4 inch and 2x4 inch. I'll slip through a few of the images that I want to show you. The challenges of, the timber drying, not being at the right scale. We had to actually connect things with ratchet straps because bolting at height would be absolutely impossible. We had to have these giant footers that were connecting the modules on the ground. We had to serve food for about, at the end, 200 people nonstop, and explain every single day the tasks that were at hand, build showers because no one could shower. And so buy and rebuy some chargers so that we could actually cater for the alkaline ground. And we had our actual truck and we became a bit crazy, people dressing up as bananas and writing down the most complicated diagrams together. Everyone had to interface with one another for about 18 days. Each one of those days would be marked on our arms, remembering how much time we had left and running around with our drawings. People thinking I'm some kind of fascist. This was in the toilet where I asked for more triangles. And so it was really beautiful because as we opened the space, people would finally use this place as a temple and share the most moving element, like offering. I don't even know how to call them, but it was absolutely beautiful. I got a chance to get married here with my wife, which was, another way to change all this stress into something positive. And so by the time we reached about day 7, the structure was in all its strength, sort of volcano on Mars, really, as relevant for that session. And then we burnt it quietly with 70,000 people around this giant chimney, which we then had to clean and clean deeply because we had cables running all over. It was a real mission. Okay, so I think I've passed 20 minutes. I'm at 21. Just saying that we will be building this structure this summer. It's called Catharsis. We won't be burning it. We'll be disassembling it and then bringing it back to the Somerset House. And it will be a giant art gallery that people will use for, performance and exploring. And it's currently in another space in the metaverse, in Alt Space. If you have your VR goggles, you can come and meet me there, and we can go to both Galaxia and Catharsis. I shall stop it there. Let's do this together if you want to come with us. Here, back to London. Back to you guys.
Fantastic. Thank you so much, Arthur.
Thank you.
Okay, so one moment. Okay, so we'll move to our second presentation in the desert session, and I'm really excited to introduce Mazen El Ali. Mazen has, I first got to know Mazen through the AA Visiting School in Jordan back in 2014, the first one we did, and Mazen joined, and he joined us every year thereon, and he started teaching with us there. So I've known him for quite a while. He's basically the best student you can ever imagine, and then he also, became a great architect and very ambitious and very aspiring. And I'm very proud of everything he's doing, including his practice from Atelier that he'll share with us insights. And we continue to involve Mazen in a variety of things. So thank you, Mazen, for joining us. And please go ahead, share your screen.
Thank you, Kais. I'll start sharing my screen right now. Okay. So is my screen on? Can you guys see my screen?
Yes, perfect.
Okay, great. Thank you, Kais. Thank you, everyone. So basically, I'll start the timer as well. Okay. So basically, hello, my name is Mazen. I'm an architect. I'm based here in Amman, Jordan. And I run a small atelier called Drum Atelier. And Drum is a place in the desert in Jordan. Actually, Kais talked about what we have done there for some time with the AA, and it's been super inspiring to me. So I decided to move my practice to inspire from the desert. So basically, this is another picture of the location. So I started my practice as soon as I graduated, actually. So when people have some difficulty doing things the old traditional way, they always come to me because I don't know the old traditional way. I tend to have started doing stuff my own way as soon as I graduated. This is Amman. So you can see the huge difference between the desert environment and the city we live in. It's clusters of houses built on top of mountains, and Jordan is pretty interesting for its environment. So you could be at the forest half an hour, you could be at the desert another half an hour, you could be in the middle of the sea environment, and then you can go to the Dead Sea. So you can see mostly all environments in the region we live in. So that's what makes it really unique. So Drum Atelier is specialized in doing tasks that are a bit hideous, and that's why I think we succeeded in the beginning. So what we do normally is we take either full projects or we take on tasks within certain projects that are that require our input, basically. So we do everything from fabrication to building skins and in architectural design. These are some of the projects we have worked on in collaboration with studios like UNS and Arctic as well. So we have Al Wasl Tower, which is the world's largest ceramic facade on a twisted tower in Dubai. And this is Rolaya train station, which we helped design the facade, and we'll talk more about it in a bit. And this is the Qatar Marina Lucille, and we've worked on fabrication of the outside panel and the interior as well. So using and utilizing digital fabrication tools and means to achieve the optimum solution for complicated matters or structures. And these are some of how they look right now. Some of them are a bit more evolved. But recently, this is the last image we have took on site. So we talk about desert, and when I look at this picture, I always tell people to tell me what they see. And it's quite interesting to look at this environment, as people see arid land, but I think most of the architects you're going to meet here see opportunities. They found resources that are not introduced into the construction business today. And this is what the space exploration program is all about. It's about looking at resources that we haven't used before. So I invite you to look at this picture and think, what do you see? And we'll come back to it in a bit. So my personal work goes on exploring the maximum limit of also utilizing digital fabrication and parametric design, using fractals as a mean to drive really interesting designs that are on the verge between man-made and natural. And I think that in order for us to think of the most basic solution, we need to push the limits on what can be done within our technology today. This is Shrine, a small exploration I've done after visiting a location called Al Bayda in Jordan that has temples carved into stone. And we'll see some pictures of that later on. This is a flow, which is a column as well. I was looking at how to utilize the sandstone structures and how can we create the structures in fractal, basically, biomimicry. And also looking at adding some elements to some of the designs that are human, as a human force is part of the environment, and it helped actually evolve a lot of the project we have done, and we'll look into that much more. And so when you look at the desert, you might see the amazing structures or the amazing patterns and morphologies you could find within rocks or sand. And you can start with that. So looking at the movement of sand dunes within wind, we've worked on creating the Rolaya train station facade, understanding how to utilize a language that is really unique to the desert and try to put it in a city that is actually in the middle of the desert. And the funny story is that the client asked us to do an image of the city of Riyadh. And once you go, you find really tall buildings and interesting structures. And when we went there, I said, well, this is just like any other city. We need to see what environment do you have. And then when we went to the desert and we started looking at the beautiful sand dunes and the environment, we realized what is unique about the location and the space. So this is how it looked when we started scripting the actual facade. And the interesting part is when you start doing something like this and you want to impress a client, you never think about how you're going to build it. And so you never anticipate that. It's like, if he likes it, he'll say, okay, now we need to build it. And then we started to understand more how to utilize digital fabrication and create or bring to life these inspiring structures. So what we did is actually slice the whole thing. So we have 5 panels going down. There's one going down. And every panel is 3,990 millimeters with a 5 millimeter gap between each panel and the other. And that's great. You can cast them within using GRC and GRG. But the problem is how you're going to put them on the building. And the client had this issue of he doesn't want anything to be he doesn't want anything to be welded. And the building was actually constructed, and we need to intervene and put the skin on. So we built also using computer tools that is not conventional, this really complicated structure. I think the steel factory went crazy when they saw that every sheet is held by a secondary steel, and there is tubes of steel coming on and flex anchors bolting the whole structure together, because the structure will be up on wind. So the whole structure moves with wind in one way or another. And so this is how it read the mockup on the computer, and this is the mockup on site. Today, the project is within this scope of finishing, so hopefully it's going to be done soon. But this brings us back to the question again, which is, how did people live in the desert for the longest time? And Jordan has with the north of Saudi Arabia and some places from Sinai, an old kingdom called the Nabatean kingdom, people that are ancestors to the Arabs that have built houses in stone in mountains. And you look at the structures that are marvelous and beautiful structures carved into stones that brings anyone to awe that sees them. And on the right, this is the Rose City of Petra in Jordan. And this is the place that we have gone to see actually what is desert architecture really about. Looking at how rich the material is, so mountains and sand, and is not arid land. There is a lot of places to look at. This brings us to the first project I'm going to talk about, second project I'm going to talk about, which is the Eco-Lodge of Al Bayda. And the site, as you see, is actually in the middle of the desert. And our task was to work with the community, with the actual local community, not experienced builders, to try and teach them how to build using the materials of the land. So we started to teach them how to do rammed earth structures. And as soon as you see the opportunity of you can build your own house with no cost and with as less labor as possible, people started to adopt this method in the area. And it is beautiful to build from the material of the actual site instead of bringing in materials that are alienated. And also, this brings us to think about what we could be using when we go on a mission to Mars. And another resource that is really interesting is the human resource. So we've talked about the mountain, we've talked about the sand, but also people that are living in these conditions for the longest time, and their ways of living is also quite interesting. And I think that one thing that people at the space program should look in is actually meeting the nomadic tribes wherever they are, whether it's in the desert or anywhere from the program we're doing. I think that they have the simplest answer that you couldn't think about. And we can take from that a lot in terms of solutions. And the stories you take on with building in the desert with the desert people is the most precious thing you can get from that land. So the next project, which is the last project that we're still working on. Sadly, I cannot share any renders. You can imagine it. It's really beautiful, and it's on top of a mountain. It's 40,000 square meters, but I can share about our scope more. So this is located in the city of Al Ula in Saudi Arabia. And the general notion is Saudi Arabia today is looking at the heritage of the nomadic tribes that lived there 3,000 years ago. And they're building a huge resort. And our scope was not the actual design, but it was quite interesting. So this is the site. So the client and the architect wanted our studio to actually start thinking about 5 new building materials that are unique to this project and taken from the land. And it was really interesting on the start because material innovation is a thing of its own, but they wanted someone to know the desert really well, to have started to think about these materials and what they could be. So this is our practice in Jordan. It's in Jebel Webde, which is an old area. And once we got the job, it transformed into this. And basically trying to create a makeshift lab in the quickest way possible to try and investigate some leads on what kind of materials you can come out with, the resources you have. And also looking at what are the resources. So we look at sand in a unified kind of way, but sand is different. There's types of it. There is colors, and there's also pockets of materials within the environment that needs to be explored. This is taking a really risky ride to draw boring holes inside of some of the locations in the desert and try to understand the layers on the site as well. And then we start doing the quite interesting. And so this is one of the materials we created in the office, which is a sandstone window. And it's quite interesting as you get to filter lights on the interior of the living spaces, but from outside, it's almost camouflaged. It can be viewed as part of the rock or part of the scene. And it is done on site using materials on site. And then we went into the most interesting one, which is we saw that the architects want to use a foaming concrete. And we thought we have all of the sand, so can we create foamed mud or foamed sand within a natural process? So we have successfully created 3 alternatives of this material using 3 different methods, which is chemical, mechanical, and biological. And when you go to each stage of this, you are lowering the carbon footprint. You are actually using material from the site itself, and you are involving the local community and the place. And the best part is when you test these materials, you can't say that it's a winner because it has a lower carbon footprint or because it's natural or it needs to perform. So we have successfully created a material that is as tough and rigid as concrete, using only materials from the site. And sometimes you do stuff just for the looks of it. And one of the things that we wanted to do is to create the same formations and the same looks of the erosion found on the rocks. And so we started to actually build the same processes and shapes that exist within the land using only mechanical and chemical processes. So what you see here is only sand binded together within the method we have invented as analog 3D printing to create the kind of shape and feel of the site itself. And then we start to play around with traditional materials such as concrete and how can it be integrated into the site itself. And also taking off material that is one side done with sand and the other side within stone or rock. It has 2 views, and all the materials I'm showing here are actually structurally sound and are being tested to be approved as an actual building material. So I invite you again to answer questions. And you look at this picture, what do you actually see? Do you see just an empty plot of land, a blank canvas, or a land filled of opportunities that can be explored? Thank you.
Great. Thank you so much, Mazen, for the exciting presentation. So now we'll go into our Q&A section and discussion on these projects. And I welcome everybody to submit their questions and thoughts either through the chat or the Q&A function. I'll start off with, one thought, and maybe you guys can elaborate on this, because the feeling of just being out there in the desert and spending a day or two, I feel, and not being in a normal office environment on its own kind of takes you out of this world, right? When I go to the desert, I was in Joshua Tree last weekend here in California, and there's this feeling that, you know, nothing else matters. You're just out there and you're in the middle of nature. It's quite different, and I think for architects and designers and engineers, you almost need that feeling as part of the design process. And I'm curious how that affected both of you.
I mean, it completely radically changes how you perceive the practice, but also the relationship with others. Like, I don't know if you've done like scouts or things like this, where you are in a purely like sort of relational, like basically everything becomes relationships. And it becomes about inspiring people, not being too negative. You can see that the main material of this project is just the sort of human emotion and how to manage a spirit, a general spirit. It's hard to explain, but it's really what it sort of reveals the essence of people when especially when you're struggling and people are like, what the hell am I doing here? And, you know, they took 1 month off from very, very busy lives to build something to make it even harder for themselves. And so it just kind of confronts you with, I mean, it's specifically because it was Burning Man. I think if it was a desert, like when we built in Saudi Arabia, we of course you have the city very nearby. I think the fact of giving yourself a challenge to be in extreme environment is a very different journey. That is, it takes you away. It takes you away in every way. So when you come back, you're just very changed. And I guess any big human adventure does that, I suppose. But
yeah, I think the same too. I think going there is really different from looking at pictures of anything, right? There is a notion that architects and designers need to gather this huge visual library and have an understanding of all of these environments, but experiencing the environment itself. Being in the desert, feeling the actual heat and looking at a sandstorm and like climbing the rocks is really different. It's an experience that changes a designer or an architect to a different level. And I think there is a connection, as Arthur said, there is a connection in all designers to a certain environment. So you can find yourself in any of these environments, and I think that you can build a lot of what you want to do or be around just a simple trip to the desert, as I have done actually. Like basically, the first time we went and looked at the desert as designer, I was a student in the visiting school at the AA, and today my practice is named after the desert. So yeah.
Right. So we have a couple of more technical questions. One is if you guys can share some of the software platforms that you use on the design of these stunning works of architecture. I think the attendees would appreciate that.
Easy, Grasshopper, and Karamba for the structure with the engineer, and a lot of the stuff we showed was the plugins, Kangaroo, Intralattice, Silkworm. It's just a big community of tools. So, and a bit of SolidWorks. Strangely enough, when it gets really complex, when you do scaffolding and stuff like that, you got to go into a software that can handle those, and Rhino can't quite. So yeah.
Yeah, same here. But we're using also coding in terms of C# and Python as well.
Okay, great. And I think a question for you, Mazen, is in regards to the binder used in the desert sand construction, if that is a thermoset polymer.
Okay, so this is tricky. So basically, the idea of using a chemical and then saying we're lowering the carbon footprint is really bad. So we've started using the thermost polymer, but we're looking at an alternative. There is a material in the desert called pozzolanas, and it is used as a binder in concrete as well. So you can use it with concrete, and there is a whole mountain of it. So we're really happy that we're using it as a binder for now. And also, when we had to use epoxy, we looked at the ecological epoxy alternatives, and you can find a lot on these with epoxies that are plant-based, basically.
Okay, great. I think we got a message that suggesting geopolymers as well as a binder, something to look at. So one question or thought I'll put out there. I think one of the things that I find in common between the two presentations is you're both doing kind of design build work, right? It's very digital technology based, and then we get in more into the construction side of this. And I think there's a lot of discussion in the architecture world in general, how much should architects get involved in fabrication? And I think what we see a lot of times is if you want to innovate in fabrication, the designers have to step in a little bit to push the boundaries and challenge the norms which the construction industry is used to. And then the other piece of this is autonomous construction. We're hearing a lot about that. And in a way, Arthur, what you were doing in the desert, you were using a lot of people and not necessarily particularly trained on that. So in a way, that's where we're heading with robots. We want to give simple tasks and kind of get to autonomous construction. So and that of course will tie into our Mars session, because we know on Mars, we're not going to send volunteers and construction workers to do that. It's got to be autonomous. So would like to hear both your thoughts, on autonomous construction and architects in the fabrication world. Arthur, if you want to start.
I think it's on the contrary, working with robots makes the construction even more human, because what happens is you have to test every single thing. We don't often see them in videos of robotic assembled stuff, but you have like a human trying to like figure it out and stuff. And so, we have a fabrication space here, and it's extremely it's actually connecting us even more with the making. And so it hasn't separated it, on the contrary, because you need the skills that an architect has to program these robots or program these complex things, you actually get even closer to the making of things. But what we realize is if we don't have the ancestral skills of connecting wood together or God knows, cement and how to make binders, then, our knowledge is just not enough. And so there will always be this dialogue with the sort of traditional craft and so on, no matter what the technology you're using. And you need to have that in order to also be respected by the builders and the contractors. And whether you become fully contractor as an architect is still a big one, because we, for example, only focus on the areas of a construction that really needs our set of skills. There's so much to a building. There's so much to figure out. Like I don't know that architects need to be involved in putting the power foundations or stuff like that.
I think having this knowledge is bringing back what architecture used to be, right? So basically, when you think about designers and architects before the Industrial Revolution, you think that people never designed something that they couldn't. They talked about building. So we think about the most marvelous construction projects that we have left, such as the Brunelleschi Dome. So Brunelleschi had methods that today is not known to us, right? He built lifts that we don't know yet what they did, right? And so basically taking that step back and understanding what is the origin of. You're also a problem solver. You're not just someone who draws shapes on a computer. You understand what you're doing really well, and you're more evaluated. Your value as a designer who understands the ins and outs of construction, and also within within digital fabrication is really important. And I think also it is quite interesting in our time to look at these things, as today all knowledge is available online, right? So you can just sit behind your computer and understand how to build the most complex shape using robotic hands on a website that gives you a tutorial. So there is no excuse not to learn or know these methods, as the whole world is moving towards that. And as we encounter more problems, I think digital fabrication is trying to solve these problems.
Yeah, that's a great point. We're moving a lot to the open source ideology and open learning and sharing tools and ideas like that. And I think one of the questions ties into this, asking about your fabrication base in London, Arthur. So I believe FabPub is open for anybody to come and visit.
Yeah, 100%. Hackney Road. If you go towards Cambridge Heath Road, come see us, and we can show you all our machines and so on. It's the idea was that it would be accessible for the public. So FabPub, as in public, also because we started it in a pub, but it was the sort of counterpart from our architecture studio, which of course architecture is still about self-expression and so on. So I thought it was a nice yin yang to allow other people to use the technology, not just us.
Great. So we have a couple more questions. One is talking about place-based practice and how is your work as architects shaped by working primarily from the desert? That I think place-based, it's the first time I've heard this term, but it's very interesting and something to think about. Do we as architects also start to specialize for certain environments? Usually, architects, we talk about certain building typologies or forms of building, but I think that does also apply. And I think one of our speakers later, Hugh Broughton, is focused on polar architecture in a way. So curious about your guys' thoughts as well on that.
I think that one was for you, Mazen. Place-based.
Okay, so basically, the thing I hated the most with starting my career is being stereotyped into working in certain environments or on certain projects, right? So I think we should have this personality of people that are problem solvers in terms of environment. I don't think that I should only be limited to the desert. I think I should have an input in other places, maybe as a consultant. And I think maybe Arthur would share the same opinion. I would like to try and work within different environments and within different problems that can be offered on different subjects. I don't think that you should be more looking into being specialized in problem solving. Then that's it. I think that because I live in a place that I have huge access to the desert. I can go on a weekend, it's just 3 hours drive and can be in Wadi Rum. So basically, maybe I know about the environment a bit more. But in terms of holistic thinking and in problem solving, as I go to the desert, I find solutions that other people don't. And I think if I go to any other environment, I can actually look up and find out solutions that are unique to that environment. And it is not about living in that place or reading about it or experience. It's about trying to find where people think that is scarce. You think it's filled with resources that have not been tested or viewed yet. And trying to find solutions within the resources that exist within a certain location. And yeah, it's easier to find solutions for the desert, but I can also buy a plane ticket and go somewhere and experience another place and try to apply. And as we talked at the visiting school with some of the students, it's really interesting that at NASA, they're looking at the first pioneers that went to the US and what are the amounts of resources they had to move and how did they move them. and Mars is totally different, but the approach of problem solving.
Oh, okay, sorry. I'm on that topic. I'm pretty torn because the desert is at the same time a complete blank canvas that, as I was mentioning, forces you to think about much more than just the form or the architecture, because you have to think about how you're going to build there. And so it forces you to think beyond the boxes of an architect. But at the same time, it's not at all empty. It has such a strong presence. On the contrary, because you're dehydrated, because you're just in a state of like you need things and you can't find it. It has an even added presence. So there's this real contradiction between the emptiness and the complete immersion.
Yeah, and I think that ties to one of the questions about space architecture relating to nomadic living, right? Because when we're building in the desert, you kind of, want to use local resources if you can. You can't reach a hardware store easily. You can't get the resources you would elsewhere. And you also, it's not so easy to bring a lot of material to the desert, which is the same dilemma we face on space. You don't want to take all the materials with you, want to try to use what's there. And that's where I think, the digital design and digital fabrication becomes particularly exciting to think about those ahead of time and to then use those processes for autonomous construction, for in situ resources, and all these kinds of thoughts. I invite Javier and others who are also experts in the desert world to chime in on the relationship to space, and I'm sure we'll get more into that as we get to the space session towards the end. There's a strong relation between desert and space, even though the environment, the temperature and atmosphere is very, very different, but on Earth it tends to be have some relationship. Okay, so maybe one last thought to discuss is going back to materials and local materials. So I think in your projects you've used different materials, and I can see, Arthur, that the timber is a great choice for Burning Man, given you have to burn the temple at the end, and at lightweight and sustainable. And I see Mazen with the local materials, and maybe we can talk a bit more about local materials, and also, Arthur, what you've experienced on the 3D printing with sand. How is it working with local materials and predictability and control and that process of it?
It's a good question, because it is very, very hard to innovate and to be petroleum free, and to use local materials that can be kind of fermented into bioplastics and so on, and meet the certification, the regulations, the fireproofing, and that paradox, because now we talk about biodegradability, but we also talk about durability, and there's such a paradox between those two aspects: things that can disappear, things that should last a long time. And so it's always been a bit of a kind of funny struggle to alternate between the two. But one thing that's really nice about, say, bioplastics like PLA is that you can activate the biodegradation. So you can compost it, if you have the right condition, but if you don't do anything, it'll stay as it is. And so one has to seek for these sort of middle ground between that, because obviously you don't want your building to disappear. I mean, obviously I don't want to burn buildings, and I don't think that's very sustainable. Saying this, one thing about Galaxia was that it was the same density as foam. It was so much tension in that structure that we could use such little amount of wood. And so if anything, I was kind of happy that we try and minimize whatever we ended up burning. So that's working with the essence, the lattices that are the least. So that's using, of course, a digital simulation like Caramba and stuff to just really try and see which direction your trusses should be and so on. So having that feedback in the digital world really is helpful.
Yeah, I can expand on the materials. For us, we're trying. It's not easy. Yes, it's definitely not easy. we were trying the most ridiculous things at the beginning, right? So one of the things we've tried, can share a recipe really quickly, is we've used mud with yeast and sugar, right, to actually create a foaming mud material, and then we fired that. And then you have this beautiful material that is structurally sound, that is fully organic, and then it starts to mold. And then you think, okay, people cannot live in a molding building, right? And then, okay, we can do something. Let's do an antifungal agent. And we put it and it kills the yeast. And I was like, oh, God, what should we do? And then you fire it and it works. And then you start to find solutions that are like yeast is a living organisms. And one of the things we have started to do is actually put some seeds in the mixture itself, and maybe water the actual building and have it grow. And some of the stuff we've trying to do is use, on the contrary, the most chemical process out there. And you try to look at both. I would say you should never be an alarmist when it comes to trying new things. You should always look at the extreme from both sides and try on a smaller scale, not to hurt the environment, of course. But at the end of the day, you could figure out a way to actually utilize both, right? So chemical at its core is also natural. It uses natural material and it is processed by a factory, but at the core of it, it's natural, right? But it has a larger carbon footprint. And you should start to think about what are the resources that exist in the area. Again, when I go to a new environment that I haven't built in, and when we started this project, I talked about 3 out of the 5 materials because we have done a lot of research work. For instance, the foamed mud took us 63 experiments to actually come up with 3 that are working. So 63 experiments, and that's only within components. We've done different ratios of each of the 63 experiments. The number is about 200 or something. So finding something like that is really difficult. And if it's not within the project scope, it's going to be more difficult. So our scope is to actually find this. While when you design or work for a client, you just go and you try to test really quickly, and then you go to the alternative that the client wants. But there is room to play, I think, within all environments.
And that's why it's so important to reinvent a little bit the practice, from how one can raise funds, the sort of entrepreneurial aspect. So we've raised funds for FabPub, and we now hire material scientists, and we look at regulations and how to go through the BBA and all that. Like basically the practice of tomorrow, if they were to innovate with new materials like this, they're going to have to completely change from just an architect designing and giving to a contractor to all these different things we mentioned, the material sciences, the legal aspects. Yeah,
pretty much.
Yeah, and I think it's really exciting to see the biomaterials and natural materials come into scale. And perhaps as architects, we don't work often enough with chemical engineers and material scientists to develop that. It's a lot more is happening, I think, on the construction side, and this is an opportunity for architects to push the boundary on these things and think about sustainability. But I also think sustainability is all encompassing, right? It's not only one part of the project, it's everything, how much material you're using, how efficient it is comparatively, and all of that. So this was a really great discussion. Thank you both for sharing your really exciting projects and work. I think everybody was super impressed and fascinated with all the work, and thank you for the enjoyable discussion.
Thank you very much.
Thank you. There are maybe a couple more questions still out there. Feel free to answer them through the chat or the Q&A. We can also do by typing, and people can continue to ask as they like. So we are going to now move to the next session.
Hi everyone. My name is Naima Critch, and it is my pleasure to welcome you together with my amazing co-hosts to this exciting event. It is great to see so many familiar faces in the audience, and it is particularly impressive that several panelists actually joined me here at the AA Gallery for today after traveling all the way from Copenhagen and Oslo to be with us in London. How appropriate that we had an extreme weather warning this morning across the UK, which truly goes to show one of the premises behind the theme of this conference, that rather than being the preserve of extreme explorers and adventurers and once-in-a-lifetime event, actually extreme weather and its consequences are becoming more and more common. I'm very happy that this event in a way shows the resilience of the AA and that despite everything, we continue almost as normal. I'm delighted to announce the next session. In the Oceanic session, we will discuss architecture of underwater environments. Our first speaker, Mike Genhardt, is NASA astronaut and submarine captain, and he will speak about the challenges of living and working underwater. His presentation will address the challenges and physiological stresses of commercial saturation diving and trace the evolution of alternative work systems to reduce dependency on complex saturation diving, expand depth ranges. Additionally, the presentation will address the use of the Aquarius underwater habitat to support NASA missions exploring partial gravity operations. After that, Heidi Peterson, senior interior architect from Snøhetta, will talk about their remarkable project which is located at the southernmost point of the Norwegian coastline, where the sea storms from the north and south meet. The project is situated at a unique confluence. Marine species flourish here in both briny and brackish waters to produce a natural abundance in biodiversity at the site. The Snøhetta designed restaurant also functions as a research center for marine life, providing a tribute to the wild fauna of the sea and to the rocky coastline on the Norway's southern tip. In Norwegian, Anda has the dual meaning of below and wonder. Half sunken in the sea, the building's monolithic form breaks the surface of the water to rest directly on the seabed 5 meters below. The structure is designed to fully integrate into its marine environment over time, and the roughness of the concrete shelf will function as an artificial reef, welcoming limpets and kelp to inhabit it. With the thick concrete walls lying against the craggy shoreline, the structure is built to withstand pressure and shock from the rugged sea conditions. Like a sunken periscope, the restaurant's massive window offers a view of the seabed as it changes throughout the seasons and varying weather conditions. Oceanic session will end with a presentation by Duncan Phillips from RWDI. He's a global practice leader for building performance. His talk will discuss their efforts to both diminish buildings' contribution to climate change through passive and low energy design, and to design for future climate scenarios by increasing buildings' resilience to extreme weather events. Duncan will be speaking about the pressure issues of submerging occupied spaces.
Well, good day, everyone. It's really a pleasure to be at this conference. I really love architecture. Architecture is cool. So I was asked to talk about the challenges of living and working in underwater environments. So I'm going to step through some of that and how robots sort of do certain things, and then circle back to talk about the NEMO missions that we do at NASA. And just in the way of historical introduction, saturation diving was ushered in by the U.S. Navy Sea Lab program back in the 60s. And for those of you that don't know what saturation diving is, when you're at depth, you have to inspire a breathing gas that's equal to the surrounding pressure, otherwise your lungs will collapse or expand. And then over time, the partial pressure of inert gas in your lungs comes to equilibrium with that in your tissues. And whether you stay down there another day or another year, your decompression time is going to be the same. and it's basically 1 day per 100 feet of depth of saturation. And it actually takes longer to come back from the continental shelf than it does from the moon. So they ushered in saturation diving, and then in parallel, as part of the story, offshore oil exploration production was gearing up. And the early generations of subsea equipment, which you see on the right, this is a blowout preventer, were coming out of this aerospace industry, and they were so-called diverless systems. They were triply redundant, had all this redundancy, weren't supposed to fail, et cetera. And it turned out they failed miserably. And that required the superior perception, judgment, and dexterity of the human diver. And that actually ushered in the era of commercial saturation diving. And on these blowout preventers, for example, you've got all these hydraulic hoses that can fail, the fittings can fail, and you can't, with this original design, you can't fit robots in there and all that stuff. So that ushered in saturation diving. And typically for commercial saturation diving, we're doing this at depths of 150 to 1,000 feet. And we have to breathe a helium-oxygen mixture for a number of reasons. One, nitrogen narcosis. Two, the nitrogen in the air would become so dense that you couldn't respire it. You'd have CO2 buildup and so forth. And at 1,000 feet, we actually breathe a mixture of less than 1% oxygen, which is a normoxic partial pressure, and the balance is helium. And then a 1% difference in the O2 concentration at that depth could be the difference between hypoxia and acute oxygen toxicity, where you go into convulsions. There's similar sensitivities with carbon dioxide and trace contaminant concentrations. The other big issue is that the increased heat capacity of helium at those depths, and because it's a diatomic molecule, is really a challenge. A 1 degree change in temperature or 1% relative humidity is the difference between comfort and discomfort, and 10 degrees or 10% can be life or death. And when you're locked out working in the water, you have to wear hot water suits and breathe heated gas to maintain thermal comfort and balance when working at those depths. So this is a typical saturation diving system, and unlike the scientific habitats that are on the seafloor, this actually resides on the deck of the vessel or oil platform. And this is a typical 6-person saturation diving system. The main living chamber here essentially has 6 bunks, and then there's a medical lock where they lock the food into you, so we don't have the galley and all that kind of stuff inside. And then to your left here is what's called the transfer lock, and that has the shower and toilet facilities, but you also transfer through that into a diving bell. And once you're in the diving bell, you make a seal on the hatch of the bell, and then it is overboarded into the ocean to the depth that you're working. And then you basically open the hatch, and then you actually open the exhaust valve and flood a little water into the bell, after you've donned your diving helmet, and then you lock out and work. And this is pretty dangerous stuff. And I always look at this in terms of the utility equation. And the utility or degree of success is basically the probability of success times the rewards minus the probability of failure times the cost. And if you acknowledge up front that this is a very dangerous business, then you spend a lot of time trying to minimize the probability of failure, because the cost is a human life, right? And so all sorts of efforts go into the design of the equipment, the procedures, the training, and so forth to really minimize that. And after some early failures, which included, for example, one famous case where a guy was using the toilet and they didn't have an interlock system, and somehow he had made a seal, and the pressure in the habitat in this particular case was 200 PSI, and so it pulled his intestines out. And fortunately, the guy lived, but little things like that you kind of learn the hard way, I guess. And but since really the last 30 years, there's been no fatalities in saturation diving. So they've learned to make it really safe. There's all sorts of different configurations. This is a ship that we had when I was at Oceanic, and it's a dynamic position vessel, so it can maintain station in 20-foot seas and gale force winds. There's a saturation system built in below decks. In this particular one, is like a 16-person saturation system. And then the bell, which you see up here, is actually deployed through a moon pool where the floor of the bottom of the vessel retracts, and then you deploy the bell so you don't have all of the problems with overboarding a bell with a crane or some kind of a lift system. So in addition to doing the oil field equipment wellhead servicing, we also do other complex jobs like hyperbaric welding. And this is a job that I was on. And to the right, you can see a mock-up of the damaged truss structure. So this would be on a offshore oil platform. And if there's damage on the platform, which a lot of them had early on because they didn't really know how to design them, in order to get a code quality weld, you have to weld in a dry environment. We do wet welding, but the weld is quenched so fast you get hydrogen embrittlement. And so we have to design these multi-piece habitats. This is roughly 14 feet tall, and we design them in pieces. Oops, sorry about that. And we actually go down and hang a ring around the leg of the platform with slotted bolt holes, and then you use crane and air tuggers to lower the individual pieces, and then you pull those together, and then you bolt in the seals. And very, very complex operation, but you now have a dry environment, and then you bring the welders in, and they put on their welding mask and breathing gear and do a code quality weld. So a lot of complexity there. So this next series kind of talks about the evolution of what I call work systems to reduce the dependency on complex and expensive saturation dive. Saturation dive is very expensive, and if you could get a robot to do what a human diver could do, that's going to save you a lot of money, and it lowers that cost, because if you lose a robot, that's not the same thing as losing a diver. And so the robots sort of evolve, even from the very beginning, late 60s. The one on the left is one that British Petroleum did called the Mobot, and it was deployed on guide wires. The one on the right, sorry about that. The one on the right is called the Trove. I actually made a lot of money rescuing those things. We got depth pay to go down and rescue the ROV. And typically these things were oversold by the salesman. They'd say, hey, it can do this, it can do that. And they got out there, couldn't do anything. The other evolution was atmospheric diving suits. And the one on the left is called the Oceanic gym suit. And so you can actually go down to 2,000 feet. The pressure inside is 1 atmosphere, so you don't have to decompress, but you then have to interface with the work site with end effectors, because you really can't make gloves work at that kind of delta pressure. So we spent a lot of time working on these end effectors. You can see the little hook here for pulling pins and interfacing and so forth. But the big thing is that you have to change the design of the subsea equipment to put all of those interfaces within the work envelope of the diver in the atmospheric diving suit. And that was a limitation. And so the next thing we came up, and this wasn't my idea, but called the Jet Gym. So it actually had a backpack on it, and you had to pull your hands inside to fly it. And you need to have a stopwatch to see how long that thing lasted, because you couldn't do anything. You couldn't fly and stabilize yourself. So kind of a bad idea. And then a British gentleman named Graham Hawkes came up with the WASP suit. Sorry about that, which still exists to this day. And it's basically a pod, and you fly it with your feet with sequenced foot pedals that become very intuitive. And that allows you to translate and then work with your hands as well. And you can use one arm to lock onto something to stabilize yourself and so forth. So the next evolution was the arms manipulator bell. And Oceanic developed the GE Oceanic force reflecting manipulator. This was a very sophisticated manipulator. I haven't seen anything that is this good even today. But you basically have a master arm inside the bell, and you can feel everything at the end effector. So you can actually, thread a shackle pin. And so, the arm was so capable. Actually, a friend of mine actually caught a fish with it. And I always say, if you want to catch a fish, buy a $75 fishing rod, not a not a $2 million force reflecting manipulator. And so over time, we evolved to simpler solutions. And what you see on the right here is really one of the first full work capability ROVs. It has a 6 degree of freedom and 5 degree of freedom manipulator. And we learned to redesign the task to make it serviceable by this kind of robust manipulator ROV system. And this manipulator is just a simple rate controlled manipulator. And instead of undoing a shackle pin, we had like a pelican clip that you would pull. This is at 3,500 feet in the Gulf. And if you don't recognize that, that's actually a sperm whale that was fouled underneath the tether of the ROV as it excurted from the cage to do these kinds of tasks. So I thought that was pretty cool. Okay, and then so this went further, and we ended up designing whole subsea production facilities. This was the Placid Green Canyon job, and we did what we call interface engineering. And so the whole subsea production facility was designed to be serviced with a robot. And one of the first things that you realize is that you need to have physical and visual accessibility. If you can't see it or touch it, you can't do the task. These blowout preventers were lowered with guideposts, and one of them was always taller than the other, and then they have these bell guides on them. And so you basically lower it down, and if you were a little off in yaw, once you stabbed that long guidepost, you could then rotate the others into place. And I actually stole that idea for installation of the high pressure gas tanks on the airlock, which were quite heavy, and it was considered the highest risk task in the assembly sequence. And each of the astronauts had different handholds on the high pressure gas tanks, so you had different moments of inertia, and you got all kinds of cross coupling. So we designed this little guidepost thing and made that a really easy task. You know, the other thing was there's all sorts of valves in this production facility that are very deep within inside. And so we routed those outside, and we have docking interfaces for the robot to come in and turn the valves and so forth. And this is all for the non-time critical stuff. Time critical stuff, you still need sort of automated systems to kick in, but anything that was not time critical, we could do by the robot. And so over time, all the subsea equipment evolved. We had different tools for the ROVs. And then when I started Oceanic Space Systems years ago, we took this standard interface where we basically had every task that you would do on these on the subsea equipment in this thing that we called the bucket. And so the ROV's job with this undermounted skid, which was configured with different work packages, was just to dock to this standard interface. And we had different torques of valves, we had hydraulic connections, electrical connections. And so that evolved to become the micro conical interface, which is now all over space station. And it's both robot and EVA compatible, so that we have the end effector on the robot that can go in and release these ORUs. We also have a handhold that attaches to that for astronauts to use. Okay, so back to underwater habitats as I try to stay on time here. So underwater habitats started in the 60s and 70s, and they actually, unlike saturation, commercial saturation, they're on the sea floor. And in the early 60s and 70s, there were many different habitats, and the fact is there's only two that remain today. One is the Aquarius habitat, and the other is the Jules Verne Undersea Lodge, which is in a canal in Key Largo, and it's kind of a tourist attraction. So this is the Aquarius habitat on Conch Reef off Key Largo. It's a 6-person habitat. There's a main lock that you see to the right. There's a sleeping quarters for 6 people. Then there's an entry lock, and then a so-called wet porch where you actually get into the water. You can see that on the lower left here. So you actually get into the water and then don your gear. There's a nice big galley table, and usually you have interesting visitors looking at you through the window. There's another view of the inside. Florida Institute International University now operates the habitat. There's the sleeping quarters, which they could have done with what I have on my rover now, which is private sleep curtains that suppress sound and light. I did one of these missions, and I won't mention the astronaut's name, but he snored really bad, so it was hard to sleep. So anyway, we use that habitat, and we're saturated at 50 feet, so we have tons of bottom time. And this is NEMO 14, where we actually weighed everything out at 1/6 gravity, and we looked at how we would offload this rover I was designing from the, oops, what happened there? Sorry about that. Oh, come on. Computer's acting up. Yeah. Okay, can you see that?
Yeah, no worries.
Okay. And yeah, so we also did center of gravity studies because center of gravity is very important. So we designed this center of gravity rig, and we looked at all different CGs to start with, and did all kinds of tasks from shoveling to picking up rocks to doing a face plant to see if you could get up. And we repeated those tests later in the MBL with force plates and time series motion data capture. We looked at various ladder angles as a function of CG, and then offloading the rover. We also did incapacitated crew member, where we had a mannequin weighed out appropriately and looked at bringing them in through the suit ports on the rover or through the side hatch. And then NEMO 16 was another cool one we did. That's back in the day where we were supposed to be exploring near-Earth asteroids. And so we did lots of work on this. We actually developed a whole circuit of different tasks that you would do on an asteroid, from deploying translation lines, collecting float samples, which is just a rock that's laying there, a rock chip sample, soil sample, all these things. We laid them out, and we investigated them with different means of restraint, from translation lines, which weren't very stable, to a boom that you would work off of. We looked at jetpacks, which not a great idea for this. And then we actually got the deep worker submersibles as a stand-in for the thing I was designing at the time called the multi-mission space exploration vehicle, which was basically the rover I'm working on with a jet sled underneath it, and the crew could excurse. And so we used this deep worker as a simulation of that. We had a foot restraint on it, and we did all these different tasks, and it was by far the best way to go. Here's just, we deployed large instruments and all kinds of stuff. Here's a quick video of that. And if you watch closely, actually when the diver is grabbing the soil sample, you can see the deep worker slightly displacing from the bottom, which is fairly realistic. So that was a real cool mission, and really, deals with task design, humans, machines, how you work all that together in a very challenging, harsh, hostile environment. Actually, near-Earth asteroids are like the worst of all, because you've got microgravity and dirt. On the moon, you've got some gravity. In space, you have microgravity. So with space station, we've designed that for translation and all the work tasks. And on EMEA, you have none of that. So that's probably the most challenging environment. And then this is my get off the stage slide. And let me think about how I want to introduce this. So I've always been just fascinated with the Terminator. And if you don't know what that is, if you look at a half moon, the Terminator is the line between day and night on a moon or a planet, and on Earth you don't necessarily see it. In space, we go from day to night, night to day, every 45 minutes. And on my first mission, I was doing an EVA, and one of the tasks that I did was to get up high on the robot arm with all the lights out to see if these new glove heaters would keep my hands warm, because we'd had people get frostbite in space flights. And it was really cool. And so like at night, all the lights were out. You could see Jupiter and its 4 moons with your naked eye, and the Milky Way like 1,000 times brighter than in the middle of the sea on a sailboat. Anyhow, so because of my love of the Terminator, when we started the NEMO missions, we always did what we call a dawn dive, where you would go out of the habitat at like 4:30 in the morning, and you'd see all the nocturnal life out. And then, we'd stay out there for 6 hours, and you'd watch the reef transform from, in the early morning, the night fish and eels and stuff are out, but the day fish are waking up and the sun starts rising, and with internal reflection, you can see your image on the surface, 50 feet away and stuff. So it's really cool. Okay, that's me done with the 30 seconds over. All right. Are we going to do questions now or later? How do you want to do that?
Thanks so much, Michael. We're going to do questions towards the end. So 2 more presentations.
Okay, great.
So Norma, go for it.
Heidi Petterswald, who has worked as an interior designer for more than 20 years. She graduated in 1993 after spending her last semester at the Middlesex University in London as an exchange student. After finishing her master study in interior, she started to work for the interior agency in Oslo. After 8 years practice there, she has worked on various projects for Snøhetta, such as the Reindeer Pavilion at Kirken Dovre, the Regionals Department for Henneman Duty Free at Gardermoen Airport, several restaurant locations for Bolgen Moi in Oslo, as well as Bar in Copenhagen and the National Academy of the Arts in Oslo. In recent years, key projects include Kula Torg, a mixed-use future-built pilot project aiming at 000, and the renowned underwater restaurant Under in southern Norway. So Heidi is actually here in London.
All black. And this is the end of the representation. It's slide 25.
Yeah.
Couple of technical problems. Okay, go to the very beginning. Can you hear me?
We can. We are seeing it in a vertical format, though, which is odd. I think part of the screen is cropped.
Can you see the screen now with the?
No, it's just like this.
Oh,
I feel we're only seeing half of it.
you're only seeing half of it. All right.
Maybe stop sharing and share again. That's
Yeah. You need to go out of it, I think. And show.
Try to share the screen now.
Share again.
Okay, we see your PowerPoint video with the notes. So if you go to full screen view.
Everyone is trying to help out. Let's see.
Yeah, I think so. No, it's not.
No?
Is it the same again?
Yeah, we're still only seeing half of it.
Maybe you could, if you unshare again, and then when it comes time to present, you could try slideshow from beginning, and that might do the trick.
It was the slide, so we're trying. Okay, try again.
There we go, that's perfect.
Perfect. Yeah, looks good.
Right, okay. But do I have, I'll take all that away so I can see my notes. To the side. Okay. I need to take it away so that I can read the notes.
Okay.
Can you take it away? Yeah. All right, let's try and go for it. Okay, I'm Heidi, and I'm very happy to join this exciting event with you all. I work as an interior architect in the Oslo-based Snøhetta office. This is also Snøhetta, the mountain most people think of when they hear the name Snøhetta, at least in Norway. There is no coincidence that we start our talks with a picture of this 2,286 meter high mountain in Norway. Our desire to promote nature experiences and the connection to nature are always important in our projects. Right, there's more. This. Today, Snøhetta has grown to become an international practice of architecture, landscape architecture, interior architecture, product and graphic design, with more than 280 employees from 32 different nations. Snøhetta has a long tradition of doing projects in large parts of the world. We're actually celebrating 33 years this year. Snøhetta has an ambition to work across disciplines, nationalities, culture, and national borders. Our practice has a global presence with offices spanning from Oslo, Paris, and Innsbruck to New York, Hong Kong, Adelaide, and San Francisco. The desire to explore nature are also very present in the project I'm here to introduce to you today, known as the Under Project. Did any of you notice this front cover of Time magazine when it came out in September 2019? Can you spot the Snøhetta project? Yes. This is our Under project, portrayed as an icon on the front cover. And we felt very honored when Under was on this list of the world's 100 greatest places to visit. So where in the world are this project? The locations are almost as far south as you can get in Norway. The idea for the project came via the two brothers and local heroes, Gaute and Stig Ubostad. A dear friend of them put them on the crazy idea of adding an underwater restaurant to their two already established hotels in this area. This map shows where the two hotels are located, and our Under project is marked here with a red dot. The two brothers came to Snøhetta to fulfill their dream of building Europe's first underwater restaurant. Visitors to this remote southern part of Norway could be a great support to make their two hotels healthy and to secure the everyday life for both them and their extended family, both now and for the coming generations. It was with great respect we started the task. Rarely have we started a project where experience from any previous projects was not particularly relevant. How many of us have actually built underwater before? Luckily, we had a great expertise on our team. Local companies had extensive experience from the offshore industry and from tunnel building. This is Europe's first underwater restaurant, Under. Under is a story of contrasts, where gastronomy, marine biology, and architecture are co-dependent. This is a complex project that has been created through a close collaboration between numerous different disciplines. This lighthouse is a weather station at Lindesnes, situated at the very southern tip of Norway. It was one of the very first lighthouses to be established in Norway in 1863. And since then, the lighthouse have informed about the weather conditions 4 times a day, and it's still going. Lindesnes Lighthouse has a very vulnerable location. When the storm occurs, the wave height can be up to 25 meters with hurricane strength. And the Under project is located only a 15-minute car ride away from this lighthouse, but it's still positioned relatively open to the sea. So we had to shape the building so that it could withstand these extreme forces of nature as wind, wave, and water pressure. This is an illustration which shows Under from a fishing and diving perspective, a slightly unusual angle, but then Under is a very unusual project. Under has a double meaning. Under can mean wonder, and under also means under something. So wonder or miracle is a term for an event that cannot be explained by either human experience, reason, or nature's known laws. It can trigger wonder, amazement, awe, and joy. In Snøhetta, we often start our projects with a concept development, where the goal is clarity and simplicity. In terms of under, the fastest and easiest way from above to under is a straight line. In this case, the answer became a tube. The tube is made up of watertight concrete, and inside this tube, we fitted a wooden log. Under is about the movement between above, the water level, and under. At +3 meters, you find the foyer and the entrance. At -1 meter, you find the mezzanine where there is a bar. And at -5 meters, you find the restaurant at the seabed. Oops. Oh, shit. Now it's moving. Sorry.
Do you want to go back?
It's going on its own. This is what I wanted to show you. We created a kind of water binoculars. You might remember them from when you were little. What is going on? This was not. Under is also a story of contrasts. The outside and inside are contrast, but still two sides of the same form or shape. The inside is mirroring the outside, as a tailor-made suit has a lining that follows and emphasizes the front of the suit's design. This illustration shows the 4 bearing elements of under. A simple 3D model shows how we filled the concrete tube with a wooden log, and further how we carved the wood to create the various spacious volumes we needed. This is a drawing showing how the building sits on the plot, above and below water. Safety, escape route, orientation is very important in such a building where most of the volume is underwater. Some guests are concerned about whether they will feel uncomfortable staying underwater. Using a simple and easy to understand concept and intuitive design language makes it easy for the visitor to understand the building and to feel safe. As a visitor, you enter the building upstairs, and soon after you can look down through the sloping volume, which brings you down to the seabed via one long continuous staircase. If you look back up where you came from, when you have reached the bottom of the building, you see where you came from. You can see where the daylight gets through the facade in the entrance area, and you immediately read how to leave the building again. Midway on the journey down to the seabed, there is a stop on a mezzanine level located -1 meter below the sea surface. Here you find a narrow but tall window, and through this window you can experience what is over and under the waterline at the same time. Some days the waterline are high up on this window, and other times it's low, depending on the sea tide. Under was constructed on a barge by the nearby hotel's deep water dock, located a 500-meter walk along the coastline from the site, but only 300 meters across the sea. Formwork of wooden planks, a sliding formwork, was used to shape the concrete surface of the building. At the end of the summer 2019, Under was detached from its barge and slowly and carefully moved over to her plot, supported by a 78-meter-long crane arm on the boat. This was a nerve-wracking day. I'll show you a short time-lapse. This is what Under looked like on the opening day, early in the morning. In this soft morning light, the hard concrete facade looks almost mild and soft. As soon as you have entered Under via a bridge, you can continue straight ahead to the very front, where the solid oak meets the rough concrete. The interior or under is a celebration of local craftsmanship and the use of Norwegian oak wood. At the entrance foyer, you get the first taste of what you are about to experience. Here you are surrounded by solid oak floor, solid oak wood as both flooring, wall cladding, and ceiling. Solid oak is used as the only wood material throughout the whole project. Hamran, a local traditional wood carpenter, have supplied all of the wood materials for this entire building. Because of the fire rating for this project, it was difficult to be able to use burnable materials, such as wood. And we needed to understand this further and ended up in deep discussions with the fire consultants. Solid oak thicker than 19 millimeters does not set fire very easily. So we were able to use solid wood after all. This picture shows the top of the stairs, where you as a guest leave the daylight behind and start your journey down under. Moving down towards the mezzanine, you get a glimpse of the large window at the bottom, and the narrow and vertical window to the right of the mezzanine starts to show. Through the vertical window on the mezzanine, you can experience the landscape outside, above, and yet under the water surface at the same time. And experiencing above and below the sea level at the same time makes you far more aware of the journey from above to under. From the mezzanine, you can look back up again towards the entrance, and further down, you get to see a larger glimpse of the restaurant room. When you're back to the large window, you can overlook the open kitchen of the restaurant. You can also study how the daylight seeps in through the tall vertical window up on the mezzanine. Some daylight gets in on the mezzanine above the water surface, and surprisingly, quite a lot of daylight also gets in to the kitchen and the serving buffet via the sea water. Daylight through the vertical window behaves almost like a sundial on the textile cladded ceiling and walls. Early in the project, we all agreed that a building like this needs very good acoustic conditions. It's a fine dining situation, but most importantly, it is underwater. So we did not want any echo or submarine-like sounds. To secure these tasks, we decided to overcompensate with an extensive use of acoustic panels. We tested many different types of acoustic materials, and the strict fire requirements challenged us once again. For the acoustic ceilings panels, we had to choose a flame-retardant synthetic textile with a pattern and a color palette that did not appeal to us. We therefore decided to design our own under textile. The textile on the right is a typical traditional Norwegian craft weaving from the region of Norway where under is located. It's a weaving my mother made for me some years back, and we brought this piece of handicraft with us to the textile developer and manufacturer Kvadrat in Denmark, where we managed to present our under project. It didn't take long to convince them to collaborate about this new textile we had in mind. I would like to show you a short movie explaining this textile development.
We wanted to create a feeling of moving deeper into the sea visually with colors. In an underwater restaurant, the acoustics are especially important.
We really wanted to use textile as a main material for the walls and ceiling. When we decided to go for textile, we thought of the beautiful and flexible design of the soft cells from Kvadrat.
Kvadrat makes acoustic panels with a lot of possibilities for us architects. And on this unique project, we collaborated with them to design the textile from scratch.
We wanted to create a gradient color in the length of the building, meaning 24 meters, going from deep turquoise, blue and green of the bottom of the seat, via dark brown and orange in the middle, to the light pink and yellow of the daylight. Naturally, a textile like this was not on the market.
We also needed to use a special weaving technique because the textile had to be partly open, so that the acoustic performance requirements from the acousticians were fulfilled. Working directly with the weavers in Holland has been a whole new experience for us and a lot of fun. We were concerned if the 370 light fixtures that were integrated in the panel would cause any issues, both with regards to the tension on the textile, but also the access to the wiring behind the panels.
Following the process of mounting the panels was moved. We had left only 2 centimeters margin on each side, so we had to fit perfectly.
But there were no issues at all. It really works well with the lights incorporated in the panels. It calibrated very seamlessly from the bottom of the restaurant all the way up to the entrance.
But the vast window at the seabed are the magnet of this project. 11 meters wide and 3.8 meters tall. Artificial lighting should not compete or destroy the magic that happens when natural daylight makes its way down to this restaurant. Not to mirror the luminaires in the large window has been a guiding parameter. No elements of the inside should be reflected in the large window and destroy the view out under water. Daylight down through the 5 meters of sea and into the restaurant room. This is where the term under or wonder or miracle really makes sense. It is simply impossible for me to find the right words to describe this. Standing there by the large window, looking up towards the sea surface, where the sunlight strikes and penetrates through 5 meters of sea, is truly magical. If the wind makes waves or the rain hammer the water surface appears as a chandelier, where the prism changes according to the weather conditions. So what do we see outside the big window? We call the whole thing a peep hole into this coastal system, says the marine biologist who is connected to UNDER. The biological diversity in cold sea is little known. We believe that if more people get knowledge about marine life, they will become more aware of the important life in sea, he says. The restaurant is important for his research. Instead of giving written explanations of sea life in the restaurant, he trains the waiters to inform the guests about what they see outside the big window. He continues, usually when you dive, there's a time limit to how long you can stay underwater. And you also have to stay in motion and swim from place to place. And you only get to study the different conditions for a shorter period. Looking through this massive window, you get to study underwater life for as long as you like. This gives us greater opportunities to discover new species, to study their behavior and stages of underwater life that have never been seen before. The researchers have already discovered species of jellyfish that they didn't know existed in this area, only by looking through this restaurant window. I received this little movie clip from the construction site in mid-January. Okay, that one didn't work. Okay,
that's true. 2 of them, right behind each other.
You can hear the sound, but you can't see anything. I'll move forward. The colors in the North Sea are not as bland and gray as you might think. The UNDER restaurant's culinary philosophy are closely connected to the building itself. The chef, Nikolai Ellingsgaard, has an ambition to show the wide variety of different commodities in the southern part of Norway, where we do not have a lot of one ingredients, but a small amount with a broad variety. To dine at UNDER is almost like a hike around the nature of Lindesnes. The ingredients are locally harvested and adapted to the changing seasons of the local flora and fauna. It's mainly fish, seafood, seaweed, herbs, and wild game that are harvested nearby. To reduce waste or leftovers from the catch, the chefs at Underwater have an ambition to utilize the whole animal from nose to tail. Ellingsgaard and his team are constantly in dialogue with the marine biologists to understand and learn how and when it is best to harvest from the ocean in the most sustainable way. In the future, the goal is to have ingredients on the menu that are harvested directly off the building. For the moment, they are monitoring how the kelp and seaweed grow on the building, and I have just started to harvest small sea animals. And the building you see here, I received a couple of days ago, and it shows how seaweed are actually now growing on the building. So I would like to close this short lecture with a couple more fresh underwater photos of this project. And these photos are almost unreal. But I can assure you this building exists under a project where marine biology, gastronomy, and architecture work together. Thanks for your attention.
Thank you so much for that fascinating presentation, Heidi. So our next speaker is Duncan Phillips. He's RWDI's Global Practice Leader for Building Performance, heading up a talented pool of building performance engineers and scientists as they develop climate-responsive design strategies for individual buildings and master plans. RWDI's clients benefit from Duncan's ability to solve tough building physics problems by analyzing airflow and heat transfer phenomena. These capabilities have applications in ventilation strategies as well as renewable energy. Duncan is a critical player in RWDI's efforts to both diminish buildings' contribution to climate change through passive and low energy design, and to design for future climate scenarios by increasing buildings' resilience to extreme weather events.
Thanks, Nirma. I take it you can hear me. Hi, everybody. Welcome to Mission Control at my end. It's interesting. I don't think Heidi knows this, but I've worked with Snøhetta a few times. I've actually been to your New York and your Oslo office. I didn't realize you had so many. I've got some other travels to take care of. So what I'm going to talk about today is managing hydrostatic pressures in connected environments. Just checking, you guys can hear and see me okay?
We see your slides with the notes, not the full screen.
See the slide? Oh, that's interesting. I'm not even sharing that yet. Give me a sec.
So if you go to full screen, I think that'll do it.
That working?
Perfect. Yep.
Yeah, I'm sorry. In that case, I hadn't got there yet. That's the reason for that. What I'm going to talk about is managing hydrostatic pressures in connected environments. And just so we're not distracted, I'll turn that handsome guy off there. And I'll explain what I mean by that as part of this. So first off, a little outline. Forgive me, I'm an engineer, so I need a thought process. So I'm going to talk about what is a connected environment, and then I'm going to talk about what a self-contained environment is, and then I'm going to talk about hydrostatic pressures, and you'll sort of see where I'm going in terms of what the issues are about submerging something into water, because that's ultimately what we're talking about. And then I'm going to sort of talk about how that relates to buildings on land and what that means for the design and construction of buildings on land, now that you've sort of seen what happens when we go to water. So what do I mean by connected environments? It's really sort of a building that immerses itself in the water, that is open at the top. And so there's been a variety of examples of these. You can sort of go to different places. I've provided the reference for some of these at the bottom. This is the ocean spiral, sort of an idea of a 500-meter diameter disc at the surface of the water. It's open. And then there's this sort of swirling platform that goes down to the ocean floor, and it's roughly 4.5 kilometers deep. And so the idea is, of course, you've got these spaces where people are connected to the air. They can see the sky, but they also get the benefit of seeing the waterscape. Here's another one. This was a floating city. And in this particular case, the idea of that chimney in the center is to deliver daylight and natural ventilation. And then as you go further down, there's access and connections for submarines and things like that. So this is another example of a connected environment. And then Heidi's just spent 20 minutes talking about this fabulous project. But this too is another connected environment. And in this particular case, we're 5.5 meters below sea level at the lowest part. And so these are all kind of cool spaces, but so what's the challenge is a reasonable question to ask. And so the challenge comes from this. What we're doing is we're immersing something, and it's almost like if you put a cup into a bucket of water. So that's really what we're doing. We're taking something and we're sticking it into a large body of water. And the issue is that cup that we're putting into the bucket, or the building we're partially submerging into water, has a completely different density in that the air is 1.2 kilograms per meter cubed, and the density of water is 998 kilograms per meter cubed. And these are sort of rough numbers at sea level, and they'll change a little bit as we go down, but for the purposes of our calculations, this works. So we've got almost a sort of, call it 800, 900 times difference in the density of water and air. What that ends up meaning is that when you go down to the bottom, and in this case, I've defined the bottom to be 100 meters, the difference in the pressures at the bottom, if you go down to the bottom inside the building, you're only exposed to roughly an additional 1100 pascals of air. Whereas if you go down to the bottom 100 meters down in the water, you're exposed to almost 1,000,000 pascals of extra pressure, where I've defined zero pressure being sort of basically at the top of the building or the top of the water level. So we've got almost 1,000,000 pascals difference, or 966 atmospheres, or 142 PSF, or 3,900 inches of water, depending upon how you want to, what kind of pressure units you want to use. So I've got an enormous pressure difference between the two. And what that then means is if I stick my building into the water, that pressure at the bottom of the water acting on the container will be very high. So we then sort of think, well, okay, well, we put submarines into the water. Those go a lot deeper. Yeah, they go an awful lot deeper. And we've put astronauts into space, and they're outside, theoretically in space, the pressure is almost zero. It's not exactly zero, but it's almost zero. So what's the big deal? And you can do the calculations, and the calculation I've done here is effectively for a submarine. I've made some assumptions about the diameter of the submarine. It's about 10 meters in diameter. I've just made my submarine out of mild steel. I can calculate this thing called the hoop stress. And the best way I can describe hoop stress is if you take the belt on your trousers or pants, depending upon where you are, and you tighten your belt, the force in the belt is what the hoop stress is. That's the force that the belt actually has to use to sort of squeeze in if you're pulling your belt too tight. That's what hoop stress is. And so if you do these calculations, and I've dropped a cylinder into 100 meters of water, and of course, remember the outside, I've got nearly 1,000,000 pascals, but remember inside, I've got a little less. The thickness of my steel only needs to be about 1.8 centimeters thick. It doesn't actually have to be that thick in order to deal with those stresses. So in the end, we can build submarines that go very, very deep, and we do. Another way of looking at this is to look at the space station. And in the case of the space station, of course, the atmosphere in the space station is pushing outwards onto effectively zero pressure. And so in that particular case, if you make your space station out of aluminum, you wouldn't make it out of steel, but you make it out of aluminum, it roughly, just to deal with the pressure, just slightly less than 1 millimeter thick. It's actually not that difficult to deal with that pressure in terms of controlling it. Now, I will say that the space station walls are a lot thicker than that because they've got to deal with missiles or debris. They've got to deal with hard points where they've connected things. So all of a sudden you have local stresses. So it's a lot thicker. But if you just had a perfect cylinder, you'd want it about 1 millimeter thick. So what? Well, so the so what goes like this, and that is that we can design a pressure vessel that will take these pressures fairly easily, but we're not talking about a pressure vessel. We're actually talking about submerging something in the water that's open at the bottom and open at the top. And as Michael sort of showed earlier on, it's quite possible to sort of submerge a living quarter down to the bottom of the ocean. And as Cecil said, he sort of showed you can go quite deep. In this particular case, I'm still working with my 100 meters. And what ends up happening is that if I have my living quarters here open at the bottom, that's actually fine. That will actually work. The pressure inside will be approximately the pressure of the water at the bottom here. So let me just I got a pen. So the pressure inside here will be roughly the same as the water pressure here. If you're, and that's that number there, nearly 1 million pascals. If you're really going to be rigorously attentive to the details here, what you end up having to do to calculate the pressure where this person is, you actually have to take this sort of 979,000 pascals and actually subtract the pressure as you come up in air, but it's small compared to the whole thing. But that would be if you really want to be mathematically rigorous. But in the end, this works. However, this is not, of course, a place where us mere mortals would want to be. The pressure is a little high, and Michael sort of went through that a little while ago. But what happens if there's a hole? And so if I stick a hole in here, all of a sudden, I think you sort of know intuitively what's going to happen. We start to fill up. And the rate at which you fill up can be calculated, and I'll do that in a little bit. But what will end up happening is the vessel will fill to a level approximately just above the opening of the hole. And I say approximately just above. It depends upon some background sort of assumptions and what the pressure was in the air when we started. But let's sort of assume for a moment it sort of ends up about there. So that's clearly a bad idea. So now let's go to our immersed building. And if the immersed building is totally sealed and I've got my people and they're in here and they're all happy and stuff, that's great. If I have a hole though, and the hole is open at the bottom, so long as I'm sealed at the top, we're all good. So in this particular case, so long as that seal is there, I might be able to be okay. However, because there's a pressure difference, what ends up actually happening is that because the sea is pushing down, or the water is pushing down, it actually creates a pressure here that the only way that this vessel does not fill up is if the inside pressure at this point in the air is the same as the outside pressure here. If this pressure is different, what will end up happening is water will come in. So that means that the pressure difference between the inside and the outside at the bottom where I've got this opening is 0. And so if I then go back up, what ends up actually happening is as I go up inside this this column of air, what ends up actually happening is because the density of air is so much lower than the density of water, what ends up happening is that the pressure as I go up inside, it actually drops a lot slower than the pressure outside. So another way of saying it is, as you go up here, because you're dealing with water at 998 kilograms per meter cube, you end up getting up to a 0 pressure up here roughly, whereas inside, because the pressure here is the same as it is in the water, but I'm dealing with air and I'm only going up at 1.2 kilograms per meter cube, it means that I've got an enormous pressure pushing outwards from inside this structure. So this actually starts to be sort of part of the issue we need to deal with. So now we go back to this partially submerged building, and there's a hole, but we also have a hole at the top. Well, I think you now know what's going to happen is all of a sudden water is going to rush into the bottom, air is going to rush out at the top, and this thing is going to slowly start to fill. And so we have a little bit of a challenge. So the so what now is about leaks, and we can calculate the rate with which water will flow into the crack. Or flow into that little hole that I created. And it's approximated by something called the orifice equation. If you go to Wikipedia or somewhere like that, the orifice equation is described in long detail, but I've sort of boiled it down to the bits that we're really interested in. But that's what it looks like. It's basically a relationship on the square root of delta P, the pressure difference. And so if we do that calculation for a 1 inch by 1 inch hole. So it's a sort of a 2.75 centimeter by 2.75 centimeter hole at 100 meters down. And sort of you see the math here. This here is my 989,000 pascals. I thought it was 038, I think it was. That's that number there. That's how you calculate that. If I do this maths, what ends up happening is I get an answer of about 960 liters per second coming in through that little hole. That's what ends up happening. That's if I'm in the water 100 meters down. If I go to the space station and I've got the same sized hole, and I will acknowledge that having a hole in the space station is a bad thing, the flow rate that we have of air through that hole is something like this number. And the reason why the airflow here is so much greater than the water flow here is because the density of air is a lot less, even though my pressure difference is a lot smaller. So the rate with which we lose air out of that small hole, well, I guess it's not really a small hole, but that hole that I've defined in the space station is a lot greater. So we clearly need to be worried about that. That's an enormous quantity of air. So now let's go and sort of think about this waterscaper. Here's another example of those buildings. So a lot of these concept buildings have connections at the bottom for submarines and sort of access for people to go for a swim and things like that. And they also have openings planned at the top of them. So we end up running that risk where if there's a leak at the bottom, we end up having a bit of a challenge in that water can start to come in, and we would need to start pumping out that water very, very quickly. And bear in mind that pumping the water out would actually be very difficult, because we'd either have to push it back out the wall locally or pump it all the way up to the top of the vessel and then dump it over the edge. So we still actually have a bit of a pumping problem. So leaks in these kinds of structures happen when there's a change in materials, like that glass wall. So the team that was working with Snøhetta would have to have been very careful with that glass wall. Clearly they have been. When you have something that's operable, like an operable door. So if I've got submarines picking up and connecting to these buildings here, we'd have to be very careful about that. Changing components, things like that. So all of these are places where we can have small leaks. And the leak doesn't have to be very big. So I defined that earlier hole in my building as an inch by an inch, but it doesn't have to be that big. So now let's flick to land, because this is sort of, we've sort of spent some time talking about water, took you into space for a moment, but let's now talk a little bit about land. And what ends up happening in land is that we have a similar sort of problem. We take a hot building in winter and we immerse it in a cold outside environment. That's basically setting up the same pressure regime as me taking a building and partially submerging it in the water. It's exactly the same physics. If I take that hot building and submerge it in cold outside air, the hot building has a lower density than the cold outside air. So I set up the same sort of thing. So if you look at the image on the right here, what's ending up happening is that I've got, for any particular building in any location, I may have a pressure regime set up where air wants to come in at the bottom and leave at the top. This is for cold conditions, but I also have the case of something called reverse stack effect, where if I take a cold building and immerse it in hot air, the opposite happens. Air wants to come in at the top and leave at the bottom. So if we now start thinking about some of these tall buildings, there are currently 4 buildings that are over 600 meters tall. The one in Dubai, of course, Burj Khalifa is somewhere around 828. The one in Kuala Lumpur is pushing over 600. Shanghai is somewhere around 630, and the clock tower in Mecca is 601. There are lots of super tall buildings. The super tall building is defined as 300 meters tall, but sort of for the purpose of our thinking, let's start thinking about those very, very tall buildings. And often there is that temperature difference indoors to outdoors, which is that density difference I've talked about. So what I've tried to do here is give you some numbers. And so the way this table works is I've just taken the design temperatures that we have for the conditions we're concerned about. So in Dubai, we're worried about the hot temperatures. So that's a design condition. It's not the hottest it ever gets. That's just a design condition. For those of you in London, this is the design condition in London, minus 2.8 degrees Celsius. Edmonton is interesting. Edmonton, Alberta is minus 35 degrees Celsius. That's the design condition. So you can sort of see where we're at. I've given myself an indoor temperature, and I use these two sets of temperatures to create calculated density. So this is exactly the same sort of thing we would have done immersing that building outdoors. Sorry, immersing that building in water. And then I calculated the pressures that would exist between the total pressure difference for each of these buildings in different locations with different heights. And so we're starting to talk about some fairly substantial numbers. The consequence of that, though, is what happens if there's a leak. And so, what ends up happening in buildings, of course, is we need to allow people to go in and out. And in order to get in and out of a building, you need to be able to move the door. And so one of the ways we define thresholds, and just to put this in perspective, is for a standard door, roughly 2.1 meters by 0.9 meters, or roughly 7 feet tall by 3 feet wide, that standard door, in order for you to be able to open it, the typical guidance for fire codes is no more than 30 pounds force. You're not allowed to have a door that takes any more than 30 pounds force to open it at the door opener, at the handle at the far end away from the hinges. That works out to be about 130 pascals across the door. So if you look at some of these buildings, what ends up happening, there's a substantial number of these buildings that end up having pressures that are higher than that 130 pascals. So So to put this in perspective, the kind of forces that I'm talking about are fairly large compared to the ability of someone to move a door. That 130 pascals is assuming that you're a reasonably fit individual who can move a door. If you're a small child, you may not move the door at all. If you have mobility restrictions, that may also be a very difficult force to apply. So we need to be careful. The other thing to then think about is, okay, how much leakage do I get? And so what I've done is I've assumed here that I've got a gap of 3 millimeters, so it's about 1/8 of an inch, around 3 sides of the door. And then I've calculated the flow rate that would leave through that door for all of those cases. And I've sort of made some, of course, some other assumptions in there. But let's sort of take an example for a minute. So if I'm in Dubai and I've got a 600-meter tall building, bearing in mind that Burj Khalifa is taller than that, but the occupied zone is just over 600 meters. My force, my pressure, the total pressure is about 440 pascals, but the flow rate that would go through that door is 137 liters per second. At that flow rate, this door would be howling. It would be whistling very loudly. And the whistling happens because of some physics associated with musical instruments in some respects. If we go and have a look at that building in Edmonton, and I decided my building in Edmonton at 600 meters wouldn't really happen, but I pick one at 300 meters. I've got 800 pascals, so I'm going to have to manage that in terms of the doors. That flow rate at 300 meters is 188 liters per second. So if you start looking at it, this is actually greater than that building that's immersed 100 meters into water, right? That number wasn't this high. So in closing, sort of, hopefully I've given you something to think about. I've taken you from the ocean environment where I immersed a building in there and so started to do some quick math about what I'm going to do with the pressures. I sort of showed you we can deal with the pressures, but the issue is what happens when I have a hole. And a hole could be that something I put deliberately, but could also be a small crack that I don't know about. A small hole in that space station has a slower leak than we might actually have through a single door on a building on Earth. So that's another way of thinking about this, is that I've got a door on a building on Earth that would leak at a faster rate than a 1 inch by 1 inch hole on the space station. We design a lot of buildings, but we don't really think about the permanent energy loss associated with a lack of consideration to what I've just described, which is stack effect. This is stack effect physics. And thinking about the design of future subterranean ocean scrapers should drive us to think a bit more about those on land. And stack effect causes all sorts of problems, including an inability to close doors, slamming, whistling, and things like that. So hopefully, coming out of this, you'll start thinking about how you get in and out of those tall buildings. And I promise you, those folks in the UK will now be thinking a little bit more about it when they leave the building they're in today, and whether or not the airflow coming in is being driven by stack effect. Got to fix those buildings. Thanks, folks.
Thank you so much, Duncan. And thank you, everyone, for an amazing, such very different presentations, and but all three extremely fascinating. So if I may, I'd like to start with a question for Mike. You were talking about robots, and we often, especially in student projects, get dismissed because of the use of robots, in terms of that we should be designing for the humans. But it should be seen, in my view, that robots can very much help us rather than replace us or make us obsolete. They can help us actually live and do the things that are difficult for the humans to do. So in terms of your missions, what are we talking about in terms of how many robots and how many crew did you have, and how does it work on a kind of practical level? And I have another question, which is to do with privacy, because it was quite astonishing actually to see how little space you had on those submarines, and not even a curtain. And what can designers and architects do about this? I mean, how can we, through design, improve these what seem to be highly utilitarian environments with very, very little physical space?
Okay, let me answer the first question. Yeah, first of all, I totally agree. Humans and robots need to work together as a system, and that can range from everything that, the robot is a precursor that defines the environment so that the humans are better able to survive there. In the case of underwater, we use ROVs for a lot of things. Real simple example, there was a flying eyeball called the RCV-225, and we would use that to pre-inspect the work site, and then we would leave it at the work site. And on some of these platforms are huge, and you can get lost in there. And so we'd leave the robot at the work site with the lights on. And so when you get in the water, you just go follow the robot. So anyway, I think they work well together. And the interesting thing that's happening now is a lot of folks, including my friends at NASA, are trying to develop humanoid robots. I'll start my video. Okay. Humanoid robots that can do the same kinds of tasks as humans. And my sense is, first of all, on all of this stuff, you need to start by understanding what the task is and break that down into forces, torques, dimensional access, that kind of thing. In general, my experience subsea and in space is if you design a task for a robot to do, it's actually going to be easier for the human to do it. And then you can get by with a simpler, more reliable robot. Now, there's some exceptions to that, like our guys built the R2 robot that was a joint project with General Motors. And the thought is, certainly robots can do things that humans can't. So you want to exploit that. They're stronger, they can have longer reach and so forth. But most industrial robots, you don't want a human right next to it because it could fail over and hurt you. And so these newer humanoid robots have all kinds of force controls where they can't hurt you. And so that's an evolving balance. On Earth, you can go fix the robot. If it breaks down underwater in space, it's harder to fix. So there's no one answer, no one size fits all. As far as the sleeping quarters, yes. Like I said, on one of my missions, I've barely slept because this other guy was just snoring like crazy. And so you might or might not be familiar with the rover work that I've been doing, but we have a small pressurized rover. And one of the key features, there's two things. One, any task that you have to do every day, I have a requirement that it takes less than 5 minutes, okay? But we have these private sleep curtains that are covered that have visqueen and all this sound suppression, and they deploy out of the roof and the sides, and we have evolved those to where it can take like 2.5 minutes to set that up. And they are so good that when you're in there, you have to yell to hear your crewmate. And that's really important in a small rover like that, because one person might want to stay up late with his lights on and, do his email or whatever, and the other crewmate might want to go to sleep. So the privacy is really important. But what doesn't work, and I've worked great with our architects and human factors folks, and they always have ideas and they have great tools, and I love working with them. Some of their ideas aren't that great, but you don't, in a small space, you want to keep it open, but have it be reconfigurable for the various functions. And like, for example, just another quick example, and then I'll get off the stage here. We have an exercise device. We need to exercise all the time. So it goes down in the aisle, and then the WCS or the toilet's on the back, and we have pads over that. And so you actually install these pads and you sit on what was the toilet, and you use that as a seat to pedal this exercise ergometer and things like that. So you have to be really clever and really use those spaces well, but you want to keep it open, because when you're in there for 30 days, if you have it all bifurcated into little areas that are even smaller, you're gonna you're probably not going to perform as well. So that was kind of a long answer to those questions.
Thank you so much. We have one more question for you because I know you might have to leave early. How autonomous or human controlled are the NEMO mission robots? And from your experience, which direction do you see the future of these robots going?
Okay, good question. We have in various NEMO missions, I haven't got into it, actually used autonomous robots because you don't need to have an umbilical from the surface. And so it decouples the dependency on floating equipment. And there's one that we use called the Gavia that you can program, and it does a lawnmower pattern over the reef and documents with video and side scan sonar and so forth. And so that's extremely valuable. You couldn't do that with a diver. And you couldn't do that in rough sea states. And so this robot does its thing, and then it comes back to the surface, and then you go pick it up. So that's an example of an autonomous robot. The other robots that we use on NEMO are like ROVs that basically, maybe hold your tools and provide a camera view of the diver working out on the reef, so the ground has different points of view and so forth. Generally, the robots that we use in NEMO, other than the autonomous ones, are not as sophisticated as the robots we use in the commercial offshore oil production. And again, those robots have evolved to be super reliable and use work packages. And a final theme is we had a big blue sky meeting on maintenance to talk about maintenance, for space station and planetary exploration. One of the attendees was a guy named Tyler Schilling, who was an old friend of mine from the 80s. I used to buy manipulators from him, but he now has a company. But he made a comment. He goes, "There's two things that will get an engineer fired on the spot." And he says, "If you show me any design that has a wire harness or any repair that needs a calibration." And his point was, like with a wire harness underwater, it's not deterministic. And so it can, you can get fouled on a pipe or whatever, and they break down. And typically ROVs, we actually implemented the dual Hydra system, because if one failed, we had another one ready to go, and they failed. And even then our availability was probably 85% or something. And Tyler's robots, there's no wire harness. Everything is a module that fits together, and he's getting more like 99% reliability. And his comment was, it takes 20 times more design work to make the robot that way. But it pays for itself just with the assembly itself, which is much simpler, and then, of course, in the reliability.
I have a question for all three of you. It's to do with the leakage. Mike, have you had experience of problems such as leakage, serious leakage in your experience? And the same for Snøhetta. I think one of the questions from the audience was, how did you prevent leakage when the materials meet?
Yeah, so we have all sorts of things. And even on the space shuttle, we had this stuff called duct seal. And, the good news is that the pressure inside is higher than is higher generally than the pressure outside or equal to. And so if you can plug the leak from the inside, that works pretty well. In saturation diving, for example, like in the diving bell, you actually open the exhaust valve and let the water flood and come in just so that you can swim out easily. In the Nemo Aquarius habitat, as the last speaker mentioned, it's open to the sea. And when you get high waves and so forth, you feel those pressure reverberations inside. All of these habitats have emergency gas to feed the leak for enough time for you to safely evacuate. But generally, leaks have not been a problem in saturation diving, and we have had a few small leaks on space station, which again, because the pressure on station is higher than the vacuum of space, it's relatively easy to seal those leaks.
Heidi, can you tell us about under?
Yeah, I mean, our project is not any further than 5.5 meters underwater, so any leakage wouldn't be. It could be, you know, you can't really compare it to what Michael's saying, but at the same time, obviously, you don't want the restaurant room to be flooded. But what we actually did is that we had to test this. I mean, you saw on the short movie that we built under above water on the barge, and then we sank her. I mean, we actually filled the barge with a lot of water so we could, you know, drag her down. And then we released her from the barge so that she was floating. And when she was floating, then she was exposed to a lot of water. And the window, the big window and the small window were both in at that time. And then we were carefully kind of moving her as a boat through over to her side. And at that time, there were the whole window is put in with putty or silicone or those type of sealers. And there were some small leakages in the beginning, but that was also because, you know, it needs to be exposed for the water before it takes some time to set. And the same with the concrete, even if it's watertight concrete, it's not watertight in the beginning. It takes a while until you actually, all the pores and the holes in the concrete, it works with the water, the surroundings, and it tightens itself. So for the under building, the shell outside, the core outside is 45 centimeters thick where it's underwater, and it's slightly thinner at the top. The acrylic window is 25 centimeters thick for the big window, and it's only 8 centimeters for the tall narrow window. And the inside of under is a separate, I mean, it's a separate construction. It's like a box in a box. So there's 15 centimeters gap or airspace between the concrete and the actual inside of under the wall. It's almost like a straightforward wall, if you could call under a straightforward building. But there is, and in this 15 centimeters airspace, there, when it seeps in with a little bit of water, it's pumped out with a normal pump system out of the building. So it's leaking a little bit all the time, but it's taken care of.
Can I ask a question?
Of course, please.
What about insulation?
Yeah, the insulation of the building is in the inner shell. It's in the normal wall, if you call it the normal wall. Yeah.
After the air gap.
Yeah, after the air gap. It's first of all, it's concrete. There's an air gap, and then there is a normally insulated wall. With obviously a membrane. So yeah, with a membrane. Yeah.
So we have a question for Duncan. How can we take advantage of the pressure differentials in a desert environment for natural convection, air conditioning, and ventilation?
How can we take advantage of these pressures? And we're talking about in the ocean environment, or are we talking about buildings in general?
I think we're always talking about the desert environment.
Desert environment? So let's go back. So in a desert environment, we're probably cooling the building. That means that the pressure at the bottom of the building is outwards, so that the building is colder than the outside environment. Air wants to come in at the bottom, drop, and then come out of the bottom. The issue there is that there really is the only reason that that flow is moving is because you're losing air at the bottom of the building. So think of it this way: if you have in that desert environment a hot outside condition and air is working its way in into the top of the building, the first thing you have to do with that hot air that's outside is actually cool it, because otherwise it will be too hot. A personal story there is that I was in Dubai. I was at the top of the hotel building. I was working out one evening, and the pool was outside at that level. And every time someone went out the door to go to the pool, there was this rush of hot, humid air that came into the gymnasium. I'm slugging away on the treadmill. It went from 24 degrees Celsius and a reasonable humidity to somewhere around 38, 39 degrees Celsius and an ugly humidity. And then the air conditioning system would have to work on that to cool it down and make it comfortable again. It was a bit gruesome for a couple of minutes there. And then someone else would come in. So it was a constant process. And the reason I'm just mentioning that is we then have to spend energy to cool that air. And that air then sort of ends up, because of the pressure forces inside and outside, drops and runs away at the bottom of the building. So there is really no taking advantage of it in that it's a parasitic load that we don't want in the first place. The only thing you can really do is take advantage of a chimney effect, where if you want to pump something up a building, you arrange for that chimney to be warmer. So at one point a few years ago, we were working on a project where we wanted to get moisture. This was in the Dubai environment, get moisture from the bottom of the building to the top of the building. And the way we could do it was by creating a large chimney that would receive hot, moist air at the bottom of the building. The chimney was warm. It would draw that air up to the top, and we'd manage to get moisture to be at the top of the building. That's one way you can take advantage of natural convection. But in terms of buildings and cooling them in a desert environment, there's not a lot there. The only other thing that I've seen that people talk about, and there's been one installed demonstration of it, is what's referred to as a solar chimney. And in the solar chimney, the same stack effect phenomena is happening, where we heat the air at grade. We channel that hot air to some sort of tube that goes up. And then somewhere at the base of that tube, because that air is wanting to go up, we arrange some wind turbines. And if you do the mathematics, you can actually demonstrate that it does generate energy. There was a demonstration project that was set up in Spain. I think it was something like 80 meters tall, where they basically arranged for a large greenhouse at the base of this tube. The tube went up, and all we're literally doing is talking about chimney effect or stack effect. It's just standard stuff, if you will. And you can generate energy through that system. The drawback is that you need an enormous piece of land where you're going to stick sort of like a greenhouse, so that you can connect that to a tube that goes up, so you can put wind turbines in there. There was an effort a few years ago to generate one that would be 2 kilometers tall. I was involved in some preliminary mathematics on that, and you can show that you'll generate energy, but it's not a slam dunk, and there's an awful lot of cost to it. Maybe that's sort of, maybe there's a few examples of what ends up happening with pressures in tall buildings helps to answer that question, Rob.
That's great, thank you. So we have a question for Michael, if he's still with us. Regarding robotics and human collaboration, like the one in your images, is that collaboration going to be the same, let's say, on the lunar surface, or will there be more autonomy of the robots or VR controls from an orbital or lunar base?
Yeah, I think Michael may have had to leave. He had a commitment.
That one will have to answer it perhaps.
Circle back to.
So we have one more question. Wondering how the shift from public sector government to private for-profit financing of sea and space exploration have impacted work of the panelists. So perhaps Heidi, you could start.
I have to try and figure out if I understand the question. From public sector to government to private profit. Okay, so if you mean the fact that it's like for example our project was financed by private people. Is that what you mean? And then not why is, but at the same time though, it's also a research center for the marine biologists. So it's also like a collaboration of a lot of people wanting to use this project for knowledge, to gain knowledge about what happens at the shoreline or just under the water level. But obviously it's also, it is a restaurant, so they're making money.
So it's privately owned and privately funded, but it also has a public.
It is privately owned to a certain extent, but at the same time, just because of the marine researchers, they are connected to the university in the southern part of Norway, and also some money has been funded by our own government as well, just because in water life or sea life or marine biology is very important to Norway, as we have a vast coastline. So anything that has to do with trying to figure out what to do, how to behave along the long coastline, how to maintain and to protect the shoreline, at the same time learn more about it and use everything the right way, both on land and underwater, is a very strong something that we all work with, a lot of people working with. So we feel that we have something in Norway that we call allemannsretten, which means that we're not allowed to privatize the shore, along the shore, just because we want everybody to be able to, walk along the coastline, be next to the water. So we have very, very strong historical sense that it's difficult to build there just because of that. In older days it was farming and it was fisheries, so obviously they were building somehow along the shoreline. But for us now to privatize it, it is a question. It's something that we felt as well when we built under that, to privatize a short part of it could be, some people could protest against that. But at the same time, this is a step towards learning about what's going on underwater. And in that sense, gaining more information is better for us all. If that was a part of the answer of the question.
And Duncan, do you have a view on this?
I do. The observation I'd make is that we see, with it moving with more interest in private, let's say, activity, one of the things that ends up happening is there's two different types of private individuals getting into this, or private organizations getting into this. There are those who come in with the knowledge and experience and realize what it costs and the time it takes. And then there's those who come into it without understanding what it takes in terms of cost and time to do something well. And this is sort of going to go to the next question to Heidi, is that doing something well takes time and money to get it designed right and planned properly. It's not just something where you whip it off. And I think some people sort of just don't have an understanding of what it really takes to do something properly and well. So there you go, Heidi. I segued you into the next question.
Project and high quality design that is usually expensive. Building underwater is not cheap because there's so many other issues that you have to consider. So the end of the day, this building was a lot more expensive than the owners first thought. But at the same time, they understood as well, because since we have a lot of collaborators or people working from the offshore industry and the tunnel building, we knew that this was going to be challenging also for the economy. Actually the biggest cost or the biggest issue we had with controlling the cost was because the building sits on the seabed. We needed the marine biologists were examining the seabed to see how sturdy it is, so if we could fasten the building to the seabed. And it ended up that the seabed was a lot more porous, a bit more, it was cracking when we was starting to mount the building. So we needed to reinforce it to make it more sturdy before we could mount it. And that type of investigation we didn't get until quite far into the project. So that put us a little bit back, both when it came to progress on the project and also money-wise. But again, everybody involved in the project knew that this was, like a first-time build. So we knew that there would be challenges, and but none of us knew that it was going to be. I mean, time is money. So, but we learned a lot. A lot of people have learned a lot for their parts, and a lot more next time. That's all I can say.
There's also a question about material choosing. So I don't know if very quickly we can just talk about that. Do you think that today there are better options on materials to build with?
Is that a question to me, you think?
Both.
Both of us.
Yeah.
Okay, I can go first. I mean, when we first developed this project, we were very concerned all the time about, we wanted this project to be a project for the southern part of Norway. We knew that we had expertise down there. We wanted to use as much material as we could from the locally. So, I mean, as I told in my presentation, all the wood is local. We also used, for the concrete, we used the sand that we mixed in with the concrete is also from the area. But at the time, obviously, we watertight concrete is not something you can find in the southern part of Norway. So at the time, when we were constructing this, that was the best thing we could find to do the job properly and for security as well. So maybe we would have thought differently about it today, since the development of sustainable materials goes fast these days. And but at the same time, I felt that we were kind of looking at each different materials and thinking about whether this was the best material to use or not.
Yeah, it's interesting. My perspective on materials is that materials are going to be what saves our species. There's constant evolution and changes and improvements in materials that are going on. Just to think about what's happening with PV panels, what's happening with steel. An example would be in the Second World War, they were building submarines out of a mild steel. These days, we're building them out of something completely different. And what you could do with a submarine now is completely different from what you could do with something 50 years ago. I was involved in a project looking at what materials you'd have available if you went to Mars, and how could you construct anything on Mars with the available materials. There's not a lot of stuff up there, so some of it you're going to have to take up with you, but how do you minimize that? So that's back to that material choices. We are so fortunate that we're making progress that way. And the piece of advice I gave my two daughters was, if you're interested in it, go into material science. That's where the big progress will be. I can't answer the bit about what Heidi chose, but I just know I've got a huge plug for material scientists. They're doing some phenomenal work for us.
I mean, one of the greatest part about this project was actually to try and explore what type of materials, what type of carpentry or craftsmanship that was in the area already, and to get to know what they actually do in that part of Norway. I mean, we could easily buy it from Germany or Oslo or wherever, but it was a great opportunity to learn about the expertise and local expertise in the area. And we realized very quickly that even though this is a part of Norway that is quite remote, there is a lot of skills, people with a lot of craftsman skills.
Thank you so much for fascinating conversation. And I'm sure some of these issues or similar issues will come up in the next discussion, in the next panels. So please stay with us and feel free to contribute. So the next session is I'm particularly excited about is Paula's session, and it's going to be again 3 very different speakers, very different presentations, but with some commonalities. I first came across, the first presentation will be by Dr. Polly Gold. I first came across her work when she was still working on her PhD at the Bartlett, and I still remember her beautiful watercolors and powerful explorations of the history of the Antarctic explorations. After Polly, Hugh Broughton, whose name he doesn't need much introduction, really. His name is pretty much synonymous with astonishing Antarctic station designs. He will talk about the extreme challenge of creating sustainable architecture in Antarctica. He will introduce the design of buildings designed for the UK, US, Australia, and New Zealand, which support science research in Antarctica and the Arctic. He will explain how the designs respond to the extreme environment, support the well-being of crews living away from home in isolation for long periods, and how the designs respond to the cultural identity of their host nation. He will also explain how projects in the polar regions provide an excellent analog for projects on the Moon or on Mars. And finally, Saga Space architects Sebastian Aristoteles and Carl-Johan Sorensen will talk about their astonishing project called Lunar, a lunar analog habitat in the high Arctic. Ever since I learned about it whilst we were still in the pandemic, I found it particularly impressive how they actually managed to realize this and build it and spend 3 months inside and returned back to Denmark completely undamaged. Lunark is a deployable moon habitat prototype developed to meet functional requirements for near future missions and propose a new human-centric architectural design philosophy. A terrestrial analog was tested on a 3-month mission in northern Greenland. In this presentation, they will share the process of developing the habitat from conception to manufacturing and shine light on some of the hard realities related to constructing for the extreme environments in the Arctic. Sebastian and Carl-Johan will also present the lessons learned during the mission and show how Saga are implementing those in future space architecture project. Thank you. So we just need 1 minute for a changeover.
Hi, my name is Polly Gold, and I'm really thrilled to be here. Thanks, Nema and Kais, for inviting me. The title of my talk is Antarctica Through the Archive, Architecture for an Extinct Planet. And my talk is based upon some parts of my recent book, Antarctica Art and Archive, in which the works of the Antarctic explorer Edward Wilson and the thought of the anthropologist Franz Boas are read through each other. And I do this by considering their practices of observation in landscape art and in anthropology. I read through these 2 lives. I read through these 2 lives because one of them pushed the boundaries of geographical exploration of an extreme and uncharted environment, and the other one reconfigured the study and understanding of the human. I make an argument for our ecologically entangled relation between the human and the environment. But I'll also be showing you some archival encounters with Antarctica through art making, both my own and those of this famous explorer, and some examples of built structures and other shelters. But I make my contribution to architectural discussion, not on the level of design programs, but on the level of how we act upon the architectural histories and future imaginings of architecture. But first, I want to orient ourselves. I want to ask, by what measure are extreme environments extreme? The Antarctic environment is extreme in its cold. It's extreme in its remoteness. It is extreme in the levels of endurance that it demands of human bodies. Extreme environments are extreme by measure of their human livability. Antarctica is not extreme to an emperor penguin. In this presentation, I challenge some of what I see as the wrong thinking of the architectural design paradigm that fails to think outside the modernist box of the humanist subject. That wrong thinking sets up a future in which our planet, as humanly habitable, is becoming extinct. In the 19th century, there was great interest in geographical exploration, while there were still places on the surface of the Earth yet to be discovered. In 1895, the meeting of the International Geographical Congress announced that the exploration of the Antarctic region is the greatest piece of geographical exploration still to be undertaken. Antarctica was an unpeopled landscape, void of indigenous human life. It offered a tabula rasa for imperial projects of self-realization. Reaching the poles had symbolic significance with regards to conquering space and putting man at the center. The stories of the attempts to be first to reach the South Pole are deeply embedded in a whole set of cultural values around the human, in contrast to, if not against, the natural landscape. And most usually, it is the man-male pursuit of dominance over that environment. Edward Wilson travelled twice to Antarctica, the first on the Discovery Expedition from 1901 to 1904, and the second time on the Terra Nova from 1910 to 1913. Wilson took on many roles on the expedition. He was the doctor, the head of science, he was a naturalist and a sledging explorer. And by all accounts, and I want to note, he was also a very nice man, much loved by his fellows. But it is Wilson's role as the expedition artist that I'm particularly interested in here. His sense of responsibility in making accurate observations of the new territories in his drawings and paintings, and how the climate got in the way. Wilson used Winsor and Newton materials on his expedition. As sponsors, they wanted to be associated with product reach and stability across global space and time. Winsor and Newton had been embroiled in defending the reputation of their pigments against accusations of lack of permanence. And they were obliged to set out and identify which of their pigments were fugitive and likely to fade. In return for their sponsorship, in a letter, Wilson extolled the remarkable stability of the Winsor and Newton watercolour and paper under the extreme conditions of Antarctica. Yet, the practice of making watercolours was not standard across all space and time, but subject to climate too. Wilson had complained during the ocean ship crossing about what happened to his watercolours as he crossed climate zones. My paint box has been upset more times than I can say, and this in the tropics, where most of the paints are semi-fluid and all get swamped in pasty vermilion, makes it hard to know where you are. Everything wanders if it isn't chained up. This watercolour shows the hut at Hut Point, which was built on the Scots Discovery Expedition from 1901 to 1904. Hut designs had their climate stories too. It was a prefab structure fabricated in Sydney, made of Douglas fir and Scots pine. It featured an open veranda on 3 sides intended to circulate air for cooling. And it was based upon an Australian design that seemed better suited for hot climates. So, transplanted to Antarctica, unsurprisingly, it proved impossible to heat. So the 47 men lived on the ship for the duration, which had become unintentionally trapped in the ice for 2 years. They only used the hut as a store and entertainment room and a venue for their talks. The hut gave its name to Hut Point Peninsula in McMurdo Sound, which became the site of the US base in the New Zealand segment and is now the size of a small township. The hut at Cape Evans is 20 kilometres north of Hut Point and was constructed during Wilson's second expedition. It provided the base for the Polar Party's attempt to be first to reach the South Pole. The Terra Nova hut was erected in 1911. It was prefabricated in England, tested in New Zealand before being shipped to Antarctica. It was the home to 25 men and insulated with seaweed and lined with felt. The hut was designed also with these internal temperature zones, the floor level remaining below freezing to make it easy to sweep out snowdrift, the mid-body area kept at 10 degrees Celsius, and the ceiling height at 21 degrees Celsius. Whereas the tents used while sledging towards the South Pole experienced temperatures in the region of -50 to -60 degrees centigrade. Here, Wilson is pictured sketching on the Beardmore Glacier on the early outward bound leg of the attempt to reach the South Pole. Although this appears to be the typical image of an open-air watercolour artist making immediate impressions of the view before them, it is, in fact, impossible to work with watercolour in sub-zero conditions. Wilson's works were begun in monochrome as quickly executed pencil sketches made out in the open. As regards colour, one can do nothing out of doors. Drawing too was often very difficult in the freezing cold. Pencil lead became hard and difficult to use, fingers froze, eyes suffered from snow blindness, and as soon as you breathed near the paper, it was covered in a film of ice through which the pencil would not bite. So the faithful copyist, Wilson, trying to work direct from nature, was dependent on pencil sketches supplemented with annotation and note-taking. Here, Wilson is pictured inside the hut at Cape Evans in 1911, in the dark, long winter months, working on a watercolour. Wilson had to work against the distortions of memory and the colour cast by acetylene lighting to bring accuracy to the watercolour paintings that he produced there. So my argument is that with a close reading of these dislocations in the practices of observation, the archive of Antarctic watercolours can be interpreted in a way that foregrounds climate. And it can also be done in a way which produces an ecological, post-human understanding of human and environment. His watercolours are remarkably colourful, and it's interesting how they show the colour of the environment, which is usually dominated by, in our imaginations, by black and white photographs of that period. So finding colour in the archive is something that I'll return to, but in terms of colour as a marker of racial difference. The Norwegian team, led by Roald Amundsen, were the first people to reach the South Pole. They left the first shelter there as proof of priority, their tent. Scott's team arrived second and then perished on the return leg of the journey. Evans died from a head wound and frostbite, and Oates famously wandered off into oblivion. Wilson, Scott and Bowers' frozen bodies were found by a search party the following season, heartbreakingly close, only 11 miles from the next food depot that might have saved them. The South Pole, as the last elsewhere of the empty places on the map that figured as the prize to heroic explorers, is now a place that cannot be returned to in its undiscovered state, but its traces are recorded in the archive. And it's through the archive that my encounter with Antarctica has occurred. One of the major archives of polar material is to be found at the Scott Polar Research Institute in Cambridge. On entering, you see pictured Antarctica, the names of explorers encircling the continent in gold. In the domed ceiling of the vestibule, reminding us that architecture is the shelter that stands between us and the open sky. And it's reminiscent too of the geodesic dome that was the iconic structure at the South Pole Amundsen Scott base from the 1970s until its deconstruction in 2010. Archives tend to be quite chilly to preserve the artifacts. And I'm not saying that my suffering was comparable, but I did have to wear a cardigan sometimes. In the archive, I could handle Wilson's watercolour of the hut at Hut Point, but in a distorted repetition of Wilson's watercolour practice, I too found that I was unable to use watercolour to make a direct copy of what I saw. I found that in the archive, the use of watercolour is excluded due to an institutional prohibition made in order to preserve the vulnerable artefacts in an air-conditioned atmosphere of controlled temperature and humidity. Encountering Antarctica through the archive and these small-scale two-dimensional works on paper by Wilson made me want to remake those landscapes into three-dimensional worlds. I made distorted copies of his watercolours on sandblasted glass placed under hand-blown mirrored glass globes. And the huge icebergs pictured in his paintings I reformed in glass versions in domesticated ornamental dimensions. This was as a practical method, as my way of understanding his watercolour representations and their relation to the environment. So my ecological argument is invested in the belief that the transformation in the human relation to the environment to one that is more properly ecological is also dependent on emancipatory politics of gender and race. And this I have in common with many eco-critical thinkers. This is why I paired the examination of Wilson's archive with the work of groundbreaking anthropologist Franz Boas. Franz Boas, born in 1858, a full 14 years earlier than Edward Wilson, died on December the 21st, 1942, in the midst of delivering a speech criticising racism. He collapsed in the arms of Claude Levi-Strauss, his colleague and protege. What a way to go. Boas was committed to the role of observation in the field and developed a qualitative and engaged, reflexive mode of participant observation. And much of his life work focused on exposing the distortions that interpretation wrought upon observation. He aimed to show the relativity of culture and did this in museum displays through development of the diorama, in contrast to a typological evolutionary arrangement as extolled by people such as Pitt Rivers. My point is that in different designs of anthropology museum display can be read contrasting arguments for the human relation to environment. Here, in the unrealized proposal by Nervi for the new Pitt Rivers Museum in the 1960s, is the inclusion of a climatron at its heart to provide the natural environments as a backdrop to the displays of material culture. Human environment, extreme or otherwise, is imagined here as separate from human culture. Significantly, Antarctica, a place without indigenous human inhabitants, and until recently with no human history, does not feature in the Museum of Anthropology because museums of ethnography address geographical areas through their inhabitation by human culture. As for the archive of Antarctic heroism, there are other stories to be found there, and other figures too. For example, in the Wellcome Medical Diary, Wilson, as the expedition doctor, carried Wellcome pharmaceutical products and wrote his sledging diary in this book. Wellcome was another expedition sponsor and was a collector of ethnographic medical artifacts, and he illustrated his publications with them. This book, that went to the South Pole, was found with Wilson's frozen body and is illustrated with multiple Maori motifs. And during the winter seasons when sledging was impossible, the expedition crew amused themselves with debates on women's suffrage, on the future of the British Empire, and with lantern shows like this one. This Japanese woman featured in a magic lantern show presented by the expedition photographer Ponting about his visits to Japan. The near mythic quality of the polar journey and its destination of the pole and the ultimate destiny death is recorded in and remembered in the archive. But the archive is unstable and always open to refiguring. And I suggest we refigure it with a nomadic subjectivity. Taking the nomadic approach to the archive of Antarctic heroism is a strategy for undoing and subverting a subjectivity, male, white, European, that is all too comfortably at home there at the center of things. One of my heroes, the feminist philosopher Rosie Braidotti, writes, "The nomad is my own figuration of a situated, postmodern, culturally differentiated understanding of the subject in general and of the feminist subject in particular. And although inspired by the experience and cultures that are literally nomadic, not all nomads are world travelers. Some of the greatest trips can take place without physically moving from one's habitat. Consciousness raising and the subversion of a set of conventions define the nomadic state, not the literal act of traveling." So it's clear that the explorer, though traveling far, may not in fact move very far at all in terms of the subversion of the conventions of the subject. So what kind of humans do we need to become for the coming future of extreme environments? The heroic explorer requires a nomadic refiguring. Ursula K. Le Guin, the sci-fi writer of imaginative anthropologies, wrote a short story titled Sir, speculating that a group of South American women made it to the South Pole first, but decided to leave no trace, no footprints even. And bones of a real indigenous Chilean woman who died at around 1820 was found on an outlying Antarctic island in the 1980s. Not there by choice, perhaps, but there nonetheless. In his book, Beyond Sustainable, Ryan Ludwig states that we need the attitude of the astronaut rather than the cowboy. That is, the astronaut as a conserver of limited means on a biosphere of finite proportions, rather than the cowboy, a pioneer of unlimited space, frontiersman. We need to be astronauts on planet Earth. Did the Antarctic expedition crew in 1911 have similar pause for thought? I think so, as shown in this poignant sci-fi example I'm about to share from the archive in the South Polar Times. It was a one-copy edition magazine that the crew amused themselves by writing and sharing. And this magazine featured a number of science fictions that imagined their endeavours recorded in fragmented archives met by future humans. And in this case, interstellar aliens from Sirius, written by the expedition meteorologist Simpson. The story describes the decline of civilization, decrease in numbers of blizzards, failure of the Ross Sea to freeze, an absence of very low temperatures on the barrier, and the desperate attempt to glean knowledge from the archives. I know not why I write, for there will be none to read, but the history of the human race since the dawn of civilization has been written, and I feel impelled to set down the memo of the end. And what Simpson's sci-fi tale tells it of is the failure of the world to learn from the British Antarctic expedition of 1911-12, and the warning of a changing climate to be found in that archive. Archives tend to be on the cold side. As for the cold, it's an astonishingly effective preserver. The hut at Cape Evans remains an extraordinary vivid freeze frame. And if you navigate your way with Google to the desk where Wilson worked on his watercolours, you'll find there preserved for over a century the corpse of an emperor penguin. To conclude, Antarctic exploration offers examples that attempt to modify the extreme environment towards human comfort. The expedition tent, the huts, the geodesic dome, the ship Discovery, and also architectures that, although not located in Antarctica, refer to it, such as the Scott Polar Research Institute and its archives. But my point is that this extreme environment is no longer only conceivable as an elsewhere that intrepid explorer hero types might make the choice to explore. Extremes of environment are coming to us under the new regime of the climate crisis. And we need a nomadic refiguring of the human to address this. For architecture to step outside the box of the humanist subject, we need an ecological assessment of architecture, not just as discrete built elements, nor as technological solutions to maintain comfort or livability in extremes, but as the entanglement of interconnected relations between humans and non-humans, the natural and built environments, our interpreted pasts and imagined futures. Thank you.
Thank you so much, Polly, for that fascinating presentation. And now, Hugh Broughton, architects.
Thank you.
Welcome.
Thank you. And thank you so much as well, Nirma, for inviting me to talk at your conference today. I've been listening into quite a few of the talks, and it's just been totally fascinating and amazing as well how many similarities there are, despite the differences between the environments, whether underwater, in space, or in the polar regions. So in my talk today, I want to talk about our work in Antarctica. And I'm going to do that around two stations in particular. One is the Halley 6 Antarctic Research Station, which we designed for the British Antarctic Survey, and one which is an ongoing project which we're designing for Antarctica, New Zealand, for the redevelopment of Scott Base on Ross Island. So yeah, very close to Hut Point, where Polly was just showing us Scott's expeditionary hut. So as a company, we have been working in Antarctica now since 2005, and we've been involved in stations both on the islands, on the peninsula, and on the mainland. I'm going to show Halley, but currently we're involved in Scott Base, at Davis, and at Rotherham for the British Antarctic Survey. So this is the site of Halley 5. Halley 5, all the Halleys were constructed on the Brunt ice shelf, which is a shelf of ice which has flowed off the main continent of Antarctica and is supported on the Weddell Sea. The ice is moving constantly, flowing out to sea at the rate of around 400 meters per year and is around 150 meters thick. It's a very dynamic site. This is the previous station, Halley 5, split into 3 buildings, 2 science buildings, one for near ice chemistry and one for outer space research. And the third larger building you see on the right-hand side was for habitation, so for bedrooms, dining, some office spaces, storage, and so on. And as you can see, a flat and very hostile environment, essentially a desert. For much of the year, the temperatures are extremely cold and never rise above freezing, even in the summer. The lowest temperatures recorded to Halley are around minus 56 degrees Celsius. And as temperatures rise during the summer, so katabatic winds blow off the main polar plateau, sometimes in excess of 100 miles an hour. So we thought it was windy here in London today, but it gets a lot windier in Halley in the Antarctic. The resupply takes place just once a year when the polar resupply vessel arrives at the edge of the ice shelf, and all the supplies required to keep the station operational for the remaining part of the year have to be unloaded and then carted on sledges to the station itself. This requires a passage to be found through the sea ice, which can often be extremely difficult, even for ice-breaking vessels. So you might think in that context of extreme temperatures, extreme winds, difficult logistics, actual darkness for 3 months of the year, why would anybody want to live in such an environment? And the answer is really very simple and lies at the core of modern day research into climate change. And it's because the things that happen in terms of climate in the polar regions affect us all. And in fact, it was in the early 1980s that 3 British Antarctic scientists working at Halley first discovered the hole in the ozone layer, which subsequently led to the Montreal Protocol banning the use of CFCs, which even to this day remains probably one of the most significant pieces of global environmental legislation brought into existence. And there's science carrying on at all the different research stations in Antarctica today, which is again informing politicians and leading the fight against climate change. But at Halley, a specific problem became observed in around about 2000, when a crack started to develop in the Brunt ice shelf. And the predicted line of the crack was along this red dashed line shown on this drawing here, grounded at the top and the bottom. And the site of Halley 5 was due to be on the wrong side of the crack. And as Halley 5 was elevated on steel legs, which were locked in the ice, it ran the risk of disappearing on a giant iceberg the size of a small British county. So as a result, the British Antarctic Survey decided to commission the design for a new research station, Halley 6, which they required to be mobile so that it wouldn't disappear on an iceberg and wouldn't need to be removed as the previous 5 Halleys had been. So to find a designer, they went through a design competition, and after about 6 months of design interviews and preparation, our team was selected as the winners. And this was our concept for elevated, connected modules supported on hydraulic legs on giant skis. So the idea here is that the giant skis can be used for relocation. The hydraulic legs can be used to climb above rising snow levels, and the buildings are split into modules to allow them to be hauled by bulldozers to new locations if ever there's the risk of the site disappearing as a giant iceberg. So we came up with the concept of a series of equally sized single-story modules raised on 4 legs, and these could be used for laboratories, they could be used for bedrooms, they could be used for offices, for storage, and also for energy modules containing combined heat and power generators, wastewater treatment, water treatment, fuel storage, fire suppression systems, and so on, with 2 of these energy modules connected by a bridge so that if one fails, the other one can be brought into operation. However, what we found is whilst we could fit most of the requirements of our brief or program into these standard blue modules, each one around 1,600 square feet, 150 square meters, there were some aspects of the brief which required to be co-located and needed a bigger solution. So for this, we developed a 2-story building called our central module, eventually named after Sir Robert Fulton Scott, the explorer. And this contains the kitchens, the dining area, open plan bar, and also quieter spaces upstairs for browsing the internet, watching TV, going to the gym, and so on. And this drawing here is one of the drawings that we used in the design competition. And we have a couple of features here that unfortunately didn't get included in the current scheme. One was the hydroponics greenhouse at the center of this drawing. Unfortunately, that was removed due to the potential of smell and also contamination by greenfly into the station. And the other one was the climbing wall you can just see in the background there. We thought, well, people who go to the Antarctic do love outdoor adventures, so they'd enjoy to have a climbing wall to go from the lower level to the upper level, until the British Antarctic Survey's health and safety officer pointed out to us the proximity of the bar and told us we had to make a choice between the bar or the climbing wall. So you can imagine which one got the vote. Before construction could take place in Antarctica, we erected both the red module and one of the blue modules in South Africa to test buildability. This was absolutely crucial because any mistakes that we encountered in South Africa could easily be rectified, but any mistakes that we would encounter in the Antarctic would be truly difficult to solve, especially as there's obviously no way of getting extra supplies without a lengthy shipping journey across the Southern Ocean. So you can see we were able to test the installation of the hydraulic legs, the lifting ability of those. We were able to test air tightness and also the installation of complex glazing systems and so on. Then when everything was ready, it was shipped across the Southern Ocean on an ice-strengthened vessel to the edge of the ice shelf, where it was unloaded and hauled to the construction site next to the original building, which was used as accommodation for the construction crew. And then it was put together using a factory line technique for assembly. So the largest components were the space frame substructure of one of the modules, and then the cladding we installed was made in glass fiber, so we could have really large panels. So this panel here, for example, is around 3.5 meters, 10 foot high by around 10 meters long or around 40 foot long. Many of the rooms inside the buildings were prefabricated, so bedrooms, bathrooms, plant rooms were all prefabricated, fully fitted in, and so on. And then that allowed the buildings to be built as quickly as possible on site in construction periods of just 10 weeks per year. And when everything was ready, it was dragged using the bulldozers from the site of Halley 5 to the site of Halley 6, around 10 miles or 15 kilometers further inland. And the modules moved at the rate of around 10 kilometers per hour, and then took the rest of the day to fit together using flexible silicon connectors like you get between trains carriages to connect one to another. And here you see the connected together station. So it comprises 8 modules. On the left-hand side, there are 2 science modules Then there are 2 energy centers connected by a link bridge. Then the main red living module, and then finally 3 blue modules, one containing the commander's base, the boot room, the doctor's surgery, and the other 2 containing bedrooms. So 8 bedrooms in each of those final 2 buildings to the right-hand side, bunk rooms, which people can share in the summer and have to themselves during the winter. The break in the middle of the station allows for people to escape from one side to another in case of fire, remembering that if there is a disaster in the middle of winter, it can be many, many months until people can be rescued. So I'll just show you some pictures of the interior. This is the ozone and meteorological laboratory on the top of one of the science modules. And this guy at the end here, he's using a Dobson spectrophotometer to take measurements of ozone, measurements which have been taken at Halley since its establishment in 1957. This is the interior of the main social module, which has a double height space with a pool table at its heart. And that glass incorporates double glazed panels with a nanogel insulation, nanogel which was invented originally by NASA to insulate the end of the space shuttle cone as it re-entered the Earth's orbit, and therefore has a very high thermal protection properties, ensuring that we didn't get any condensation despite using such a large window in such a cold place. This is at the very center of that main central module where there's a stair rises up to the quieter parts of the building. It's lined in Lebanese cedar panels because we determined that Lebanese cedar is one of the very few veneers which gives off a nice, pleasant smell in a place, of course, where there are no plants. So it was just one way to combat people's sensory deprivations in a place of many sensory deprivations. As you can see, one of the other deprivations is of the British royal family. So we address that with a nice picture of our Queen within the middle of this module as well. We also work very closely with a colour psychologist, Angela Wright, who helped develop for us a special palette to counteract the effect of seasonal affect disorder, which can really influence people working in the Antarctic, especially in the 3 months of total darkness. So she came up with what's called the spring palette, which combined with daylight simulation lighting throughout the station does help to bolster people's mood, bolster their levels of serotonin at the expense of melatonin, particularly during those winter months. This was applied also in the bedrooms, which you can see here. Each of the bedrooms has a view out, something that the previous station didn't have. Plenty of storage. There's room enough to work privately on your computer or watch movies, but the bedrooms are not so spacious that people hide away from the community, which is also a key factor in the design. The weather isn't always that great. As you can see here, there are often thick mists, high winds, driving snow driven by the wind, and then of course, long periods of darkness and extreme cold. And this is what the station looks like in the middle of the winter, when the wind has blown from the left-hand side, scoured the snow away from underneath the modules, and then deposited it in a large drift on the right-hand side. And then at the end of the winter period, the British Antarctic Survey will jack the buildings up using the hydraulic legs, push new snow under the skis and level off the site underneath the modules, ready for the next winter. For our own firm, the benefit has been that we've been, as a result of the success of Halley, able to work on a number of other Antarctic and Arctic projects. For Spain, top left, for Juan Carlos, which is one of the islands off the Antarctic Peninsula, now completed. For the US, at the Summit Station in Greenland, a project for an atmospheric observatory, still waiting for final funding, unfortunately. For Davis Station, an ongoing master plan for the redevelopment of that station in East Antarctica. And currently on site is this building top right, which we're developing as part of the Antarctic Infrastructure Modernisation Programme with the British Antarctic Survey at Rothera, which is a science and operations building, which also provides a communications centre for BAS in Antarctica. probably the largest project which we're involved with in the Antarctic currently is the redevelopment of Scott Base for Antarctica New Zealand, which sits on Ross Island. It was also established in 1957 by Sir Edmund Hillary as part of the Trans-Antarctic Expedition, and it sits in the shadow of Mount Erebus that you can see top left there. The reasons for the redevelopment is, despite a successful station built in the 1980s, a series of deficiencies were becoming apparent, whether that's multiple levels reducing efficiency, services which were very difficult to access and therefore maintain, out-of-date water production plants, sometimes as old as 30 or 40 years old, compromised fire safety, making it a bit dangerous for people if a fire should erupt, the biggest challenge for anybody working in the Antarctic. Constant snow drifting, which needed management around the buildings to stop ice damaging the cladding, and dangerous removal of ice and snow from the roofs, which compromises health and safety. So after much engagement with different people who'd worked at Scott Base, we looked through a series of different options, both at paper level and also working with RWDI, with Duncan's team in Guelph in Toronto, where we made models of the proposals, put them in a water flume, allowed sand to drift over, simulating snow drifting around buildings to determine the optimum layouts of one building compared to another. And this is the current state of the proposal. 3 interconnected buildings which step down the slope of Pram Point on Ross Island, connected by link bridges, so that the lowest level of the upper building connects to the upper level of the middle building, and the lowest level of the middle building connects to the upper level of the bottom building. The upper building contains accommodation. The middle building is where there are science laboratories, administrative areas, and science preparation spaces are located. And the bottom building contains workshops and stores. There are also helipads, and retained on the site is the historic Trans-Antarctic Expeditionary Hut, first established by Sir Edmund Hillary in 1957. One of the parts of this project which I found most interesting is weaving in the cultural narrative of New Zealand and of New Zealand's involvement in Antarctica into the design, particularly the interior design of the project. A part of that involved a hui, which involves staying over in a Maori meeting house in Christchurch, where we talked about those aspects of Maori culture and New Zealand culture, which would have a big impact on the interior design. We also look very carefully at the designs of the huts of the explorers, whether that's Scott Shackleton or, in this case, Hillary's TAE hut. In Hillary's TAE hut, colour psychology played a significant part in the design, and has also played a part in our own design. This is the entrance of the building, where we place the dining room above, so there's a large window to be welcoming, with a big deck where people can also be welcomed, and a welcome space at the entrance. So you can see welcome, a key feature of any building in New Zealand. The principle of the design is really very straightforward, with a very warm jacket around habitable spaces inside. And then this is the main living building, with a big double height central space in the center, running the full length of the building to emphasize sense of community. I mentioned we work with a colour psychologist at Halley, and we've worked again with Angela to develop a palette for Scott Base, but a different palette, where we used group 1 colours in Halley. We've used group 3 colours at Scott Base as better representing the culture of New Zealand and a intense interest in landscape and environment that came out through the consultation. And then we've started to apply those colours through the design of the building, and you can see a particular prevalence towards natural finishes, and in particular Southland Beach ceilings, Southland Beach coming from the South Island, evoking not only a sense of home, but also cocooning the residents against the extreme environments outside. And then further down in the lower buildings, you end up with more functional spaces linked by these link bridges with views out into the landscape to constantly remind people of their location, and therefore of the seriousness and sensitivity of the place in which they find themselves. And that takes you into other collaborative workspaces, science preparation areas, and workshops. And in all of these, there are constantly views from other spaces into them to ensure people's health and safety, in particular when they're working as part of only a small crew of 20 people in the midst of winter. The station is approaching its construction phase. It will be built in New Zealand, and then it will be split into 8 sections, 8 large sections, 25 meters wide by 25 meters long, and shipped on this giant cargo vessel to Pram Point, where it will be unloaded and then wheeled into place using these self-propelled motorized transporters. So the largest piece of volumetric construction ever attempted in Antarctica. And this is what the finished station will look like. And I know I'm short on time, but I'll just run very quickly through the parallels with space design, because I thought it'd be kind of interesting for today. And I don't think it takes much of a jump to see the comparison between the modularity of buildings in the Antarctic and the modularity planned for future developments on Mars. We can see that the landscape of Mars is like a desert, much as the landscape of the polar regions can be like a desert. And that even the form of logistics can be quite significant in determining the types of construction, with only small ships in some cases delivering some of the construction materials, or small spaceships delivering to space. And even the clothing is similar, probably a little bit more intense in space, but nonetheless in Antarctica, we have to think about the restrictions in terms of gloves, very thick clothing, and restricted eyesight when people are putting buildings together. So one of the interesting tasks we've had as architects is collaborating with NASA to determine the minimum habitable volume for interplanetary missions to Mars, around which the engineering of future spaceships might be developed. So we work with a group of human factor experts and engineers at the Johnson Space Center to look at the different spaces that would be needed within the space module, whether that's berthing, galleys, workspaces, exercise areas, and hygiene spaces, to then plan out and come up with an expected volume of between 18 to 20 cubic meters for a 6-person crew, around which the engineering of the module would then need to be developed. Whereas I believe in the past, it's normally the engineering that's been developed first and left a volume for the astronauts to inhabit. And I know at the beginning of today, Ella was on the first call talking about a more terrestrial but equally Martian project to build a prototype Martian house in Bristol. The project should be on site in April or May, and we are going to be building a portion of this community that you see in the bottom image here, which is partially underground in the Martian landscape and partially above ground, and will provide a really exciting interactive prototype for members of the public to get involved with as a kind of counteraction, I guess, to the development of Mars currently planned by big corporations such as SpaceX, or countries such as the US, China, or Russia. And with that, thanks very much. Sorry if I took too long. Yeah, really enjoying myself. Thanks.
Thank you so much, Hugh, for that fascinating. So we'll have to move on straight on to Sebastian at Aristoteles and Carl-Johan Sorensen from Saga, and we'll take a question and answer session afterwards.
Yes, so we just had some feedback.
We are sitting in the same room.
All right, so my name is Sebastian, and this is Carl, and we are the co-founders of Saga Space Architects. And I couldn't have imagined a better transition from Hugh Broughton to just touching a little bit about space, a lot about the Arctic, and then going into us. Because we've looked, obviously, a lot of Hugh's work. So let's just see if we can present it here.
Share the screen.
Let's just go back.
Oh, yeah. Sorry. Yeah, is it coming on? Can you see that?
Yeah, all right, we are through. All right, so what we're going to present today is probably our most ambitious project to date. It is a simulated moon habitat in the very, very far up in northern Greenland, 1,000 kilometers north of the Arctic Circle. Just very briefly, Saga Space Architects is a small design studio in Copenhagen. We are growing. We are 11 people now, a mixture of architects, engineers, and software developers. We not just only design all our architecture, but we also have built most of our architecture. So the Lunar habitat, we designed it, we built it, we did all the logistics for the mission. We found a place in the Arctic, we shipped it, we unfolded it, we did everything.
We lived in it.
We lived in it, yeah. So there has been a Danish national documentary of 6 episodes made about the entire expedition. Me and Carl, we lived inside the habitat for 61 days on 4.5 square meters. Of course, the volume is larger, it's a tall structure, but the footprint was 4.5 square meters. We did this in 2020, and last year in 2021, we won an Index Award for the project. So why did we choose Northern Greenland? We specifically chose Northern Greenland as the best simulation site on Earth for a moon mission. So the first reason is the lighting environment. So it doesn't matter where you are in outer space, if you are in orbit, on Mars, on the moon, you have an alien lighting environment for humans. And that's not healthy for our circadian rhythm. And in Northern Greenland, we found a similarly strange lighting environment. So in the first part of the expedition, we had almost always sunlight. And in the last 30 days of the expedition, we had complete darkness. The sun didn't go above the horizon. Then you have the vast wide landscape of the Arctic, which is similar to the vast wide landscape of the moon. You have extreme temperatures. And why is that important? A lot of simulation missions around the world is done in more comfortable environments. But I believe that it is in human nature to cheat. If you really want to, like on day 50 of the expedition, and you really want to go outside without your spacesuit, it would be too easy to do that. But if there's minus 30 degrees Celsius outside, you really physically cannot go outside without your spacesuit or your Arctic suit. Then we chose Northern Greenland because it's super isolated. So there's not help around the corner. If something broke in the habitat, we would need to fix it ourselves. If me or Carl broke during the expedition, we would have to fix each other. So you are very alone. Help is not around the corner. Your friends and families are not around the corner. And all of these features or challenges, you could say, we would like to say it's features, creates a realistic amount of stress. And this was the entire foundation for the expedition, to create a realistic amount of stress, to test how can we create a piece of architecture that works as countermeasure to the stress. So this is the project. This is the Lunar habitat. I'm just going to go through the structure with you. Actually first, so I just want to tell you a bit about the site conditions. So just to give you an intuitive feeling of the environment we were living in and designing for, this is what 24 meters per second looks like. It's a storm in Florida. This is what 32 meters per second storms looks like. Also, I believe this is also Florida. And here in a bit, you can see the roof of the building being torn off. And there we go. And in Northern Greenland, 50 kilometers from where we were, one of the strongest or one of the fastest winds ever recorded at 93 meters per second was recorded. And in terms of degrees, we were experiencing minus 30 degrees Celsius, but what we learned quite quickly, we knew this already coming into the expedition, but wind chill is a completely different thing. When you factor in the effects of humidity and wind, minus 30 on a wind still day is not a problem, but as soon as there's a little bit of wind with a little bit of humidity, minus 41 can be extremely, extremely cold. And if we go through the habitat, so there is, we like to say that it's 1.5 stories tall. So if we do 2 splits, the first, to the left, we have the lower living quarters and airlock. So the first area you walk into is the airlock and wet room. This is where we went to the bathroom, but it's also where we took our showers. We didn't have running water. All the water was melted ice that we would chop outside every day. But we had wet wipes. So for 61 days, we had wet wipes. Then we have the living quarters, which is the most dynamic space of the expedition, or of the habitat. This is where we spend 90 to 95% of our waking hours. The tables fold up, so it was a workout space. There was different things that made it into a dynamic space. Then on the top floor, it's too much to call it a floor because it's very tiny. We have 2 sleeping pods, and Carl is 2 meters and 6 centimeters, so he's a very tall guy. I'm more average sized and 183, but we both barely fit inside the sleeping pods. So we found some awkward sleeping positions, but we made it work. And this is what that looks like. I don't think we have time for this, right? What does the time say?
I think just go briefly through it.
Yeah. So we talked a lot about the dangers of space and how humans are not made to live there. And this is what the current state-of-the-art space station looks like. It's the ISS. And this looks more like a laboratory than a home. What we wanted to create is a home. That's why SAGA Space Architects exists. And this is, to us, the best example of space architecture. This is the cupola window, probably the window in the world with the best view in the entire galaxy. This is not crucial for survival, but it is important for making the astronauts thrive in outer space. And I think that's distinction of what we want to make. And here, before coming to this presentation, I Googled what is the best day on planet Earth. So I Googled best day on planet Earth, and I believe this is an image of Hawaii at sunset. You know, when I look at this image, I can almost feel I can hear the palm trees, the leaves in the wind. I can hear the waves. I can almost taste the salt from the sea, and I can feel the sun on my skin. And this guy says that making a spaceship is basically, because everything is mechanically controlled, you have the opportunity to make a day in a spaceship like the best day in Hawaii. But we would actually argue that that is wrong, because then a day would look like this. This is a graph of stimulation, and your day would be flat. There would be no difference between yesterday and today and tomorrow. It would all be flat. And what humans really need, and all living things, is stimulation. You need variation. You need cold days and hot days. Today it was extremely windy, but that makes us remember today walking around the streets of London, and that gives us a sense of time. And one of the ways we added this variation was with lighting design. So we designed these large LED panels with very high accurate, with very high CRI LEDs that simulated skylight. So in the morning, we would wake up with a sunrise inside the habitat, then with the daylight, then sunset and twilight and darkness. And this would stimulate, first of all, it would give us a sense of time in the dark periods, but it would also stimulate our sleeping rhythm. And so we would get tired at night. And this was the most beautiful sunset during the expedition. So we had different days as well. So we simulated weather. So some days would be boring, some sunsets would be beautiful. And this was the most beautiful sunset during the expedition.
Yeah, I'm just going to carry on and talk a little bit about the structure and why it looks like it does, because a lot of people ask, why does it look like a black mechanical ananas? And it has a really good reason for it. One of the principles of going to space is that jet fuel is really expensive, and so is space. Hugh Broughton touched upon the fact that you need to ship things in vessels, both to space and in ships when you go to the Arctic and Antarctic regions. So things have to expand, and inflatables have their advantages, and we wanted to see if there are other approaches to take, because there are also advantages of having rigid panels instead of something that is curved. One thing is that you can put solar panels on, and in Greenland, in the Arctic, it also has the advantage of being able to withstand the wind pressure and the extreme environmental factors that were at the base. So we knew it had to expand, and there are many ways of doing this. And our process started out with a lot of sketches. We looked at things that were more like harmonica structures and things that were assembled. And we did a lot of digital mock-ups looking at the geometric volume and proportions. And through this process, it's a very chaotic, creative process. We started looking at patterns in nature and at origami. And this is what we chose to discover further. So we went through a process of iterative prototypes to see if there was any value in using origami as an alternative to inflatables. And the first part was to figure out the language of origami, how to design the tessellations and control them. And we did this first as a flat plane. We know it from origami when we fold it. It's always a flat piece of paper. But we knew that we needed to make a volume. And making a volume starts with adding curvature in one direction, which was achieved then. But it's something that hasn't quite been done before. So we also reached out to experts in the field of origami. One of those is Robert Lang, who works at NASA. And we sent an email asking if he had any advice on how to make this closed origami sphere. And he sent a long email back saying that essentially it couldn't be done. But he was interested in the idea, and if he would like to explore it further, it would be $300 an hour. So we had to do it ourselves, and we managed to design it in such a way where you have rigid panels but connected to flexible seams that absorb this deformation that Robert Lang was concerned about in our design. And in the end, we generated and simulated this closed geometry, which then defined the entire architecture of the habitat as well. It's something that hasn't been built at this scale before. So the only way to do it was to go through this series of prototypes, always going up in scale for each prototype until we were sure this is the last prototype we did before building the final habitat. And this proved that it worked at the scale we were hoping to achieve, and we can actually test the materials and especially the connections to the seam here. So the origami shell is the flexible part, and then it has to interact with a static structure which can resist these extreme hurricane wind speeds that Seb mentioned before. And our solution was to integrate a foldable structural ring which is made of aluminium, and then connect that to a frame that connects to the ground. And here you see the actual habitat unfolding in Greenland. This is me and Sebastian working alone over 24 hours to unfold it without any external help. And this is why it looks like this as well. We could have made a kit of parts, but as you see, it's snowing, it's windy, it's rain, and we need something that is a coherent whole that folds out. Yeah, I'll also try to speed up a little bit. But this structure, again, hasn't been, there were very few examples we could be inspired of. So we had to solve all these little structural details ourselves. So we did this by looking at, say, a critical point, which is this node here that connects the legs to this ring and to the origami vessel, and then we prototyped that. So we 3D printed in scale and with the hinges, tested that we could add these blocks. So this block, now it's 3D printed, but in Greenland, of course, it was made of aluminium. This block is added to lock the structure once it's deployed, but also to seal seal the gap between the rubber and the ring. And it has to fold as well, so that's another dimension of complexity. So you need to have a very specific length for this rubber so it doesn't interfere with this pinch point. Another approach we had to take, because it's an extreme environment and there's very little data on the actual conditions at the site we were at. So we had to take a conservative approach to every design or structural design part. So this was the design suggestion that one of the mechanical engineers we were talking with suggested, and he called it heavy duty. And it's very telling of our approach for this structural design. You see, it's a solid piece of aluminium milled out. It's 60 by 100 millimeters, and it has probably around 10 safety factors above what we're actually expecting to meet. But there's no reason to be careful when you're in a place like that. Here's some prototypes of the insulation, which was added after the deployment. It's a flexible insulation with high safety standards and low smoke emission. And we, of course, also tested that by freezing it before to see if it would retain its strength and flexibility. FEM simulations were used. Some of you were asking earlier in the desert session about software, and for all the design and the management of the digital files was mostly done in Rhino with Grasshopper, and then these simulations were done in solid modeling software, specifically SolidWorks. So we also managed the fabrication, built everything in-house, both because it's cheaper and we could control the process ourselves. So yeah, just some pictures of the assembly we did, working with a lot of volunteers, including our girlfriends. Mine is standing there lifting the top of the habitat. And then we assembled it in Copenhagen and shipped it to Greenland on a ship, where me and Sepp was left on shore to drag it in to our site ourselves. It weighs, I think like this, it weighs around 800 kilos. And we erected it. Here we met some difficulties. We thought going in that we'd made it really automatic. Everything was like click in place, self-deployable. But we learned that even that was just, wasn't enough for it to be an easy experience in such an extreme environment. One example is the ground anchors that we had to hammer in the ground to secure it from winds, and it might be easy enough to hammer one of these in, but we had, I believe, 19 in order to secure it for the wind. And these manual tasks are probably a factor 10 times more difficult when you have to deal with the wind and the deprivation and the fatigue of being there. It was unbelievable how much more difficult it was than we anticipated. Actually, you have a few hours a day where you can actually work hard on these things. So yes.
Yeah, so we are almost finished. I'll just take 3 minutes, or 2 minutes, but we had calculated that it would take us, I believe, 7 days to set up the camp and the habitat and hammer in the ground anchors. But hammering in the ground anchors alone took us 2 people, I believe, 8 or 9 days, 10 hours a day hammering in the cold. And it was insane, and I'm happy I'm never ever going to have to do that again. All right, very briefly, other projects that we're doing right now. So we just finished printing the Sommer, the largest concrete house in Scandinavia. Should look something like that. The habitat itself is just opened last Friday, 1 week ago, at an exhibition at the Danish Architecture Center in Denmark. So we flew back to Greenland this summer, picked up the habitat, shipped it back to Denmark, and unfolded it in this exhibition area. So you can come and see the habitat and step inside the 4.5 square meters And it is very claustrophobic, and I don't have to spend, I think we have spent enough time in there, us too, but I think it's interesting for people to experience. There's a lot of the things we could not talk about today behind the scenes. How did we do this? What was our design process? Our next habitat is another simulated moon habitat that is being developed for a client in Switzerland. The habitat is going to be used for education and research, and it is based on a lot of the learnings that we made in Greenland and a lot of the improvements. It's not an unfolding habitat, that's the biggest change. It is a static habitat. A lot has happened in rocket innovation in the last 3 years while we came up with the idea for Lunac, but a lot of the interior is organized like we did Lunac. Oh yeah, and it's I guess we can skip that. Yeah, it looks something like this. It's a pretty large structure. That's it. Thank you so much for spending the time to listen to us.
Yes, and I believe we'll do a little panel discussion now.
Thank you so much. So we're not going to have a lot of time for discussion, but of course you're welcome to stay with us till the end when you can, many of these questions will be very relevant. So I'd like to start with a question which is kind of, I find it quite difficult personally to address myself, is how do you balance your wish for traveling and for exploring with also wish to protect the environment? Polly mentioned in your presentation, you talked a bit about the nomadic existence and how it's possible not to actually travel, but still have an amazing experience. I just wanted to ask you, you obviously travel a lot, and how does that kind of reconcile?
So maybe I'll just say that the nomadic reference is really building on what Rosie Brydotti's philosophy is. So it's a way of critiquing a certain idea of the human in a kind of modernist Cartesian sense. So she points out that it doesn't really relate to actual nomads and actual nomadic practice. It's a kind of philosophical, theoretical way of deconstructing notions of the human. So it's really within that kind of context of trying to think in a kind of post-human way. So it's not making a clear statement about staying at home or not traveling. I think it's just about bringing into these conversations about, investigations of these fascinating projects like yours with Saga, about building in these environments, about aspiring to go to planet Mars. Kind of moderating that with consideration of what kind of human that is that we're imagining there being, what kind of relations, ecological relations we are fitting into that. It doesn't necessarily mean that you're going to be these kind of investigations into extreme environments don't necessarily mean that you're going to be unecological, but they don't necessarily mean that you're going to be having a kind of ecological and sustainable frame of mind when you approach them like that.
And Hugh, how much do you travel? You must visit your sites, which are obviously as far as you can travel on Earth. So how often do you do that, and how do you reconcile with the concerns about the environment?
I haven't been anywhere for the last 2 years, so it's been very easy. But I agree. It does angst me, and I guess one of the things probably we've learned a lot about over the last two years is that potentially we don't need to travel so much, and the impacts of it are so significant. We should constantly challenge why we are doing it. But on the other hand, of course, we learn so much by traveling. So I do find it, a kind of challenging thing to come to grips with, and it's one of the challenges that besets Antarctic research generally. that there's an enormous amount of travel both to and from Antarctica, but also in between the programs as well to exchange information and so on. I think there's a danger that you try to justify it by the benefits of the research that is carried out as a consequence. But in reality, that is a form of sort of, self-justification, isn't it? I think it's something we have to question all the time. Within the British Antarctic Survey at the moment, they challenge every journey that they make. They question every journey and they look at the benefits that it will bring. And I guess that's something that we're all going to have to do. I haven't got an answer which makes us all feel good, because actually I feel really bad about it. And I think that it's something that we're all kind of probably increasingly feel bad and challenge ourselves about it. But if we don't do it, then we won't see I just loved that last talk by Carl. Honestly, that's just made my weekend. I thought it was totally awesome. But nonetheless, if we don't travel, we can't do that kind of experimentation. And if we don't do that kind of experimentation, we stand no chance as a race. So, we just have to balance these things, don't we? I have no answer, sorry.
Yeah, please.
Obviously, we wouldn't have been able to travel in a sustainable way to northern Greenland. It would just not have been possible. And during the dark periods, so there was a lot of good, and also what you said, Hugh, there's a lot of good things that comes out of these kind of things. Obviously, we were studying how to have a very resource efficient way of living. We didn't take showers. We basically, our water consumption, we had a one-to-one intuitive understanding of how much water we were actually using, because every day we had to go out with an ice pick and chop off a chunk of ice to melt it into water. And in the summer periods, we could run on mostly solar panel or solar power. But obviously then come the dark period, then we had to use generators. So there wasn't a way to do I don't think we could have done our expedition more sustainably than we did. I just don't think it's possible as of right now.
Please, can I just ask you both a question? Were you for those 3 months, did you only live with each other in that period? And did you see anybody else?
No.
Just me and Seb and the Arctic.
and look, you're still sitting next to each other now. I think that's amazing.
It really gives me a lot of hope for future space travel, the fact that...
doesn't it? It's amazing.
And we also were visited once by a polar bear. But that wasn't it was a safe encounter. Nothing happened, luckily. But I think just one note to that, what amazed at least me was how adaptable humans are. Obviously, it was not a comfortable expedition. Like, a lot of it was hard, but humans adapt, and that was kind of the most. That made me feel very comfortable about the future of space travel and claustrophobia and cabin fever and isolation and all of these things.
Because one of the challenges we have in our projects, because obviously they're completely different to yours because they're big and a lot of money goes into them, and that you run the risk sometimes of them becoming too comfortable and people become unaware of the environment that they're living in. And you can get some people and they won't go outside for days and days on end. It's unfair to pick on a chef, but you can be a chef and your job is inside and your food stores are all inside, and you never need to go outdoors, and you as a result become almost unaware of the extreme environment outside, and that can be dangerous if something goes wrong.
Well, we experienced something very similar. We in the end, at least I experienced a lot of apathy. In the end, you're just looking forward to getting home. You're tired, you're exhausted, and you don't get that much excitement out of things anymore. And going outside was we changed. So one day I would go outside, and the next day Carl would go outside and do the chores and chop the ice and turn on the generators. But in the end, when it was my turn to go outside, I would almost be too lazy to do it, because you are you just get like an animal in a zoo. You just get too lazy to move in then. And but then every time you went outside, it would always be a refreshing and very healthy experience. And I tried to focus on that. But I think with architecture, you can kind of force people to have a stimulating lifestyle. Yeah.
Can I add something?
I think this mic works.
I just want to kind of comment on how hard you made it to feel interesting within the space. And Hugh, also, you've made a lot of references about really thinking about how to create the community or a kind of sociability within the space, which I think connects also with comments in the desert section as well about how important it was building relationships to make those structures work. So it seems like a really interesting thread through this about the importance of relationships and social bonds. Beyond really fascinating conversations about what material innovations can supply, it has to be part of a kind of human social cooperation.
Yes.
And so interesting as well, this is nothing new. There must be, I guess, a really interesting comparison that can be done between, the huts of Shackleton, Scott, Borchgrevink, and Amundsen, and seeing the differences between those huts.
Oh, Hugh, what did you say?
Oh, sorry. I was just saying, this is not kind of like a new problem. This is something that goes to the very core as well of like the great explorers that Polly was talking to us about. And there are significant differences between the environments within, for example, the Hut Point hut and Shackleton's hut, for example. You could imagine living in, one you could imagine instantly turning your back on, and it's sort of, that kind of whole concept of comfort, community, security, the sense of being cocooned is really important to people's kind of well-being. And, we could see it in your Greenland pod. I could easily imagine how you could end up just becoming so comfortable in it. It just every surface looked so comfortable.
I'm happy you say that.
Hell is other people in the end, isn't it? Like who you end up having to
Yeah. There's only so much you can do with architecture, but the person that you're with is like probably 80% of the well-being you have there. And also the people that you miss at home is 80% of at least what I felt difficult from being there. And there's no easy way of solving that.
Yeah, you mentioned something about it's not necessary for survival, but how certain features are very important. So could you expand a bit on that? You talked about windows, and you talked about, because we know that these issues always cause problems, and that usually space stations have tiny windows. So how do we build and make architecture which is not just for surviving, but it's actually much more fulfilling?
Well, so the first thing that's pretty interesting is, so we use space architecture as kind of like a magnifying glass to find solutions for problems. They are much more easy to find and see in space or extreme environments, but some of the solutions might also solve problems here in everyday life on Earth as well. So, for example, I think we spend about 93% of our time inside during a day. So it's not like, even though we were in Greenland, we spend a lot of our time inside, but still in Denmark, in Copenhagen, where
people spend 90%.
Yeah, exactly. So a lot of the benefits of what we are developing for space would actually benefit everyday people as well. And more specifically, what we try to do is actually design as little as possible. And that sounds a little bit cliche, but I actually mean it when I say it, that we try to steal as much from evolution and nature as possible. For example, the lighting panels, we one-to-one stole the spectrum of light from the outside, from the sky outside in Denmark, right? So we just stole that the rhythm and the timing and the spectrum of light from the sky, and then put it into the habitat. So it's more stealing than designing, I think. Yeah.
And you mentioned that there's no planting in your designs, but I recall you did have some planting in Monarch. Is that correct? Can you tell us a bit about that?
Yeah, so not exactly living plants, but we did bring an experimental bioreactor using algae, so an algae reactor that we had running. And it's one of the technologies that are being looked into in space travel because it can work as a biological life support system. But what we were also interested in was the sort of sensorial aspect of being close to another organism, even though it's just a million little microscopic cells. There's something about just knowing the fact that you have life with you and it's shining green through that aquarium and you can hear the bubbles. Mm-hmm. So even though you can't really bring a lot of indoor plants, so it's hard, then just having that is
it reminds me that Wilson tried to grow vegetables, salad leaves to supplement their diet. It didn't work out very well. He tried to grow them in the Discovery ship, up near the kind of roof space. And he talks about that in his diary. It didn't work out.
It was, I also want to disclose that it was extremely hard to keep the algae alive under those circumstances. Like, the water, we could not keep the water clean enough, and the temperature variation was too high. Like, then it was too cold, and so it was really hard to keep alive.
It's interesting that at the South Pole Station, where they have a hydroponics installation, it's one of the most successful hydroponic installations in the Antarctic. And there it's so popular that they now have to have a booking system. And so people book half-hour slots, and then they go into the hydroponics and they're allowed to sit there for half an hour and just read their book, because it's really high levels of humidity, really nice, strong, intense lighting, and has a beautiful smell about it. And so it's just just demonstrates three of the key sensory deprivations that you experience in the Antarctic, but that people would also experience in space, and how important these kind of, nature is in helping to counteract that.
100%, yeah.
So unfortunately, we have to end this discussion, but please do stay till the end when we'll have at the end of the outer space presentations, when we'll have, I'm sure, some similar issues and questions to discuss. Thank you. Thank you.
Thank you.
Thank you.
Thank you all. So as Norma mentioned, we'll try to leave some time at the end for overall discussion and maybe go a bit beyond the schedule for those who are interested to continue the conversation. We will be moving shortly to the next session. Before we do that, I just want to say thank you to our event sponsors. Icon 3D Printing out of Austin sponsored the event, as well as Walter P. Moore out of Los Angeles. And this was very helpful to the visiting school and the event today.
Hi, good morning, good afternoon, good evening, wherever people are following. It's been quite a day already. We did deserts, we did underwater, we did polar of extreme environments. So where can we go next? And there's even more extreme, well, of course, space, I think. Space, high levels of radiation, huge temperature differences, vacuum, microgravity or partial gravity. It can't get more extreme. Now, I think it's an exciting time to be involved in space, particularly because of it's not the field anymore for just agencies. There's lots of private companies, and we have really commercialization of space. It's not really new, commercialization of space. It happened over the last few decades, I think. But what is new is really commercialization of human space exploration. So that is something that's been happening this decade and will continue to happen. So it's that kind of human aspect that I thought was really important. And when I was asked to put the session together, I really thought hard of, can I get people from a creative background that look at really the human aspect of space exploration? And I wanted to get people from different backgrounds as well. So I've invited an architect, a designer, and an artist. First one will be Melody Assar, architect. Second one will be Anna Talvi, who is a designer. And the third one will be Michael Najar, an artist. I'll introduce the last two in a minute, but let me just introduce Melody first. Melody is an architect, technologist, and researcher. She's the head of building design and performance at Icon. Now, Icon, the sponsor for today as well, and Icon is a company that is taking large-scale 3D printing and seeing if they can really commercialize that. So I think it's a really exciting thing to push. They're pushing it on Earth and also in space. Melody also teaches undergraduate and graduate topic studies at Art Center College of Design. Previously, Melody was part of NASA. She was a senior research associate with the Human Systems Integration Division. And she was also the co-founder of Space Exploration Architecture, Search Plus. Now, Melody has a really impressive portfolio of space habitat work, both in lunar, Mars, and orbit, lower Earth orbit. So I couldn't think of anybody better to come and ask and speak about the space habitats in extreme environments. And I also think Melody is one of these space architects, new generation of space architects that believes, I think space is not there for humans to survive, but really to thrive and to really make space into really interesting habitats in the future. Melody, over to you. Thank you so much for being part of this.
Thank you, Xavier. Thank you for the introduction. That was very kind. And thank you to Case as well for the invitation to come and speak with you all today. It's a pleasure and it's an honor to be here. Allow me just a minute to share my screen. Okay, can everyone see that?
Perfect.
Yeah, great.
Excellent. All right, thanks so much. I'll try and go fast. I have quite a bit to go through, but I'm really excited to be speaking with the AA and everyone joining us from all over the world. I'm speaking to you from Austin, Texas, which is where Icon is based. Today, I'm going to tell you a little bit about my trajectory into space architecture. As Xavier mentioned, I have a pretty mixed background. I started out in industrial design. I transitioned into architecture. And then I, from there, transitioned again into human factors and human computer interaction research at NASA. But the most, let's say, formative space architecture projects that I've been involved in that have led towards my trajectory to Icon have been a result of the 3D printed habitat competition. So I'll tell you a little bit about those projects today, as well as some of the more active, the two active projects that we have going on at Icon. So to start out, the ISS is essentially the one and only and prime example representing the state of the art for long-term human habitation in space. When I teach, I typically show this image and my students look at this photo of, this representing the state of the art for human habitation in space. And the first thing that comes to their mind is, why exactly does it look this way? And the truth is that the ISS has been designed, but not necessarily for the same value system that we might bring as designers and architects. The truth is that the ISS is a machine, and very often in architecture, we might refer to a machine aesthetic. There's nothing aesthetic here. It's truly about living inside of a functional machine that regulates temperature, pressure, and that remediates and provides, and then that provides remediation for water and air and waste as well. And that's for good reason. These systems are the ones that are keeping people alive on the inside. The vessel and the vehicle, which is the ISS, is essentially providing temperate breathing and interior environment that the astronauts need. And that happens through life support systems, which is the mechanical system that is maintaining air, water, and waste remediation and monitoring things like temperature and pressure, as I mentioned. And so humans are part of this mechanical network, which is a closed loop system that is keeping them alive. It's not a machine aesthetic. It is truly being at the intersection of what it means to be inside of a machine. And that always fascinated me. I always knew I would be working at the intersection of design and technology, but I find space architecture and I find designing for space so interesting because we really have an opportunity to put people at the center of what it means to provide technological solutions that can introduce environments in extreme, that can introduce solutions in extreme environments. In typical systems engineering workflows, we have a network of subsystems that come together to inform mission design. And what's notable about this diagram in particular is that we have subsystems like navigation and controls, propulsion, power, communications, etc. And the human is nowhere to be found. And so most of the human-centered design paradigms that have emerged have been very recent when it comes to human exploration and thinking about a long-term human presence in space. So where I see a real opportunity for designers and for architects is to work at the intersection of engineering constraints and requirements, as well as human factors-driven design innovation. I believe that there is a way to address both value systems through design and introduce solutions that can actually speak to both areas. And I think that the most compelling projects tend to do a little bit of both and speak to both domains. So again, here's a general project timeline. I'd like to start telling you a little bit about the work that I was involved in with the 3D printed habitat competition, which was a multi-phase challenge that started in 2015. It involved both design levels as well as construction prototyping levels. And the really interesting thing, so there's the title page for the competition and us winning the first time in design and then the second time in design. The really interesting thing about the 3D printed habitat competition and the projects that we were involved in the 3 phases that it was run was not so much the solutions that they introduced, but actually the number of, I would call it spin-off projects that resulted because of these proposals. So typically speaking, robotic construction lives and is prototyped and happens within a research context that is confined to a lab. The thing that's unique about ICON is that, as Xavier mentioned, we're looking to commercialize 3D printing and develop accessible, dignified solutions to the housing market at large at multiple price points using automated construction. And what the eventual application that we have in mind is for space. So we're working at the intersection of both construction on Earth and construction in space. In regards to the spin-off projects, we didn't really anticipate that the work would evolve in the way that it did. But as soon as these proposals and projects were sort of introduced to the public and introduced within the competition, they generated a great amount of interest and spawned new ideas for new prototyping And then eventually the scale of those projects got bigger and bigger and bigger. And that's one thing I hope will resonate with you as I go through some of these project examples. So the first prize winner in the phase 1 competition that we submitted to was Mars Icehouse. This was a collaboration between Clouds AEO and Search Plus. We introduced a 3D printed ice shell on the interior of a pressurized inflatable enclosure, and introduced a redundant shell on the interior that basically encapsulated a vertically oriented lander, and all of the programs would basically center around that. Traditional typologies for space architecture, some of them look at going underground for the sake of protecting the crew against radiation, galactic cosmic rays, and solar particle events. And then others that are above the surface typically employ what are known as Class 1 or Class 2 space architecture types. So hard shell pre-integrated modules or Class 2 deployable inflatable modules. In our case, we decided to take a Class 2 deployable inflatable module and 3D print on the inside of that form. The reason why we chose water ice as a building construction material is that materials that are hydrogen rich tend to be most protective and tend to attenuate against radiation most successfully. And so it was a clear, in a long-term mission where we want to be creating a sustainable presence on Mars, we knew that mining for water would be a central part of that mission. So we wanted to leverage that as a means of actually using that water for the sake of protecting the astronauts in a means that would be more protective compared with regolith, which is Martian dirt, or aluminum. Here's a view of the award room of Mars Icehouse. We imagined a vision window that could look out to the landscape of Mars. And in later stages, we're able to prototype that to a certain extent. And we also introduced a vertically oriented hydroponic garden that would cascade down from the lander that would be launched from Earth. At the time, we didn't really plan much or intend to do much technology development with this proposal because it was simply a competition entry, right? But we imagined that there would be we imagined two concepts for how robotic deposition would happen. One would be a sintering robot on the outside of the habitat, and the other one would be ice printing robot on the inside. We collaborated with McGill to put together these initial ice prototypes. This is using a binding material, but essentially left the project as is and didn't really anticipate much would come from it until we were connected via Centennial Challenges to a principal investigator at NASA Langley who was interested in moving the concept forward. This time it was not a 3D printed habitat, but instead an inflatable that was filled and frozen with water ice. The program was very similar for this habitat in that it was intended for a crew of 4 to stay on the surface of Mars for 1 year. And over the course of 2 years, we worked with the group at NASA Langley to come up with the material system for the habitat and to do some preliminary prototyping on what that material system is and how it would behave through a freeze-thaw cycle. So here's the very basic program that we put together, showing vertically oriented ice cells, as well as a functional program for a crew of 4. So crew quarters, hygiene units, wardroom, and some other areas. We were able to get some funding to do some very basic tests within a vacuum chamber, just to look at the kind of grain quality that we could get when freezing ice within Tedlar bags. And through SEM imaging, we were actually able to validate that we could achieve the translucency that we were interested in for the ice shells, but also that the ice shells in that vertical orientation could be self-supporting. And this was some additional prototyping that was done at Langley. with the Tedlar bags as well, using these like plastic fittings and metal fittings at the top. These underwent freeze-thaw cycles until they failed. So basically they were they were frozen, thawed, and then we were able to observe different types of failure with these Tedlar plastic bags. And this was enough for us to submit to the Materials and Space Science Experiment, MISSE. And because of this project, we were able to send some samples up to space station to be tested for a short period. The competition, the 3D printed habitat competition had, as I mentioned, multiple phases, and each phase had I would say, a different value system that was introduced for the materials that were encouraged to be explored for these for the designs. We actually submitted again within phase 3 for a different proposal called Mars X House, and won first prize again. And in this case, we introduced a regolith-based sulfur concrete that also had an exterior egress tunnel wrapping around the habitat. The general shape is a hyperboloid. And similar to the other proposal, it was intended for a crew of 4 to live on the surface of Mars for a single year. We imagined that the interior of the habitat would be made out of high-density polyethylene, and that there would be a deployable mechanical core launched from Earth that could also contain and house all of the echoliths and other hardware that would be necessary for outfitting the habitat. Here's a view of one of the crew quarters, the wardroom at the top of the habitat. And then here's a quick construction sequence that we created showing the telescoping mechanical core, the high density polyethylene being printed first, that's the white material, the windows being emplaced over the course of that print, the airlocks also being emplaced over the course of that print. And then after this is done, the sulfur concrete, the regolith-based material being printed as well. Okay, and that brings us to the present day with ICON. ICON was also identified as a finalist within the 3D printed habitat challenge. And as a result of this, I was introduced to ICON via the NASA Marshall team. I'll tell you about it in just a second. And we kicked off together. First, I was a consultant with ICON via search. And then more recently, having joined ICON as a full-time director of building design, we were able to work on the CHAPEA analog together and future work on Project Olympus. So CHAPEA stands for the Crew Health and Performance Exploration Analog. This is a project that we've been working on for the last almost 2 years, which is essentially an analog mission that is being planned at the Johnson Space Center for next year, where four volunteer crew members are going to be living in this structure, and as part of research evaluating what long duration missions might be like on the surface of Mars. We brought on Bjarke Ingels Group to help with the design of this habitat, and it's roughly a 1,700 square foot structure that is contained within another building at Johnson Space Center. It's funny because on the opposite end of this building, there's another analog habitat called Hera, and Hera runs 45-day missions. And so constructing that while Hera has been operational is a challenge. They want us to be really, really quiet. For the printer, that's not really much of an issue because the printer is pretty quiet, but I mean, we also have like general construction that happens on the interior as well, which I'll show you some pictures of that in just a second. So here's a simulation showing Hera in the background and then our Vulkan printer printing the wall system of the habitat. In this case, we also 3D printed the roof structure. I'll show that in just a second. And then installed the roof on the top of the walls. But the general project goals for CHAPEA are to look and evaluate at what a functional food supply system would be for humans on Mars. And what that means is that there's going to be a hydroponic and aquaponic system, aeroponic system that's going to be implemented within the habitat. And the researchers want to identify if that's going to be sufficient for nutritional purposes for the crew for the long term, and also whether the consumables, the packaged food that's brought with them when they close the door of the habitat is actually sufficient for nutritional purpose as well. And so crew health, performance, crew cohesion is going to be evaluated over the course of this year-long mission inside of the habitat. We were given requirements by NASA for designing the habitat itself. They wanted to maximize the footprint of the analog, understandably, because it's really not that much space for 4 people. But it was truly a collaboration between ourselves and NASA to come up with the layout and the program. But the requirements similar to the competition were given by NASA in this case. So the floor plan that we ended up with introduces a gradient from private to public in that each crew has an individual crew quarter. There are restrooms that are specific to the private, I would call it private crew quarters areas. We have food growth areas, which are the aeroponics, recreation, food prep and kitchen area, fitness room, a medical treatment room, as well as a workstation. There's an additional restroom introduced in the work area because there was an ongoing research question by the Human Habitability Division as to whether having an additional restroom near the airlock would actually be of benefit to the crew. So they're not really sure. Because when the crew is out doing extravehicular stuff, they have to hold it in. They can't go to the bathroom, right? So here's a rendering of what was proposed as the interior of the workstation. It's been a challenge working with NASA to outfit the habitat to look like you see here, but this was the vision that was introduced initially. And here are some in-progress shots of what the habitat looks like today. We have a few weeks to go to finish construction on the interior, but you can see these beautiful Artemida ring lights that have been installed. And as I mentioned a little bit earlier, the roof is actually 3D printed in this case. We were working with several constraints. One of them in particular was about keeping the overall building, keeping the overall weight of the building up to within a certain limit. Because they didn't want to destroy or rebuild the foundation within the current building. So this impacted the design, but ultimately we ended up 3D printing the roof in panels that were then installed using the overhead crane at Johnson Space Center. So here we have the crane lifting and lowering the pieces and putting them into place. And there's also a sandbox that's going to be that has been created and that's going to be used over the course of the mission next to the analog. The sandbox is intended to simulate extravehicular activity. So when the crew leaves the analog, they will wear some VR glasses and then walk out into this, basically a sandbox, to simulate what it might be like to walk on the regolith on Mars. Okay, and I'm going to end with a quick synopsis of Project Olympus, which is ICON's current work with NASA to realize 3D printing capabilities on the moon. NASA has taken on ICON as their prime contractor for the sake of working on the Moon to Mars Planetary Autonomous Construction Technologies Overview. ICON then collaborated with Search and Bjarke Ingels Group as a result of this to put together some preliminary ideas for what a lunar base might look like. This is a bit of what we call an eye chart, but the important thing to note here is that we're working with with NASA on every phase of construction, starting from excavation to construction and then outfitting of habitats and other types of permanent lunar infrastructure. So we're interested in 2 types of construction for the Olympus system, which is ICON's ICON's construction system for building on the moon. Horizontal construction, which covers anything that's like a road or a landing pad, and vertical construction, which would include anything that's built in layers vertically. So anything ranging from an unpressurized shelter to a habitat. And here are some images of what that might look like in the future. Over the course of a 1-year period, we put together a schematic proposal for plans, essentially a master plan for a lunar base. We started off with landing pad designs and what those might look like, and introduced concepts that would be appropriate for a number of landing systems. And then, of course, started to think about how the icon system might, what the form factor of the icon system might look like, and how that would actually inform the constraints of what's possible to design in architecture. So here's some of the landing pad designs that we came up with. And then the lunar lantern was a habitat concept that we introduced, that introduced a pressurized interior as well as discrete wiffle shield channels on an outer layer. And that was also intended for a crew of 4 to live on the surface of the moon. Here's an image of the icon system printing the lunar lantern, a view of the upper floor, which is the wardroom of the lunar lantern, the work area of the lunar lantern, as well as the crew quarters on the ground level. And with that, I'll just end by mentioning that the conceptual designs, even though they might seem far removed from the technology development that's currently going on to realize 3D printing on the moon, it's actually far from the truth. And so we're currently on track to deploy an initial demonstration mission with the NASA Marshall team as part of the MPACT group to demonstrate a proof of concept using 1 or more material processes. And I really want to emphasize that the architectural and master planning work that was done lended so much to realizing the hardware requirements for this initial demonstration mission. And I look forward to seeing how other, designs and concepts for the moon and Mars inform and actually implicate the decisions that are made when it comes to the hardware requirements and other systems for construction in space. Okay, thank you.
Thank you, Melody. It's so amazing to see how architects and designers can be central in this really technical world of space exploration. Really fantastic. We're going to have questions later, but let me introduce the next speaker, Anna Talvi. I met Anna a few years ago now because we were both part of an exhibition at the Design Museum just before the pandemic hit. And that was called Moving to Mars, an exhibition about Mars, but was focused on design. Now I talked about, having speakers that have humans central. And I think with Anna, humans are very much central to her work, because what she's looking at is looking at what humans, astronauts will wear into extreme environments. What will they wear in the space habitats? Anna is a designer and researcher. She has a background both in tailoring, mathematics, and physics. And currently, she is pursuing a PhD in UCL, the Department School of Architecture, in collaboration and partnership with the European Space Agency. And she's developing a 4-dimensional microgravity-specific astronauts body mapping, and that really would lead to a new generation of a next generation of spacesuits. Anna is also the founder of Microgravity Technologies, a startup developing technology for automated generation of knitting instructions for 4D CNC knitted structures. Anna, thank you so much for being part of this session today. Over to you, please share your screen. You're welcome.
Hi, Xavier. Thank you so much for having me, and thank you for the very lovely instruction. So all panelists, why can't I share? It doesn't allow me to share my screen.
Can you see if there's a...
Yeah, the green button at the bottom.
Yeah, but it tells me... Okay, now I can.
Okay, perfect.
Okay, I think it was disabled. Right.
Yes, we see PDF. Yeah.
Okay, now I hope you can see it.
Hang on. It's coming through, I think. We see the PDF at the moment.
Yes, I am sharing a PDF. Can you see?
Yeah, but it's not full screen. It's not full screen at the moment.
Sharing is paused. Bring your share. I am very sorry. I will resume it.
Showing the PDF, but not full screen. There we go. That's full screen.
Okay, now you can see it.
See snail shell and.
Yes. Okay. Sorry about that.
Go.
Okay, now we are ready to go. Sorry. Thank you. So as Xavier introduced, I am here to tell you a little bit about some of the challenges of designing both the past and the future spacesuits and astronauts' microgravity wear. So from the very first single-cell organisms on planet Earth to the variety of species that have lived here since, our living environment is reflected in the design of our outermost layers. And the natural reprogramming of our outer shells, it makes it possible for living organisms to adapt to the ever-changing environmental conditions. However, the skins of humans, they are not programmed to grow in that is kind of on level with our ambitions to explore and survive, and also environments way beyond our blue protective skin, which is the atmosphere of the Earth. And spacesuits and habitats, they not only need to enable us to survive in space, but also address many of the human aspects that enable us to live and work there. And they must combine, so spacesuits must combine some of the environmental necessities of a habitat into a very thin skin-like envelope around the body, and then mediate between the complexities of both the environment and the body. And going a little bit back in history, the development of spacesuit designs has been evolutionary. So it means there has been no one invention of a spacesuit, because the pressure suits that you see, for example, on the left, and altitude and G suits that were used by the military pilots, they were the direct predecessors of wide range of flight and EVA suits used today, including the Apollo lunar spacesuits. And actually, the story of the development of the lunar suits is a rather intriguing one, because there were kind of very different points of view whether the suit should be engineered or fashioned to the human body. And on one side, the suits followed NASA's way of describing and sustaining people in space through managing all of their inputs and outputs. So on the left, you see the engineering scheme of a suit's life support system, and it's an engineering graph. And actually, in the early days of the lunar spacesuit development, there were several attempts to completely engineer the man to space. And for a long time, the preferred suits were these, what you see on the left, they were hard shell and they were like heavily engineered suits. However, the problem was they didn't work very well with the human bodies. And besides some technical issues, astronauts were not able to properly move and work in them. So the suit that won the NASA contract to land on the moon, it was a soft white one. It was hand sewn on Singer's sewing machines by seamstresses of Playtex. And Playtex is a company that originally made women's bras and underwear. And the A7L that you see on the right, it kind of ended up that the manufacturing of it, while the outer layers followed very strict engineering protocols, the inner layers were based on garment logic. Despite the perspectives of sending humans to Mars and back to the moon in the next decade, it is quite clear that majority of people going to space in the next 20, 30 years will live on the orbit of Earth or on the orbit of the moon or in a spacecraft on the way to another planet. So basically in microgravity. So also my majority of my work focuses on understanding how human bodies work and how to design for them in the microgravity environments. And there are several physiological changes that need to be considered. And the most significant one is bone and muscle loss when living in weightlessness over long periods of time. Because you probably know well that in order to make our bones strong, we need to apply forces on them. So on Earth, there are constant forces due to gravity, but also ones exerted by our muscles, including muscles that we have no control over. Now, in weightlessness, not only is the gravity loading taken away, but also our muscles are completely relaxed. And also our postural muscles are completely relaxed, which means that these involuntary anticipatory mechanisms that counterbalance our voluntary movements, they don't work. So like a simple example of that would be if I would stand up right now and try to do a ninja kick, my anticipatory muscles will activate in several parts of my body so I wouldn't fall over. So I can only focus on the kick. This overall muscle inactivity not only contributes to the bone loss, but it also makes you grow a few centimeters at your lumbar spine. And the best countermeasure to date for musculoskeletal deconditioning is 2 hours approximately exercise daily at the ISS. As you can see, you're strapped down by bungee straps while you run on a treadmill, but that causes other problems, for example, knee and back pain. And it is very likely insufficient for future longer missions. So for a few years now, I have been developing this antagonist exomuscle bodysuit. And it is not directly to gravity load the body from shoulders to your feet, but it's actually to trigger these involuntary anticipatory muscle activations throughout the day, just as all of us do right now, even while you're sitting on a chair. So that those the weight-bearing bone loading would occur more naturally. But if you think if you need to wear something for long periods of time over the day, it is clear that there is a much bigger range of considerations that need to be made. And not just one physiological system, but several. So I will quickly run you through some of the things that happen in microgravity. Also, the cardiovascular system is kind of turned upside down. Especially in the first days in microgravity, the blood moves from your limbs towards your torso and your head. You get quite a puffy face, bigger neck, which contributes to all sorts of other physiological changes. But if we just speak about suits, then you can see that the measurements are very different. Furthermore, you acquire something that is called the neutral body posture, which you see on the right. NASA has, since a long time ago, tried to standardize this, but it turns out it's quite individual specific. And also in that posture, if you observe footage from the ISS, you see that astronauts move by using their hands. Their shoulder joint is very mobile, and lower limbs and torso is quite static and relatively in the same position. Also, there is no convection in microgravity, which means so convection, warm air doesn't raise up. So when you sweat, when you work out, when you sweat, it doesn't evaporate. It creates an aura around your body. So that needs to be considered in the materials used. There are also no washing machines, no showers. The cargo is very limited, so you need to count your number of clean socks you can take with you. And on top of everything, astronauts mainly right now, they need to work there without distractions. And they need to be physically and mentally as comfortable as working on Earth. So seeing the scope of considerations when developing suits, we need to think about biomedicine, biomedical engineering, material science, very basic garment construction. And until now, I have only mentioned considerations for intravehicular suits, but for extravehicular activity, so that's when astronauts go outside the space station or a habitat, the suit also needs to provide all the environmental protection, like pressure, radiation, life support, oxygen and CO2 management, health monitoring, have communications, and so on. And for example, lunar exploration suits, they need a system that repels dust because Moon has no atmosphere. So the lunar dust cell regolith is very sharp and highly abrasive. And no matter what type of suit we talk about, there is a very high number of requirements that need to be addressed through a very thin layer around the body. The problem is that many of these requirements are actually not very well understood. One of them is how the suit and all its technical elements are related to and interact with the human body. In other words, wearability, ergonomics, also sizing and fit. And if I quickly talk through the principle, how fit of spacesuits is approached right now, is you start with the astronaut's body, and the Apollo lunar suits, they were bespoke made for each astronaut. But all the current suits, they come in standardized sizes. And this sizing system is based on anthropometric databases of earthly bodies. And they are taken on standing straight posture. So how the pipeline goes is that from these three-dimensional earthly bodies, average one-dimensional measurements are taken, such as chest circumference, hip circumference, back length, all those. And these one-dimensional measurements are used to draft two-dimensional patterns. So on the left, you see how the Apollo suit patterns look like. And these are cut from two-dimensional textiles. And these two-dimensional textile pieces are put together with all the engineered and all the smart elements, and they're assembled into three-dimensional suits. And these three-dimensional suits are then now having to work on four-dimensional moving bodies. And these four-dimensional moving bodies, they're different from those bodies that the measurements were taken from. And actually, these bodies are also, everyone has a different shape to them. It's not, no one's body fits the standard. They also, as we spoke before, have a different posture. The torso is a bit longer, the legs are a bit skinnier, all these things. And they are constantly moving. And to my mind, with every stage of abstraction moving between these dimensions, the mistake that accumulates is rather big. So I've been looking into other ways to understand and measure astronauts' bodies in a way that can be directly translated into making all the smart wearable elements of spacesuits more wearable and better integrated with the suit, as well as the moving body. So it's a better integrated system as a whole. And I've been looking, for a way, is it possible to quantify this complexity in a simple way? And what I found is that in surgery, there are lines of least expansion that have been long used for making incisions. So if you cut along those lines, the wounds heal faster and you get less scarring. And that was already done in the 50s by Langer and others. But there was really no technology. So they were like manually stretching the skin and looking at wrinkles and kind of intuitively drafting those maps you see on the left. But this idea has been actually used already for a development of a mechanical counterpressure planetary exploration suit that you see on the right. So actually, there is technology to map out a full strain profile. So all the major minor strains, their directions and magnitudes, and it's called digital image correlation. And it's a brilliant tool, and it's very precise. And what you get are these four-dimensional strain maps of the body. And right now, knowingly, a map of the full body doesn't exist, but this is something I am trying to create during my PhD. And what this understanding allows us to do is, for example, if you know this mapping, this 4D mapping at different stages, you can see, for example, the lines that are very stable, so they don't stretch or compress. So these are the lines, like for a spacesuit, where you want to insert all the or very fragile or stiff filaments, such as like conductive wiring or tubes of the liquid cooling garment. And in the same way, you can see exactly the areas with very high strains and then directions of very high strain magnitudes in which you can insert materials that harvest your kinetic energy and turn it into electric energy. And I mean, most importantly, to achieve a optimal four-dimensional fit of the spacesuit that allows our earthly bodies to feel comfortable and protected in space. Now, there actually exists one excellent design that is developed today that can do that. And I've saved the best bit for the last. So this design, it can stand temperature from minus 250 Celsius to plus 150 Celsius. Pressure nearly 6 times you can find at the Mariana Trench, withstand cosmic radiation, vacuum of space. And actually the design of the suit was all done without the help from NASA. And the design is the tardigrade. So there are several things why I think the future human spaceflight and spacesuit design will learn an awful lot from this 1 millimeter long little creature. Because it is a very simple design. It can change between the active and the TUN state, and it's completely seamless, like literally seamless. So tardigrades are covered with the cuticle, and as you can see, unlike other bugs who also have cuticle shells, tardigrades have no joints, and all of it is beautiful one-piece seamless design. And there are several reasons why I don't think seams in suits are a good idea. Whether they are sewn, bonded, welded, or linked, they are a hazard because they can break. Manufacturing is never 100% perfect. Seams also change the properties of the material around the seam and affects the overall behavior of the material. They're bulky, and they imply that the whole is an assembly of several smaller pieces, which I discussed earlier. But actually, textiles, they don't need to be flat, and they don't need to have orthogonal mechanical properties. Textile hardware, such as the CNC knitting machines, they are highly advanced, and they are capable of knitting very, very complex 3D textiles with locally differentiated structures and variety of combinations of materials, and like anything from natural and common, such as wool and cotton, to metals, shape memory materials, carbon fiber, you name it. However, working with this software for these machines is a quite painful process. It's very slow, and the programming is highly limiting. A parallel I can give is if in architecture, if Xavier and Melody would design their 3D printed habitats in Microsoft Paint, and they would use red bricks to build those habitats. It is really that bad. So over the last few years, I've been developing a technology for automated generation of knit instructions for CNC machines for knitted textiles that are parametrically designed. So basically, I want to use these very powerful textile machines as 4D printers. So that I can program a certain mechanical behavior into a textile through the micro and meso level structure of the material, and across complex 3D forms. And in December, we just successfully managed to make our first sample, which is knowingly the first parametrically designed 4D textile. And we are very excited as this technology enables us to program the required behavior directly into the suit, into a single layer and in a single manufacturing process. And it really optimizes how these more sensitive elements, such as conductive filaments and artificial muscles, are integrated into the structure and with the body. And hopefully this technology in the future will not only need the antagonist exomuscle bodysuit, but also various layers and bits of several suits. To sum up, arguably, the weakest link when we think about going to Mars is the only thing we did not design for this Mars mission. It's the human. Because human skins evolved for living on Earth. And if we want to thrive in space, I think we need to learn a bit more from tardigrades. Thank you very much.
Thank you so much, Anna. That was fantastic. Okay, we'll do questions later. So we're up to the last speaker of today, which is Michael Najjar. I met Michael quite a few years ago now, when I was still working at Foster & Partners, and I was asked to show Michael around to the studio. And very quickly, it was apparent that we both had an amazing fascination and passion for space and technology. So we stayed in touch for up till now, and I'm really glad for Michael to be here now, just for the kind of different audience as well. Now, Michael is an artist. He has his practice in Berlin, where he fuses art, science, technology into visions of future social structures, emerging on the impact of cutting-edge technology. 2011, he has been working on the topic of space exploration. His Outer Space work series deals with the latest developments in space exploration and the way they will shape our future life on Earth, in Earth's near orbit or on other planets. Now, the reason why I actually asked Michael to come and be part of this session, because I think the human is also very central to his work. And mainly because of himself. He actually puts himself through these extreme environments. He has been on astronaut training, and I think he's also signed up to be one of the first artists to go to space in one of the Virgin Galactic missions, which is hopefully happening soon. Michael, thank you so much for being here. I'm also aware that you're doing this talk from your holiday, so I'm really a massive thank you to really doing this for us. Over to you.
Thank you very much, Xavier, for the introduction. I'm very happy to participate at this fantastic symposium. So it's really an honor to be part of this. And I prepared a little presentation for you guys regarding my work, basically about the Outer Space series. So I will try also here to share my screen. Let's see if that works. So desktop 1. Okay, that's not working. Why is that not working? I will try again. So desktop 1. What are you seeing? It says I have to activate the system.
Oh, I think that's on the device settings on your computer, actually.
Yeah, it tells me that I have to go to the system setups. Let me see if I can do something here. Just 1 second. That looks quite good. So let's see here. Okay. So is that working now? That looks good.
Something's happening. We see a screen now, yes.
So you see the screen now?
You see the screen, not full screen, but we see...
screen now?
Not full yet. Now it's full screen, yes.
Is it full screen?
It's full screen now, yeah.
Okay. So, okay, fine. So you see the title of the presentation, yeah, outer space. Is that what you see now, full screen?
Correct, yes.
Okay, so let's go. As you already introduced a little bit, I'm working since the past 10 years now on the topic of outer space. So that became really a huge fascination for my artistic work. And over the time, over the past decade, I have created a body of work which comprises more than 70 artworks. And I have chosen a couple of these artworks for today's presentation, which focus a bit on the topic of extreme environments. So let's see. I think at the moment we are really facing an exciting transition process in space exploration. The development of the new space sector is generating really a unique industrial and cultural evolution. And this will have a strong impact on humanity's future. So my outer space work series deals with the latest developments in space exploration and the way they will shape our future life on Earth and Earth near orbit and on other planets. Innovative architecture, engineering, and construction for extreme and hostile environments play a vital role in humanity's 21st century journey into our solar system. So as you already mentioned, in 2012, I signed up with Virgin Galactic to fly with their spaceship into space, because usually my artwork is based on a hands-on approach. So my own physical experience is always very, very important and is a base for my artistic creation. So when I started to work on the topic of space exploration, I said, I have to fly into space myself to have this unique experience. And that's the reason why I signed up with Richard Branson, Virgin Galactic. And so hopefully soon they will fly their customers into space. What I did when I signed up with Virgin Galactic, I said, okay, if you go to space, you have to train for space and you have to train in extreme environments. So I approached the Russians and the Russian Space Agency and their training center and asked them to allow me to train with the cosmonauts and astronauts there and have this experience, what it means to prepare your human body for the extreme environment of outer space. So I did a couple of extreme experiences there. Here you see me flying in a zero-G flight, where you learn how to move in microgravity, what is really an amazing, but also amazing experience, but also is very difficult to cope with, to move your body in zero-G. I did a spacewalk, underwater spacewalk training where I was put in an EVA spacesuit and I'd spent 2 hours underwater training on a mock-up of the one-to-one mock-up of the International Space Station. I flew with a MiG-29 jet fighter into the stratosphere, up to 20,000 meters, to learn how to cope with extreme G-forces. So the G-forces went from -1 to +7, and that was really a very, very heavy and strong experience for the body and the brain to cope with. But it's several centrifuge training. Here you see me in a centrifuge training with the German Space Center. That's a short arm centrifuge, but it spins you around. Also, you have to cope with the extreme G-forces. I did a halo jump. I jumped out of an airplane in an altitude of 10,000 meters with 3 cameramen around me, and I had 2 minutes of free fall. So I was heading with 300 kilometers per hour, 2 minutes towards the surface of the Earth, and that's the purest and most dense and most powerful way really to sense the force of gravity when your body is just falling down, falling down, falling down. So based on all these physical experience, I have created a bunch of artworks. As mentioned, I have done a selection from the past 10 years, which focus a little bit on the idea of extreme environments. Before I come to that, I give you a little idea how the artworks look in exhibitions. Usually I work with very large scale formats. And here you see an installation view of a museum show in Germany that we did recently. And here we start with the very first artwork, which is entitled Liquid Gravity. And liquid gravity is really, has become over the time, it's from 2013 and became an iconic image, iconic artwork of the series, because it comprises a lot of very important details, components regarding the topic of outer space, but also the work or how I do my artistic practice. So the astronaut here, the figure that you see, is in an EVA suit. It's floating in 0G or microgravity. It looks like an industrial environment. On the porthole, you see the Earth. So this relates, or this creates a relationship between the human body and this planet, because we all come from this planet, and this astronaut obviously comes from that planet, but now is floating in a different space away from planet Earth. And the astronaut floats in water. So it's in a huge, the photograph is taken in a huge hydro lab in 12 meters depth. And the water, the element of water, you can only see through the little bubbles that are coming out of the spacesuit on the top of the helmet. The water also is reflected in planet Earth, of course, because most of our planet is covered by water, and water is the element of life. So there are a lot of aspects which are combined to reveal the idea what it means to leave our planet, to be in an artificial environment, to be on a space station. And also it indicates my artistic practice, because I'm very much interested in the creation of reality, or let's say in the construction of reality, not in showing reality. It's about construction of reality. And this space here, as the architecture space, looks all very real and is based on real footage, but it's an artificial construction. So the image is based on my spacewalk training, which I did underwater, and it's actually me inside that spacesuit. And I was 2 hours underwater for that exercise, for that spacewalk. And that was really a unique experience in my life, I have to say. So many years later, I did a new version of that image, and this one is called Sky Space One, and it dedicates more to the younger generation who will in future time be in space, who will travel to space, will live on space stations. And as you can see, here's a young boy floating in an artificial space, but it's no longer the Earth. You see Mars here to the porthole. And in fact, it's my own son when he was 7 years old. So I used him as a model to create this artwork. So when I will start with, when we will fly with Virgin Galactic to space, we need a spaceport, of course, to start. And what you see here is Spaceport America. And the artwork also is entitled Spaceport. And that's a spaceport, a building, which is also in an extreme environment because it's built in the desert of New Mexico. It's a building designed by Norman Foster, and what I liked really about the building, the idea is how it merges with the environment. So that's, I think, very unique and different to what we know from spaceports. It's really the idea that it uses local materials and that it reflects the landscape and it really matches with the surrounding. To have a balance and a unity between the architecture structure and the environment. I think this is very unique and it's really a fantastic place. So hopefully soon I will be launching from that place then into space. Launching rockets is always an incredible experience, I have to say. And what you see here is a rocket launch from an Ariane 5 rocket, which I photographed in French Guiana. So this is the European spaceport. And this is really an extreme environment because French Guiana is 100% jungle. It's forest, it's the Amazon forest. All you see is trees and forest, but once a month there comes a rocket out of the jungle and launches satellites into space. So I think it's a very, very specific or special location there, and it's a mind-blowing experience when you see the rockets launching from the forest into space. And also a metaphor for human civilization, for the way we went during the past thousands of years, because our civilization all comes from the forest. Today we are launching from these forests with machines, with rockets, with spaceships, and we venture into space. So a big game changer for the travel, for traveling into space, for bringing payloads or people into space, was of course the invention of reusability. So that was the big deal that SpaceX invented, because with the reusability of the Falcon 9 rocket, everything changed, because the cost for bringing payload up into space dropped down by factor 10. And that really brings us a lot of new possibilities now how we can venture into space. And this is a brand new artwork which I created a couple of weeks ago. And I photographed one of the Falcon 9 stages returning from space and landing on one of these drone ships. And in the background, you see the light trace you see is the actual launch of this rocket. So I photographed the launch, and then a couple of days later, when the rocket returned on the spaceport, I photographed the rocket on the drone ship. The artwork is entitled Down to Earth. Also talking about extreme environments, technological invention, new engineering. A big step forward was the new spacecraft, the new spaceship, the Crew Dragon, which after I think 9 years of no possibility of bringing US astronauts with US spaceships to the International Space Station, with the first launch of the Crew Dragon in March 20, things also changed a lot. And what was so interesting to see, that was a whole new design to what we knew before. Now there was a sleek, white, black design. The buttons were gone. All was now controlled via touch panels. The spacesuit suddenly looked very, very fancy and cool. Not these bulky spacesuits we knew before. Now they were very sleek and yeah, very fashionable. So a whole different design now has entered into space travel, and this artwork is a composite of different pictures related to this very first launch. You see the astronauts, you see the Falcon 9 rocket, you see the design inside the spacecraft, and the two astronauts walking. So a lot of different components are merged together to create this digital collage celebrating the first Crew Dragon trip to the International Space Station. Sometimes things fail, and especially when we talk about technological invention, extreme environments, new overcoming borders, trying new concepts. In 2014, the spaceship of Virgin Galactic, Spaceship 2, crashed during a test flight. So that was really a fatal and very dramatic accident. So one of the two pilots died on that crash. One survived, what was really a miracle. And it was a dramatic event for all of us, because I was supposed to fly with this spaceship one day. So the crash really brought a lot of question up. Is that really the right design? Is it really possible to bring civilians to space with this new technology, with that engineering concept. So a lot of questions raised, and I definitely had to make an artwork based on that accident. So I couldn't go there to photograph the accident site. So what I did, I collected hundreds of several photographs from different photographers, which were on-site press photographers. And then based on their footage, I recreated a very famous painting from German painter Caspar David Friedrich. And there is a famous painting which is called Sea of Ice. And this artwork here is a new interpretation of his painting from the early 19th century, and just created by fragments and parts of wreckage parts of a crashed spaceship. This artwork is entitled Simulacrum, and shows a space simulator in the Netherlands. It's architecturally, it's a very interesting location. It's a space which is built of two cylinders, a vertical and a horizontal cylinder, and this chamber reproduces two very important aspects of outer space. Number one is vacuum, and number two is extremely difference in temperature. So the vacuum chamber here, or the space simulation chamber here, creates 100% vacuum through liquid nitrogen, and also an enormous heat through this mirror and specific light bulbs, and it creates thousands of degrees of heat. And then materials are tested inside this chamber if they will really be able to survive in the harsh conditions of outer space. Another idea of going into space is not using rocket, but using a space elevator. And this is an artwork which is called Ascension, and I created this artwork about 3 years ago. And it's still a very utopian idea, technically not realizable at the moment. But there are companies now working on that. And I really like this idea that a platform on Earth's surface is connected with a large cable, which needs to be 36,000 kilometers long, and then connected to a base station floating in the geostationary orbit. And one day that could become reality, and then we can send up materials, payload, and people along this cable with an elevator up and down to space. Another very, very extreme engineering object is the James Webb Space Telescope. It was a lot in the media in the past weeks because finally it had its launch, and it's now placed at the Lagrange point behind the moon. And I photographed one of the mirrors. I think in 2013, I had the opportunity at NASA to photograph this segment of the mirror. And it's really a fantastic and incredible instrument with the purpose of finding the very first light that the universe emitted after the Big Bang. This artwork is entitled Fast and shows the world's largest infrared telescope. So this is based in China, in middle China, in the mountains. There is this incredible futuristic instrument hidden. The bowl has a diameter of 500 meters. So it's really incredible. It's so large. And the Chinese created this instrument to find extraterrestrial communication signals. So here we have an artwork which is entitled Starlink. And you see different elements here in that picture. Number one, you see a very specific building, and the building is placed in a very extreme environment because it's in 3,000 meters altitude in the Atacama Desert. And this building is the home to the most or the best scientists and astronomers in the world. So they are placed there for several months and they work and study there and do their astronomy work. The problem now is that SpaceX is placing with its Starlink satellite system a grid, a network around our planet based on over 40,000 satellites. And these satellites are have a huge impact on the work of astronomers because they're not only visible with the naked eye, they're also affecting the telescopes of the astronomers, because the clear, starry night sky now is you can say is affected by these light scratches. So there is no longer an untouched night sky. Now technology inscribes itself into the starry night sky. So what you see here, the white lines and scratches, are based on the real picture taken by one of the telescopes in the Atacama Desert. So these are all reflections of Starlink satellites circulating around the Earth. So going to extreme environments also needs the help of robots and machines, of course, also human robots. This is a very interesting machine. The artwork here I have created is entitled Starbot, and it is based on a human robot that NASA built and which is now programmed in Edinburgh at the Center of Robotics. And this is a very, very smart robot which is now trained to work autonomously on the surface of Mars. And I photographed the robot in the laboratory, and the robot has a lot of cameras installed, and it scans the surrounding. It creates a point cloud of the surrounding, and this point cloud helps him to navigate and to do then his work. And so all the little dots you see in the background are based on the data and the images that the robot has taken, which is cameras, and then transferred into point cloud. So this was the an insight of the selection of the artwork I did on the topic of space exploration. But I have to give you a little story now to finish my presentation, because a couple of weeks ago I was at Starbase in South Texas. And this is the place where SpaceX and Elon Musk are building the new starships. So Starbase can be considered, I would say, as the cradle of humanity on the way to Mars. And this is really the most extreme place I have seen over the past time, because what SpaceX is building there is just breathtaking. So the Starship, what you see here behind me, is mounted on that booster, of that heavy booster. And then if these two are stacked together, this is 130 meters high. And the Starship is supposed to transport 100 passengers. And it's really unbelievable. And there is not only one Starship now built, and there's a huge factory, and there are a lot of Starships are built now. So dozens of Starships now are under construction. On the right side here, you see Mechatzilla. So this is an incredible new tower that Elon Musk invented. And the idea is that the tower catches the Starship and also the booster when they're coming back from space. They will not land any longer on ground. They will be catched up in the air and then put back directly on the launch table. And within 1 hour, they will be ready to restart. So it's 100% and fully reusable, and it's really amazing. And when you see all that in real, it's just the sheer size of this is just breathtaking. And it's all under construction now. There's a lot of work going on where they build the factory and the launch pad. It's an incredible energy that you can feel there, and you really feel that this is where now the journey to Mars really starts. And in the next couple of weeks, probably, they will do their first orbital test launch. So this is what you see during the night, and when you look at that, it's so futuristic. It's really out of this world, and this is just the beginning. So if you ever have the chance to go to South Texas, it's really, you have to visit this location. And I will finish my presentation with this image. The spaceport is built in Boca Chica. Boca Chica was a little tiny village, and the spaceport is built around this village. But some of the people living there just refuse to leave, and they say, we stay in our house. And that's unbelievable. So these people now live in the middle of a spaceport. So gigantic rockets are fabricated around them. And so I think it's a very extreme environment to have your home just in the middle of a spaceport which is under constructions. So I'm happy to come to the end with my presentation. For those who are interested in more going a little bit deeper into the outer space series, we just recently published a wonderful new book, which is called Outer Space V2, published by Berlin-based Distanz publishing house. And it has about 300 pages with a lot of fantastic essays from Richard Branson, Elon Musk, and many others, and a lot of behind-the-scenes footage, a lot of artwork. So it's really a cool book. If you're interested, it's of course available on Amazon. So thank you very much for assisting to my presentation. I think I was a little bit over the 20 minutes. I hope that's okay. So
that's okay.
Thank you very much.
Michael, thank you so much. That was absolutely amazing. What a way to end this day. We're not going to end it completely yet, because we're going to have a little bit of panel discussion as well. Mm-hmm. So Anna and Melody, if you're still there, please turn on your camera as well. Thank you. I'll probably have some questions from the audience as well, but I have a few questions myself. And as I organize this session, I can go first. So my first question is really for Melody, and it's a question about, you mentioned early on, you have these early slides where you said, the human factors thing wasn't really part of the question. It was all more about the engineering. Now, of course, now you're part of helping to design this this analog that really looks at the human behavior, of course. You must have had a very different brief from NASA, right? And I'm interested about that, because as architects, I think as what we always love to do is actually question that brief, right? Every brief I've ever had from a client, I've questioned the brief, because I think that's part of the design, really. So I'm intrigued, did you question the brief? And if so, how did you do that?
Oh, yeah, absolutely. It's such a great question, because at the heart of questioning a brief, you want to understand what the requirements are and what they're driving at. Like, what are these assumptions that are going into how we should be making or strategizing our design decisions? So yes, of course, we questioned the brief. We questioned the requirement for the habitat to be rectangular, for the habitat to be limited to 1,700 square feet. And all of this was met with a great deal of, I don't want to say resistance, but a great deal of discussion and debate amongst multiple research groups at NASA. And it was hotly contested. And very frequently what happens is that there's sort of information fatigue when there's so many stakeholders at the table, and people are sort of left in a position where you can't satisfy everyone, and there has to be a decision that's made that fits within budget and within timeline. So we often sort of wonder to ourselves, like as designers, how do more engineering-focused organizations end up with these very normative schemes that don't really present like innovation when it comes to design, or new or cutting-edge or exotic ideas when it comes to design? And that was really the experience, and what I witnessed in working on the chip-year analog myself, is that there were so many people to satisfy and so many stakeholders with such high stakes in what the design actually was, that there wasn't an opportunity for the architect or the designer to stand out amongst them. And so it's a real challenge. It's a real challenge advocating for design. It's a real challenge understanding, like you said, where the requirements derive from and what the intentions are behind the requirements. And it's going to make for a very exciting future, right? It's like how we actually come up with briefs for future habitats and who's going to be steering these decisions moving forward.
Thank you, Malia. I think, it's great. I think we have to be part of that decision, right? Of the brief, not just design, but actually developing these briefs for agencies and also for commercial entities. Talk about commercial entities. I'm going to move to Anna. I was looking at these the new spacesuits for SpaceX, and Michael, you did an art piece on them. And when I looked at them, they're very technical, they probably have certain requirements, but I also noticed and I read up on it, they were actually designed partly by somebody that designs costumes for movies, right? I think I'm correct with that. And so there's a lot of kind of detailing, I think, when I look at them that aren't really, there's a bit of styling that's happening. Let's call it styling, right? And look at your work, Anna, and it's extremely technical. Do you think there will be part of styling in your work? Do you think it's because it's very much engineered? Where do you will allow it in there or not? That's what I'm kind of wondering in your designs.
I get that a lot. People who don't know much about space, and when they come to my exhibitions and everything, they are kind of like, oh, they are like, why is it not silver? My designs, they are kind of more like, they're in between designs and the pieces of engineering. They are all always derived for what is their main purpose. And at the current stage where we are in human spaceflight, astronauts are still, vast majority of time, they're working there. And whenever you listen to an astronaut speaking about their time at the ISS, what they always say is like, they miss home and they want to be comfortable and they want to be working. And if you it's kind of like space fashion wants to always be like spacey, but actually, if you think about it, when you go to space, do you want to feel like an alien or do you want to feel like a human? I think the connection of wanting to be human is much stronger in space. Therefore, you look for familiarity, you look for comfort, you look for actually materials that you are familiar on Earth. Like also my exomuscle that we design with, it's a multiple layers of very technical fibers, but the fiber that we put against the body is a natural one, just for the right feeling of it, so that it doesn't feel alien or unnatural as you need to work and do science there. Definitely, my designs will never be inspired by science fiction. They're always derived from either technology or just working together with people who work in space at the ISS and really trying to understand on a very deep level what they want. And actually in garments, it's always not very straightforward, because how much to people who work in science on Earth, how much do you think they can precisely describe about materials and fit and such things? So the questions, at first you don't get many answers, but along the way you start understanding. But it's definitely about feeling more human and not about fiction.
I like this thing where you said about not being inspired by science fiction, because I think that's a kind of an easy thing to do almost. And I see it, I'm teaching a couple of courses around space architecture at the moment, and it's really hard to kind of drag the students away from the sci-fi ideas that are out there, which, it's very important to really kind of look at what the issues really are and actually design around that, by just getting, inspired by something that hasn't happened and probably will never happen. Michael, I'm going to move to you. I've got a question. Your work is really, although you look at the future, you really use always very real things, reality in your art. It's a collage of real things that are there. I'm kind of looking at the work that you've done over the last 10 years. It was really a journey towards, you booked that ticket 10 years ago. That will now happen. I'm kind of intrigued. What will happen after you've done the flight? Will that then change your work? Will you move in a different direction? What is there another step then, or not? What are you going to do after that?
That I really can't answer now. I mean, when I booked the ticket, of course, I was not aware of the fact that it will take so long, that I have to wait so long. I think Virgin Galactic also was not really aware of the fact how many engineering and technological and safety issues and problems they really would face with their spaceship design. So it was a long journey, about 10 years now. And as we all know, Richard flew last summer. So it looks that in Q3 this year, the first civilian passengers will be allowed to fly with the spaceship. So hopefully next year will be then my trip. And I have to say that it was a wonderful long journey over the past 10 years to be part of all this. And the center, of course, was the idea of flying to space myself, but so many other things happened then around this idea to do that journey and do that trip. And so many artworks then came out of this. And but then when it comes to the real flight, the physical, the mental, the visual, the intellectual experience, the overview effect, it probably will be a life-changing experience. And I always say that this will be then the climax and the end point to this series, but maybe it's not. I can't tell really what I'm going to do after that fly. But one thing is clear, of course, it's a privilege to have this opportunity to do that as an artist. And I think it's very important that artists now go to space. And it's my duty then also to share this experience to a large community, to many other peoples, to bring my experience, to transform that experience into artworks and bring that into exhibitions and symposiums and books and whatever, and to share the experience of the overview effect, because I really think it's absolutely necessary that in the coming decades, many, many more people, civilian people, go to space and have that experience.
I love the last pictures that you showed of Boca Chica, and
that's so insane. It's unbelievable.
And what I found fascinating about it, that it seems to have a different aesthetic, because it's literally in somebody's backyard. And it also looks like the way it's been built up, right? Like there seems to be a launch facility over there, some stuff happens over there, there's a hangar over there. It looks actually quite chaotic. You know, if you look at other launch facilities, I think, so is there a complete difference, you know, aesthetic and organizational aesthetic, you think, between Boca Chica and the other places that you visited? Is it a stark contrast, or is that just my perception?
No. I think it's a totally new idea of how designing and engineering. And Elon has a completely different approach, because normal is that you have a product you want to design, to build, sell. So you build a factory, and then when you have the factory, then you start producing the products. But the factory is built according, or the factory is built first, and then you do the products. And obviously, what's happening at Boca Chica is the other way around. So they start just building with little small shelters, the Starship. Yeah, so they just brought all the materials they needed, brought there, and they started to build the Starship. And then I said, oh, maybe we need a bigger hangar for the Starship. They started to build a hangar. And then we said, okay, maybe we build another Starship. So we need another factory where we can produce this. Oh, where do we store the engines? Maybe over there. So then we build a factory over there. And so it's just a growing factory based on a process of design, and also a process of try and error, because they have blown up, I think, 10 Starships so far, and they built, they designed, they built, they set it up, then it blows up, it crashes when it comes back, and then Elon goes to the crash site, looks at the pieces, and says, oh, we have to change the design of that part here probably for the next launch. And then the next Starship is just around the corner. And so that's the way how they work. And that might look totally different in 10 years, but for now, it's an incredible energy there. You really see the process of, or the interference of engineering, design, technology, and everything is just happening at the same time.
And it's good that you said it. It's like this kind of mixture of design and engineering, something that, you know, Melody, you mentioned as well. And are we moving towards this idea where design is not just part of what things look like, but maybe how the process works, right? Because design is messy, right? We try stuff out very early on, see if it works, if it doesn't work, you know. Do you see that, Melody, back to you? Do you think that is NASA is looking at that as well as a different way of process, or they're just kind of stuck in their own way and they're kind of how they approach it? Do you think there's learnings from that as well, from that process?
I think NASA as an agency doesn't have the same incentives to introduce value to a wider range of participants when we're talking about space flight. But the people who do are the commercial entities, so people like Blue Origin, Axiom, etc. They're the ones who are actually interested in creating experiences. I don't think that that's something that NASA has a vested interest in. And so when you get commercial entities that want to create and you know, sell and capitalize on experience, of course, design is going to come to the table. It's at the forefront of what that experience is. So what I'm finding is that it's really the commercial partners who are driving, just like Michael mentioned, the new space industry forwards. And it's going to bring a new value to what experience means in space and what it means to design for people in space. NASA as an agency is really intended to be the umbrella group to facilitate that work to happen, to ensure that the research is actually sound and that we're following standards and certifications that have been in place for decades, right? So it's an exciting time to sort of like infiltrate through, you know, one of these groups, one of these organizations, and see what kind of change can be made.
I think we have like 3 minutes left. What I'm going to do is, are there any more questions from maybe the other panelists that are still, because there was a bit of an overlap between this one and the previous one. We talked about space there as well. Any more questions from there? Let me just see if I've got in the Q&A anything. Okay, this is a question from in the audience. I'll just read it. First for Melodies, for you, I'll read it out. Let's do the last question. You mentioned that some of the 3D efforts were also simultaneously focused on housing on Earth. Can you talk a bit more about that and why designing for space offers a unique intervention into this critical issue?
So I think that the work that, not that I think, inevitably many technologies that are developed for space trickle down and present new value and introduce a new way of thinking about how we introduce problems on Earth. That ranges from like materials like, I don't know, antifreeze on airplanes, memory foam, technologies like LED lights, GPS. Like you never really anticipate the kind of, the kind of effect that these technologies have in the long term, but the reality is that they can change. They can change an entire way of sort of like commercializing these products on Earth. So I think 3D printing is in a unique position to change the way that automation happens in home building by using a single construction system instead of leveraging multiple trades, multiple materials, extending construction schedules, and really consolidating everything into a single system that can deploy on site and create a structure just as you would on the Moon and Mars.
Michael, Anna, Melody, thank you so much for the session. This was absolutely fantastic. We have to wrap it up on this one. Guys, I'll give the floor to you because you probably want to wrap this up now. Thanks so much. It's absolutely fascinating. Thank you so much.
Yeah, thank you everybody for joining us today. You know, really great participation from all around the world, speakers and attendees. Thank you so much, Norma and Javier, for all your help and work over the last few months. This is an effort that didn't come together overnight. We've been planning this, I think, for over 6 months, and it's exciting to see it all come together and everybody's so excited for it. So thank you all so much. And of course, to the rest of our team at the Visiting School and Public program who've also spent countless hours on this. Thank you all.
Thank you all, everyone. We're being thrown out of the AA, so it's the end of the day. It's been amazing, and thank you so much for the speakers, and hopefully we will have another iteration of this and we'll be able to continue. I see it very much as the beginning, and there's so much more. We could have had, I think, another 3 hours easily. So thank you, everyone, and see you soon.
Thank you, everyone. Thanks.
Thank you.
Bye-bye.